Hello. All right. Okay, there's good chairs over there. No, we're good. Thank you. Appreciate that. All right. Hi, welcome. It's actually kind of nice to see not so many people out there in the audience. It's a little scary when it's full. Not as much drama on the stage as last year. Non-electronic ears are a little bit more mellow. Okay, so, first off, I want to recognize that we stand on Southern Paiute land. Um, I'm a citizen of the Choctaw Nation of Oklahoma, but we should all be standing up for Indigenous rights. All right, and that's the button. Okay. All right, so my name is Mara Williams. You've seen my art around con for many years. My first art was DC 17. I've led development teams as a UX designer. I've chaired hackerspaces, and I've run a collaborative gallery. And I opened a new gallery in September called Feral. If you are in the Denver area, please come check us out. I did the design for the DC 31 badges and the DC 32 badges and ran the 32 badge team. You can find me in the vendor area or check out my Patreon, and I'll put up a slide later for that. This year's contributors, Bonnie Finley, who did the 3D modeling of the badge, so transformed the designs into 3D that we could use for manufacturing. ICSN is our manufacturing partner. And design support so that everything flows just right. With injection molding, it can get really tricky. Amy Valentine and Bonnie Finley did a lot of work on the black badges, and I can't show you those just yet, but you'll see them, and they're super cool at closing ceremonies. Thanks to Will Tuttle, who's my best friend and gets to listen to me rant and pull my hair out throughout the year, so thanks to him. And Sage, who is my monster up here for inspiration and testing every time a prototype comes off the 3D printer and I hand it to them and I'm like, hey, what do you think of this? So, all right. Okay, so one thing I want to speak to you about design, and something that I want to speak to you about last year, and where this is hard to talk about because I wrote this talk like 30 minutes ago. Okay, so bear with me here. So design in art, design and usability in UX design, it's this whole enchilada. It's this huge zoomed out thing, right? So it's not just like you put art on something and it's done. There's a whole lot of, one of my titles over the years was Human Factors Engineer, which is super dorky title, but it really like encapsulates how much work goes into the badge experience. And so that's kind of what I wanted to speak to about badge design last year, and how, you know, we had a hardware contractor who was just one small part of that puzzle. And it wasn't a very small part, you know, it was significant, but that there's many layers of this. There was also an entire game development team making a custom game last year, and I just wanted them to get the credit that I couldn't speak to last year. You know, I put everybody's names up, but with the drama, everything got lost. So I just wanted to touch on that and like thank those collaborators again for all the work that they put in last year. Okay, in design, in this whole enchilada of design, the majority of this work is invisible, and you just kind of see the finished product. And sometimes just the problems that come up along the way is like this year we've got a screw instead of a rivet, and so it's causing some problems with badges falling apart. And these are last-minute design decisions that come with the timeline and having to choose parts very quickly when, you know, getting 28,000 of something, even just a screw or a rivet, is pretty challenging. I have endless respect for the badge designers before me. As the badge project has grown over the years to scale with the conference itself, it's become more than an electronics project, right? It's a massive undertaking with so many moving parts, several different teams. Okay, so just want to speak to that. Okay, so this is kind of where I started out. I had this idea that was inspired by a jeweler's lens. If you've ever seen one of those where the little parts slide out. I had also taken some inspiration from the wings of a beetle, like a scarab beetle. So you can kind of see your badge splays out like little wings. And I had some concept designs along the way that were more beetle look, but I think it like kind of distilled down into this one, but still captures a little bit of that inspiration. I love color, and I love like color theory and how this all works. In 2016, I did a Denver Art Museum residency for 4 months, and there was a lot of exploration of additive versus subtractive color, and there's so much crazy making when you get down into like the little details and weirdness of color. And so some of the stuff that went into this badge was getting like the opacity just right and getting just the right shade of magenta, you know. So just lots of tweaking so that this badge would work. So if you notice around the con, there's art that interacts with the badge, and I have a picture of that here. So if you look at this cat, if you take the red and the magenta and the yellow lens together and look at this cat, the skeleton is going to pop out to the forefront. When it's up on the screen, you can also do blue, which in light it's different than, anyway. So the blue and the red lens together can get you like a really nice dark blue, and then you'll just see circuitry on its face. And if not, you can just switch to the cyan lens. So there's some tricks there that were fun to dig in. Yeah, I'm gonna go a little bit here. Yeah, so if you layer up the CMY lenses, then you get RGB, which is just really neat, fun. So I really wanted to do something with that concept. So you can do like a classic decoder where you have like a decoder from like a cereal box, 3D glasses, and there's some examples on the signage where you have a cyan lens. Again, you take the magenta and yellow, put them together, and you have the red on the other side. Part of the design was you have to be able to hold it up in place. And so kind of the size form factor is because I wanted people to be able to hold it up like this and do the, oops, got the wrong lenses on here, like this. Yeah, all right, and then if you want to see a really cool example of this in video movement format that's actually done not with lenses but with RGB lighting, I recommend checking out Jason Levesque is an really dig, and he's thing in Norfolk called Parent Seas. So here's our first like 3D rendering of the badge. So then how we got from sketches to this was a lot of back and forth with Bonnie Finley and 3D printing over and over and over again. Yeah, okay, so some of the challenges this year, literally right before we had to ship the badges, I'm sure you guys noticed that there was paper badges this year just for a minute before we got the rest of the shipment in. There was a typhoon in Vietnam, and it knocked out power to the factory for 11 hours, and that was during the period of time where the bulk of the badges were being made. So that caused significant delays for us. Tariffs. Tariffs were a crazy problem that we didn't know was going to happen, and Vietnam was hit hardest of a lot of places. And then that also impacted our timeline because people were like trying to book these shipments that were all happening at the same time as, because they're all trying to beat the new tariffs, right? So we had to compete with all the people shipping around the first. So that was tough, and that really impacted everything. And ICSN really came through with getting everything here as close to on time as we possibly could. Okay, here's an important thing that I've been wanting to say for a minute. I think it's important that it's said. I don't want to romanticize the idea that the badge designer can overcome all the odds and bring this crazy project to completion in such a short time, and that that's a good thing. This isn't a measure of my value. I take no pride in sacrificing sleep and well-being, and I don't think that people out there should be doing that with their projects or companies or whatever either. Like, take care of yourselves. Any manufacturing project at this scale, whether it be electronic or non-electronic, is almost impossible in the timeline of 1 year. So there's no room for errors, proper testing. There's manufacturer issues along the way that we can't address. Sourcing the right parts, that's also a challenge where we have to keep switching up what parts we're using. We have to switch up even just like the dyes that go into the plastics, things like that, because one manufacturer can't get them. There's no room for error, and no room for real testing. Like, I was still drawing designs, like, right at the end there, and trying to push them through before things had to get printed. And much love to DEFCON and all of that, but I personally will be moving to a 2-year badge cycle. So next year I won't be doing the badges so that I have a whole 2 years to do this well. Because I just want to do hacker stuff with my friends. I put this slide up last year, and working for DEFCON, anybody who works with conferences knows that, like, at a certain point, you don't get to go play anymore, and so I just really wanted to play. So I squeezed in a little bit of time to do a badge challenge this year. So you can find me near the Arts and Entertainment booth in the vendor area, and I have a big stupid pumpkin with buttons on it. Yeah, come check it out and press some buttons, and I hope you can figure it out. Yo Cookie, please support me on Patreon. It's Patreon/Spucks. Follow my Instagram. It's Spuckso. Yeah, so I post all my art there. Yeah, and come support me in the vendor booth area. I have shirts and stickers and all kinds of things. Yeah, so if you have any questions, I'll see if I can see you past this really bright light. All right, I guess that's it then. Thank you so much. I can't wait to see all your badge life stuff. This has been a great con, and we still got, all this time today and tomorrow left. So, thank you.
Mike. There we go. Good morning. Good morning, DEFCON. Hey, we made it to day 2 officially. Well, we have some new speakers here, and as we know, we have a tradition called Shot the Noob, to take a shot with the speaker. Um, so we'll go ahead and do that now before we kick off the talk. Cool. We'll go ahead and get started. We'll have Zhengyu Liu and Jingye Yu present on the domino effect. Let's clap it up for them.
Hello, everyone. Should we get started? Okay. So, hello, everyone. Welcome to our talk, The Domino Effect, Automated Detection and Exploitation of DOM Clobbering Vulnerability at Scale. So, I'm Zhengyu Liu, and this is my collaborator, Jianjia Yu, and this joint work with Tao Li, Zifeng Kang, and my advisor, Yinzhi Cao. And we are both PhD students from Johns Hopkins University, focused on web security and software security. And we spent our most of time studying vulnerabilities, building security testing tools, and thinking about how to make the modern world a better place. And today, we're excited to share our research on DOM clobbering. So I will first start a very quick overview of what DOM clobbering is, and then explain the challenges of detecting those vulnerabilities at scale, and introduce our automated analysis framework, HAWK. And after that, Jianjia will take over to present our large-scale zero-day hunting results and show how we turn those HTML injection into the end-to-end exploits with DOM clobbering gadgets we find. So let's begin. So DOM clobbering originates from an old but still standard browser feature defined in the HTML specification. And it allows you to perform named lookups on window or document objects to access elements on the page. While this feature provides a convenient way to reference like DOM elements by their ID or name, it often opens the door to the DOM clobbering attack in the scenario where those elements are attacker-controlled and it wasn't the developer's intention to use them at all. By crafting a name collision between the DOM element's ID or name attribute and a property accessed via like the window or document, the attacker could pollute the JavaScript value and change the application logic. So, and especially modern web applications often accept a wide range of user inputs, including like scriptless raw HTML to support things like rich text formatting or like embed media. For a more concrete example, to give a illustration for people not very familiar with this, is that at first the attacker needs to inject an A-link or element to the page. And then the page contains JavaScript that probably reads from like window.remote to load additional scripts. And if it's undefined, it fallbacks to use like a CDN URL and load script from there. However, with the attacker inject link whose ID equals to the remote, the lookup is no longer undefined, and instead it refers to the injected A link, and this is what we call a clobber. And later, like when the DOM element is concatenated with a string, type coercion occurs, and for those link elements, this converts them from a DOM element to their ref value, and producing a URL controlled by the attacker. And finally, the URL flows to the script.source and resulting in loading malicious code from attacker's domain. Since DOM clobbering was first introduced by Grace Hayes in 2013, a lot of work has been working towards understanding various clobbering techniques. And at the core, the key question is which HTML markups can clobber which JavaScript targets and probably under which browser implementations. because clobbering behaviors is defined in the HTML specification, but the browser implementation varies slightly. And building on years of the findings and also the updates from the browser, the recent paper from Auckland 2023 called "Is Clobbering Time?" is the first to systematically answer this question. It uncovered like over 30,000 clobbering capable HTML markups across 5 distinct techniques, making a real scientific forward in this field. However, identifying those clobbering behavior is just the initial payload landing step of the attack. And for the full exploitation, we still need the gadgets and the exploits. So the following question is, can we automatically detect those gadgets and generate working exploits so that we can really testing them at scale and better understand its landscape in our modern web? And this is where our work comes in. So to do that, there are 2 main challenges. The first one is that real-world JavaScript, especially after minified or bundled, is full of dynamic behaviors like aliasing or directed property lookups. And it's very unfriendly to our static analysis tools. And those features make it extremely hard to track how data flows through an application, and in turn makes the gadget capture a very hard problem. The second challenge is exploit generation. In DOM clobbering, the payload is no longer a string, which is usually the case, but it's a DOM element. And that elements need to be compatible with the JavaScript operations in the gadgets and carry the attacker-controlled values to the sensitive sinks. And if the element itself is malformed or is not incompatible with the gadgets, it may break the code and just fail to propagate the payload. Okay, now let's take a look at a motivating example and show how those challenges failed our existing approaches. This is a 0-day cross-site scripting caused by DOM clobbering found by Hawk in my favorite write-up platform, HackMD. The HTML injection was possible because the developer allowed the name attributes on the iframe tag, unknowingly exposing its application to the DOM clobbering. To escalate the HTML injection to cross-site scripting, Hawk found a vulnerable gadgets from the Google Client API library used in the page. And the Google Client library is used by a website that tries to integrate the Google service like Google Drive, Google Maps, or YouTube. And once the library is loaded on the page, it will process the developer-defined configurations in the page and callbacks embedded in the page, and by searching the corresponding script tag that contains the configuration URL. And then we'll use a new function, which you can dynamically generate a function, generate a JavaScript code by parsing those configuration objects and execute its code. But here's the problem, that the source it uses, document.script, is vulnerable to DOM clobbering. So the attacker can inject a clobbered DOM element that is not a script, like an iframe with a crafted name equals to the script to hijack the configuration object. And combining the HTML injection and the DOM clobbering gadgets in the page, the attacker could achieve cross scripting by sharing a malicious HackMD nodes and probably perform any unauthorized actions on behalf of the user. And till now, both the HTML injection and DOM clobbering gadgets have been fixed by the HackMD and the Google respectively. And let's talk about the private work. The thing is a static analysis tool that tries to detect this by looking at the source code. But it fails to detect it because of the dynamic behavior and condition logic embedded in the gadget code. Secondly, exploiting the gadgets requires HTML marks that satisfy both the data flow and control flow constraints along the chain. The data flow constraints ensure that the payloads can flow from one attacker-controlled variables to another, while the control flow constraints ensures that the program state execute the JavaScript, execute the gadget's logic, so we don't execute it earlier. For example, the constraint 2 involves a subscript operation of the clobber value. So this means our clobbered objects must behave like a collection, such as HTML collections. If just a single element, the access on it will throw a runtime error, and the gadget log will just fail to execute. And the thing fails to generate a working exploit because it only considers the initial clobbering pattern, but ignores all the constraints in the gadget code. And as a result, it produces payloads like image name equals to script that would never reach the sink. Another popular client-side testing tool, DOM Invader from Postfigure, failed to detect it because it relies on a canary-based testing. Well, this approach works very well for string-based exploits by checking whether partial attacker-controlled value reached the sink. It does not apply to DOM clobbering, because DOM clobbering requires a near-correct HTML element and considering all the constraints from the gadgets. And randomly generated HTML will just never reach the sink. Or even worse, it will just break the website functionality and skip executing many real gadgets. Okay, now let's see how we solve the problem with Hawk. Hawk operates in 3 stages. So our key insight here is that instead of directly injecting HTML markers from the start, we first perform the tint tracking on website-defined values from those potential clobberable sources to the sinks. And this phase is non-intrusive and helps us identify a wide range of potential gadgets without needing to guess the payload. And next, based on the tint trace, we extract the data flow and control flow constraint and use them to generate the corresponding exploit markups. Finally, we insert those craft markups to the page and replay the execution and check whether the payloads reach the sink, confirming whether the gadget is really exploitable or not. Specifically, in the first stage, Hawk performs dynamic tint analysis on website-defined values. We categorize the source into 2 tabs. First, the lookups on document can be directly shadowed by the attacker-injected values, like document links, document scripts. And in this case, we can directly tint the original values and observe how they propagate in the program. And second, there are lookups on like a window object where the attacker clobber value is only used if the original value is undefined. And this is typically appear in like those fallback expressions like ternary operators or like logic or checks. And in such case, Hawk will track those fallback values instead and identify opportunities where the attacker-controlled value might take effect. And Hawk will only inject its own value, like random value, when there is no website-defined value is present as a fallback. The sinks used in our tint tracking are typical like client-side sinks, like inval, set, timeout, and others. The tinted value in the page are managed in 2 ways. For objects with properties, we just insert another like specific field, non-enumerable property, so that it doesn't interfere with the normal program behavior. For those primitive values, which are very hard to be tinted, we wrap them with a special object that holds both the concrete value and its tint metadata. So this allows us to track even undefined values. Our tint engine supports propagation across JavaScript operation, built-in JavaScript built-ins and browser-native APIs, and so on. And the tint propagation rules are implemented in a very extensible way, like adding support of a new APIs is as simple as defining a single handler function. And we implement the tint analysis using a code rewriting approach based on Geology instead of instrumenting the browser itself. It gives us a very flexible feature and allows us to track all types of JavaScript values and supports cross-browser analysis without relying on the browser internals. The output of the first stage would be the tint trace represented in a tint dependency graph. And the backbone are the operations, and there are concrete values and also the attacker-controlled tinted values. Next, the challenge would be, once we have this tint dependency graph, like how do we generate the HTML markups that can leverage those operations observed in the graph and carry the attacker-controlled string all the way to the sinks? And in the second stage, in this stage, like we will introduce the concept of a symbolic DOM, which allows us to formally define the constraints that DOM elements must satisfy at each step along the path. And then we implement a simple DOM constraint solver that uses those representations to automatically generate the compatible and exploit-ready HTML markups. So the first step, to model, so we need to understand what a successful exploit would look like. So to model a valid exploit, we treat the HTML payload as flowing through 4 key stages in the tint dependence graph. The initial clobbering, where the attacker's DOM elements first inject to the JavaScript program. The advanced clobbering, where some parts of the first injected DOM elements get loaded and to the program. And the third stage is DOM to string, where the string payload loads from the attacker-controlled DOM elements to the page. And the final stage is string to string, where the string is processed or transformed and finally flows to the sink. In the first stage, the DOM elements should contain an ID or name attributes correspond to the named lookup keys, which is quite straightforward. On the second stage, the attacker-controlled elements must be further loaded. And this stage is only necessary when there are additional JavaScript operations before the string payload can be loaded. And since we cannot skip any JavaScript operations in the graph, so we need to use this advanced clobbering techniques to fulfill them. And the problem would become, if the base object is an attacker-controlled DOM elements, how do we form it in a way to make the results of the operation could also be attacker-controlled DOM elements and without raising any error? And there are few strategies can be taken. The first way is HTML injection, that we can inject multiple DOM elements with the same name attributes and it will look like an array. The second way is to use the well-known nested window proxy, parent-child, or input form those relationships to clobber lookups, whose property is a general string. And the third way targets a certain DOM-specific properties like previous symboling, and by arranging the DOM elements to match the expected structure. And later on, when the attacker, there might several rounds of advanced clobbering, and later on, the attacker needs to load its string from the controlled DOM elements to the program, because the final payloads shown in the sink should be in a type of string. And there are three main ways to achieve this. The first is the well-known technique through type coercion during binary operation like add. And it applies to the A and area elements, where accessing those elements triggers the use of its ref value as a string. The catch here is the ref value must be a valid URL, and browser will often auto-fix it with a protocol like HTTPS or whatever is used in the current page. And to bypass this, attacker would need to inject a base tag before the clobbered element, controlling how those relative URL are resolved. Another two-stage operations can be leveraged are function calls and get field, which is less documented. For the function calls, some JavaScript built-ins and the browser APIs would automatically coerce its argument or property values to string. So in that case, if the attacker control value is passed to those or accessed in this way, the browser would perform the coercion just like those during the binary operations. The third way is to exploit the attribute name collision. Like if a property name matches to a legitimate reflected DOM attribute, it can be abused. For example, if the application reads the value property from the element, then the attacker could inject an input tag with a payload saved in its value attribute because it's a valid attribute name. And our paper includes a comprehensive list of those attributes and APIs can be used in this stage. And finally, there would be a rise of a string-related transformation and finally flows to the sink. Okay, so we know what a legitimate DOM elements should look like. To describe those in a formal way so that we can solve them, we need this symbolic DOM syntax. So it's basically a constraint syntax to describe a set of DOM elements with the same list of features. And it counts 4 primitives: int, boolean, string, node, and a collection. And each node represents a DOM element which can have a tag name and several attributes. And a node can have siblings and children. And a valid symbolic DOM that can be concrete to the HTML must have one root node. And then with each operation type and also the stage we just mentioned, we could generate the constraints on the inputs or output elements used in the operations. For example, to achieve document to DOM through the document.p operation, the DOM elements can be described on the page. Whereas the is root has tag name and has attribute constraint. And when p equals to the script, so we can concrete to a very simple HTML element. And with those model constraints, we can traverse all the operations nodes and attach those constraints to the attacker-controlled nodes. And each attacker-controlled node in the graph should have two conjective sets of constraints, as it serves as the return value of its precedent operation and the arguments of the subsequent operations. And finally, we need to merge and solve those constraints. And the key insight here is that we start from small and then connect the dots and finally concrete to the HTML. So what does it mean? It means that first we focus on the local constraints like C1 and expand it into a disjunctive norm form or DNF form. And in this form, each local constraint can represent a valid, possible DOM trace that satisfies those constraints. And next, we will merge the formulas across different DNFs if they point to the same tinted nodes. And during this process, conflicts may rise, and we just need to get rid of them and only save the valid combinations. And you can think of the second stage as attaching different DOM trees at their shared nodes, and discard any combination that doesn't fit together. And in the last step, we'll just concrete the formulas to the HTML marks as exploit. And finally, in the last step, we would just inject our generate payload and replace the web page and see whether our canary value from the exploit could really flows to the sink. And next, I'm going to hand over to my collaborator, and she will show the results.
Hi. All right, so let's get to the real exciting part. Now I'm gonna show some real-world examples we found with our tool Hawk, as well as some. So those include some DOM clobbering gadgets in the wild, in web applications and libraries, and also end-to-end exploitations. So first, we apply our tool Hawk to Tranquil top 5,000 websites and found 497 zero-day exploitable gadgets. So our cases include modern web bundlers like Webpack, RSPack, Vite, TSUB, Polyfuse, and some core functional libraries like Prism, PageFind, MassJax version 2 and version 3, and also some third-party services including Plausible Analytics, Google Client API Library, and also web application frameworks like Astro. Our dataset is public. You can access the whole dataset through this QR code if you are interested. So the first case I want to show you is the Webpack. So according to an investigation, there are an average of 1.27 Webpack bundles per site among the Tranquil top 100K websites. So this vulnerability we found by Hawk can lead to cross-site scripting on websites that uses Webpack as the bundler. So in case you're not familiar, so the pipeline of using Webpack is like this. First, you have to feed the website source code to the Webpack to generate the production code, which includes the compressed website code and also the Webpack runtime code, which is the Webpack library code. And in that Webpack runtime code is where we found the DOM clobbering gadget. So with that DOM clobbering gadget, if that website contains an HTML injection, this gadget can cause cross-site scripting. So let's jump into the code gadget. So Webpack requires the developer to set the public health to be auto, or you can either leave it to be empty in hope that the Webpack will help you load some external scripts. But actually, it is doing more harm than you think it is doing good. So if we pay attention to the code itself, in the first box we marked up, so the document.current script can actually be clobbered. And then in the box 2, the script URL is loaded as the document.script.source. So in this case, if we construct our payload like this with the source equals to https://https attacker.control.server, that script URL will be an attacker-controlled control URL. And then later, finally, this script URL is used as the webpack require.p, which will be later load that script from that attacker control domain. So that will cause arbitrary script loading from the attacker server. So the second case I want to show is the Astro. It is a widely adopted client-server web framework to help you construct a web application from scratch. So in this code, we can also find DOM clobbering gadget where the clobberable element is called is here the document.scripts. But this case is a little bit special. So if we pay attention how the document.script is used, we can see it is accessed through array.from. So the code is treating the document scripts as an array, not just one single HTML element. So in this case, we have to construct the payload as an HTML collection instead of just single one HTML element. So, and then if we jump into the for loop to see how do we reach the final sync, we can see two conditional checks before we reach the sync. So the first condition check checks whether the script.dataset.astroexec is equal to an empty string. And the second condition checks check the type, which is an attribution, which is the type attribution of the HTML element we got before. So to bypass those two condition checks, with our payload, the first script.dataset is undefined. So the first condition will return false, which causes the code to continue execution. And then when we reach the second condition, the type, again, in our payload, the type attribution does not exist. So the second condition will also return false. That will finally lead us to the final sync, where the new script is loaded from, new script is created as a new element with a script type, and then its inner HTML is copied from the payload's inner HTML. So finally, we can achieve arbitrary code execution if we construct our payload as this HTML collection. So in our case, the inner HTML will be alert1. That causes the cross-site scripting. And then the finally case study I want to show you is the editor. It's an editor previously maintained by Baidu. So in this code, it's a little bit straightforward. So if we can see the clobberable element is the window.umEditor_home_URL, which in our case will be the HTTP attacker.control.com. And then later, that variable URL is used to be assigned to a global variable, umEditor_config. And then later, that variable is concatenated with some constant strings to construct the final URL that will be that the code will be loading the script from. It is also causing the scripts being loaded from the attacker's domain. So finally, I want to talk about the end-to-end exploitation. So to understand the end-to-end exploitation, we first need to achieve HTML injection. So as mentioned before, the web application, they accept and process all sorts of user inputs. But how does it become unsafe? So we have some basic findings. So first, some sanitizers from these websites, they do not strip the ID or name attribution by default. And the web applications, they're not aware of this DOM clobbering vulnerability, and they rely on those ID or name attributes for intended logic. So due to these reasons, the ID or name attribute, they sometimes slip through the whitelists as they don't seem harmful at all. So based on how these web applications process the user inputs, we categorize the input factors of HTML injection into two types. The first is by user typing and the application rendering. The second is by the user copy and paste HTML elements into the page directly. So the first case is easy to understand. The attacker might input some raw HTML strings, such as the image tag with source equals to X and on error equals to alert1 into some user controllable fields. And then those strings are later parsed and rendered by the web application without proper sanitization. So the second input factor is to insert through copy and paste HTML elements into the page directly. This is based on several factors. The first is that the elements whose content editable attributes is enabled, they can accept HTML elements directly. And second is that the clipboard data can have text or HTML MIME type, not just plain text. And also the browser clipboard APIs, they would sanitize cross-site scripts, but they do not sanitize ID or name attributes. As mentioned before, they don't look harmful at all at most of the cases. So based on these factors, what if the website just saved these HTML elements input from the user or attacker without proper sanitization? That will cause the stored HTML injection. I will show you with one real-world example we found. So this is the Canvas LMS discussion at JHU in our school. So in the discussion board, in the input box, if you just directly input some raw HTML text into the input box, they will be sanitized. But if you directly copy and paste HTML elements into the input box, the website will actually accept those elements and render those elements in the website. That will cause the HTML injection. This is usually caused by the web application developers. They are mostly cautious about user inputs by typing, but sometimes they are just careless about the contents from the clipboard. That's why it's causing HTML injection in this case. So we also manually hunted for HTML injection in the wild in real-world web applications. So we manually discovered 187 HTML injection vulnerabilities in various web applications, including wiki, webmail, forum, editors, RSS, social media, chatbot, and so on. And we also summarized 12 editors and client-side libraries that are vulnerable to HTML injection. They can also be accessed in our public dataset. And then in terms of end-to-end exploitation, with all the DOM clobbering gadgets we found by Hawk and also the HTML injection vulnerabilities we found manually, we can achieve 12 end-to-end exploitation with those gadgets and HTML injection. So those includes 11 of them leading to cross-site scripting, and one leads to CSRF. And the affected applications include the Jupyter Lab or Notebook and also Canvas LMS. So let's dive into the Jupyter Lab or Jupyter Notebook for details. In summary, we found HTML injection in Jupyter Lab, Jupyter Notebook webpage, and also we found DOM clobbering gadget with Hawk in MathJet, both version 2 and version 3. The MathJet library is used by the Jupyter Lab to render mathematical formulas. And combining those two together, we can achieve end-to-end exploitation. So in terms of the HTML injection, we found that in the markdown preview page of Jupyter Lab, if we insert some, if we just type in raw HTML tags, for example, image or whatever HTML elements, it will be accepted and rendered in the web page. And we also reported this end-to-end vulnerability to the developer of Jupyter Lab. And they also confirmed that it is not trivial to mitigate this vulnerability because the ID and name attributes, they are assumed to work by a large number of widget libraries. So a very easy example is that, for example, there's a markdown file with 2 hashtags hello. This tag will be rendered as an H2 element with the ID equals to hello. And the ID hello will later or somewhere be used as the fragment identifier in the URL to locate that element in the page. So if we take a look at the MathJax library, it is a library widely used to render mathematical formulas, and it is used by the Jupyter Lab. So with our tool Hawk, we found DOM clobbering gadgets in both MathJax version 2 and version 3. And just days before they released version 4, and they promised to fix this vulnerability, but we haven't checked yet. Just say good luck. Okay, so if we take a look at the MathJax version 2, we'll find the window.mathjax here is clobberable element. And then later that variable is concatenated with some constant strings to construct the file URL. And here a type coercion happens. And finally, that file URL is used to the script.source, which is to load the attacker-controlled scripts. That will cause cross-site scripting. And but if we take a look at the version 3, just at the first glance, there is no more clobberable window.mathjax, and there is no more loading of additional dependency scripts by default. But by leveraging Hawk, we found that MathJax version 3, they supports using the require macro, which allows you to load extension scripts. So we further from that, in version 3 of MathJax, there is a clobberable element called the document.currentScript. And then later that document.currentScript is document.currentScript's SRC attribution is get, and with some regular expression replacement operation, the string from that payload is retrieved. And then finally, that t variable is assigned to the r.src, which is the SRC attribute of one script element in the page. That is also causing loading scripts from the attacker's domain. So, okay. So till now, we have both DOM clobbering gadgets from MathJax, both version 2 and version 3. And also with our research on DOM clobbering, we reported those problems, and Firefox is also considering patching the DOM clobbering by disabling the shadowing on document lookups. And they are referring to the zero-day gadgets found by our tool Hawk. That's good news. So to summarize, we design and implement Hawk, a dynamic analysis tool for automatically detecting and exploiting DOM clobbering gadgets. And we also conduct a large-scale study over the top 5,000 websites and identify 497 exploitable gadgets, revealing the widespread presence of DOM clobbering vulnerabilities in popular client-side libraries. And also, we demonstrate 12 end-to-end exploitations by combining the discovered gadgets with real-world HTML injections, validating their practical impact. So our tool, the source code, the dataset, and the paper are all open source. Feel free to access them if you are interested. And also, both of us, Zhengyu and Jianxia, we are open to internship or full-time jobs. So if you have any opportunities, please feel free to reach out to us. Thank you.
More videos. I know. I know. I know. Yep. I don't know why. Okay, here he goes. Okay.
What the hell is Cyrus? What the hell? What the hell? What the hell? What the hell Ante? What the hell on? What the hell Barry? What the hell Burton? What the hell Bron James? What the hell Cyrus? What the hell? What the hell? What the hell? What the hell Ante? What the hell on? What the hell Barry? What the hell Burton? What the hell Bron James? What the hell Cyrus? What the hell? What the hell? What the hell? What the hell Ante? What the hell on? What the hell Barry? What the hell Burton? What the hell Bron James?
Never mind.
What the hell Cyrus? What the hell? What the hell? What the hell?
Okay, we're ready to start. A little bit delayed. All right, need a drink after all of that. We got some technical difficulties in the beginning. I'm sorry, we're gonna start 3 minutes late. Everyone in the back who wants to see technical stuff, move forward, because the video demos would have text in it that I'm not sure you'll be able to see way in the back. All right, so quick intro. I'm Mickey. That's Jesse. We hack things. We give talks. That's who we are. There's a lot of stuff online. We work for a company called Eclipsium. We want to mention them because they help us fund all of this stuff. Quick terminology. For those unaware, UART is a serial communication protocol that you wow, it's really distracting, the noise from the other place. Don't tempt me. Okay, so UART's a serial communication protocol, usually in IoT devices, OTA over the air, UVC, basically, read it yourselves. One thing I want to be clear about that I do want some participation. If anyone has a question, shout, because I can't see anything. I have a light in my eyes. So either come to the microphones and ask us a question, or interrupt, yell, everything's cool as long as you do it, you know, with taste. Another thing I want to be clear about, there's multiple ways to hack a thing. We did it one way. I'm sure there's at least 12 people here that can do it better. I'll start with a story. Back in the COVID days, we did a lot of e-meetings, you know, video calls, all that stuff, and I needed a good webcam. So I found one that did 60 frames per second. I'm like, yeah, I buy it. I plug it into my computer, and then a year goes by, and it starts to be flaky in meetings. And I'm like, okay, it's been on the market for 2 years. There must be a firmware update that I haven't applied yet. I should go and apply that. So I find the firmware update tool. I go on their website. I download it. That's the URL for the web archive for the original tool. I recommend that you save it because it's no longer on the internet. So I download the tool and I install it, right? Run the installer, get the GUI for the installer. It automatically opens it up. It shows the camera, the firmware version. But did you see it? It extracts into a folder. Me being an inquisitive mind, I'm like, okay, something sus here. I open and look at the files. You see it?
Wait a minute.
I take a closer look, and I look, and I say to myself, like, what the fuck? Why does a webcam need almost an 8 meg firmware update? So take a look at it again. There's a .sh script. Keep in mind, this is a Windows updater. U-boot, a USB update binary, some weird-ass looking file, OTA, and an auto-update TXT. Okay, something is off here. I like to hack IoT, so binwalk. I swear, this is one of the most beautiful binwalks I've ever gotten in my life. If you ever run binwalk, you see a lot of sometimes noise. This is the whole dump. This is how the firmware for the camera looks. Now I really have to open this device, and it's like hard. The front panel is glued in. I rip it apart. I open it up. I look at the back. I see an SoC. You see this stuff? You go like, okay, I'd expect to see a chip on a webcam, you know, USB to the chip. The chip does its, you know, conversion of the image, passes on the USB. Normal stuff. What you'd normally expect from a Linux running target or a system or a device is to have the trifecta: the CPU, the memory, and the storage. I didn't see memory, so I'm like, okay, weird. Look at the back, I see a SPI, and then I see these pads. I call them sus pads. It's 3 pads on the middle of a PCB. I'm like, okay. Turns out they're UART. So maybe I can hotwire this thing. So I hotwire it, and this is what I see. Okay, so at this point, I'm a bit processing. I'm like, okay, what did I see? I see Linux on a CPU, what Linux version, firmware version, and this is the exact process of emotions that I've had at the time. Then it turned into this, and then it came into that. Okay. I'm going to hand it off to Jesse now.
So we've already seen some kind of suspicious things already. So we started to dive into what the firmware update process actually does and how that works. So the way their package arrives, you have this firmware tool executable, and then a couple DLLs. There's this HD510 SDK DLL that has most of the update code itself. And then it has a helper function that's this AIT UVC extension API. It's basically just used for, there's something in UVC or USB video class, it's called extension units, and those are used for configuring different things about the camera. This really, most of the update code runs in that HD SDK. It only calls 3 of the functions through this helper. There's a lot of other stuff in this extension unit helper library that is used for other types of devices. So they just pulled this in for a few small commands. And then together, those will take instructions from the autoupdate.txt, which will then basically parse commands from the OTA and send commands and the firmware file to the device itself. And if you look at that auto update, it just has this E* command, and then the name of the other file to parse, and then reset. If we look in the OTA, these are even more suspicious because it's just SF probe. It's like spy flash probe, and we're probing chip select 0. And then spy flash erase, this particular region offset, this particular size, and then it's TFTP transfer. That doesn't really make sense over this USB interface for how they're doing it, but we'll go with that and then write that region to that offset that they just erased. And this is literally the full update script that it runs. We take a closer look at how this actually works in the internals. I mentioned the UVC extension units. They're only doing one call to get a property for this specific vendor extension unit to get the firmware version, and then also switch the camera into firmware update mode. Extension units are used for a bunch of other things for different cameras, like if you have like a pan, tilt, zoom, all of that, those are configured using extension units. But when you send this specific vendor-specific set property, it reboots the device and comes up as a mass storage device, which is kind of interesting. And then from then on, it's using SCSI commands, basically SCSI pass-through commands in order to use vendor-specific SCSI opcodes to continue sending command and data to the device. And then it also sends this interesting USB updater.bin and uboot.bin for the camera to run during that update process, which is also something that we're concerned and suspicious about. But here's some of the code. It's just doing the open device by path using that helper library, and then sending this extension set with a specific GUID and then a specific control selector to say what specific request I'm doing within this extension unit. Once it does this, it just starts waiting and looks to see, has a new mass storage device popped up? Can I find the specific device I'm looking for? So at that point, it starts sending SCSI commands. If you look at the bottom, there's this device IO control. The specific ioctl number is OX4D004. That's the specific ioctl for SCSI pass-through. And it's used for other mass storage devices. But in this case, we're just sending an inquiry request where we get information back from the device about the specific device from this inquiry request. In this case, they're using this in order to determine what mode the camera is operating in. So after it reboots, it comes up in what's called ROM mode. And by doing this inquiry command, they can determine if it's in ROM mode. Based on inside of the buffer, it'll have a G or a C at a specific offset. If it has a UPD at a different offset, it's in update mode. And if it's in UBO, it's in U-boot mode. And the way that this works is that it will transition the camera into update by sending that UVC extension unit request. And then it'll send an inquiry. Once it's in ROM mode, it'll send the updater. And then once it's in updater mode, it'll send U-boot. And then once it's in U-boot mode, it'll just literally send U-boot commands over that mass storage channel that it's still using, which is kind of an interesting way to do this. So they are using vendor-specific SCSI opcodes to transfer data. The TFD command, instead of doing network operations, they have special handling to convert that into, there's a load info command that they send, which says, here's the address to load this at in memory, here's the size, and then the update tool itself will then calculate a MD5 hash, pass that over, and then start sending chunks of that buffer in multiple different SCSI write requests using that specific vendor opcode with a sub opcode to say, these are the chunks, and then the last chunk has a different sub opcode. But all the other commands are just sent as literal strings to run and by the camera to interpret in this U-boot that's running for you now. So when you're looking at the camera UART itself, it basically looks like this. And you can see the camera is running, and then it switches into U-boot mode. And waits a little bit while it's doing things. And you start seeing things like this run command at the end. Those are literal commands that are being run by this, that are being sent from the updater tool to be run by U-boot in the camera. So it'll do the run commands, and then it'll do this operation of erase, transfer the data, and then write. And we can look at this, and these basically map to our commands that were in that auto-update.txt, or the OTA txt. One interesting thing that we notice is, like, if you look at the order for here, they're erasing the SPI region, and in this case, they are erasing only the root file system and the kernel. So they erase the file system, and then they transfer the new image to update. So if you look at the bottom there, there's an MD5 pass. What happens if that fails? If there's like an if there was an integrity problem while they're transferring that file, maybe it was a file that isn't going to work, they've already erased the image, and there isn't really any retry and send the firmware file again if that fails. So that's another thing to take a look at. But at this point, it's a pretty straightforward method of how we can do the updates. I'll pass that back to Becky.
Spoiler alert, it bricks the camera. That was easy. So we've seen their GUI and their tool and everything. Can we just simplify it, make our own tool? Because they're using the third-party API from some SoC vendor. Short answer is yes, and it's in C#. And the simplest thing is because we got lucky and the firmware update tool is in C#, we threw it in our IL disassembler and got the disassembly and hacked it together. And you can convert it to PowerShell if you'd like. It's fun. And it works the same, calls the DLLs, and fun. So a quick topic change. Why the fuck would you put Linux in a webcam? The quick answer is basically money. If there's a company that sells you an SoC that has all this integrated already in it, and it works, and you just got to rebrand it and maintain a small workforce of people to maintain the updates over a couple of years that already do other things, it's cheaper to do it that way, but it's not always secure. The way it looks is like this. The SoC vendor is called SigmaStar. They make this chip. You go on their website, they sell all these kinds of SKUs of it. They do for webcams, IoT, all kinds of stuff. They are a subsidiary of a company called MStar Semiconductor that doesn't appear to be alive. It's only on paper, and that is a subsidiary of MediaTek. Out of SigmaStar's SoCs we've identified so far, we've seen in TP-Link, which credit to TP-Link, they do publish their GPL code, which is great. Nexago and OBS Bot. Never heard of these before this research, but we'll get to that in a second. When you go to their website, the good thing about these companies when they want to sell their product, they build a full vertical stack of everything you need. So the SDK, the code, the documentation, the data sheets, the examples, everything. You go to the website and you get all the data you need. That's the link to go there. You do need to create a credential. Supposedly it will get you access to the source and the SDK. I have tried, I think it's been 2 months with 2 different accounts. One at Gmail, one is Gmail didn't work, so I went with my corporate email to see maybe they filter. No, they just don't give a shit. There's no data, there's nothing. It is like pulling teeth. It's terrible. So what can you do? So do it yourself. You go Google things, GitHub things, look in the forums. Surprise, you can go through LinkedIn and you can go through Twitter. Why? In a second. So the process is like this. You Google for the files, you find them on GitHub, you find them on Google, and you repeat this over and over and over and over again. And if you can go into the Russian forums, you get bonus points. There's a GitHub repo with GitHub user with 4 repos. One of them is the actual USB tool from SigmaStar. It's a bit an older version, but they keep things the same way over generations because people are lazy. If it works, they just keep it moving over the years, the technology. You get the U-boot, you get the Linux, you get their SDK. The next 2 are open directories. So you just find random stuff in open directories. And the last one is an OpenIPC kind of sort of implementation. OpenIPC, if you don't know, it's for internet cameras that you can use open source code to do it. and it supports SigmaStar's chipsets, so they do have a kernel for that. So like I said, no help from them. I thought maybe there's a chance. Nothing. Forget about it. The only other thing we could do is reach out to Lenovo and say, can you give us the GPL code? And this is how it went. We asked for the GPL code. Lenovo asks SigmaStar for GPL code. SigmaStar gives Lenovo the code. Lenovo gives us the code. We build it, it fails. We go to Lenovo and we go back to Lenovo and say, we need more, it's not complete. Again, cycle. We get the code, it works. We build all our demos for the talk, and then we're like, you know what, we want to take the extra step, do something. We did something crazy, let's do something even more crazy. We requested the GPL again, and nothing yet. Hopefully we'll get it. So we do have the U-boot, we have the kernel, we don't have the latest SDK. We have a bunch of stuff from GitHub. What can we do? We do know the structure of how it looks. They do have, for the same SoC, you can build either for SPI NOR or SPI NAND. In our case, it's a NOR. This is how the partition looks like. We're going to focus on these two because it's easy. It's the easiest way for anyone to get into this world. Just build a kernel or modify a file system. And that's what we know. We know, this is what we know. We know the camera runs Linux. We know how to build a Linux. We know we can flash it. We know how to flash it. So here comes the fun part. Can we turn the camera into a rubber ducky? Spoiler alert. There's the demo number 1. We have a laptop. We have a camera, this one. We plug the USB in. I opened the camera app on the background just to show. I disabled the built-in camera. The camera spits out a text, and then it reboots into normal, regular code. Take a picture of him too. Okay, cool. And that's it. So we took the kernel, we built it, we added the HID stack, USB gadgets, cool. The camera boots up, it's a HID, it's a keyboard, it types in stuff, it's cool, it's funny. What? There's more. So how do we do that? The file system is read-only, right? It's a SPI chip, it loads it to memory and then runs it, and every change you do doesn't persist across reboots. So it turns out there's a section in memory that's called environment variables. Every system usually has it. In this case, we just added our own variable called implant, and the camera our code in the camera checks if implant is 1, run the HID payload, change it to 0. Next time the camera reboots, implant is 0. If the implant is 0, boot into the normal Lenovo flow. That's it. This is how it looks from the camera side. The camera boots, you see implant equals 1, means run the payload, start sending keystrokes. This opens an admin command prompt and starts saying, psst, I'm your camera. This is an admin command prompt. I'm going to become a camera now. It reboots. Implant is now 0, and it just follows the normal Lenovo boot flow, and it's a regular camera. Okay, let's change gears. For some god-awful reason, the RCS script in the camera has Telnet D starting in it. So can we have a network gadget on the camera? Let's try it. So we plug in a camera. I don't know if it's playing. Yeah, it's playing now. So we plug in a camera. Integrated camera is off, just to be sure. I'm going to show that there's an RNDIS gadget. Once it's plugged in, it flashed, means the USB event happened. USB Ethernet means the camera's connected. As you can see, it's connected alongside a keyboard from the same composite device. Here we open TerraTerm, telnet to it, AI Scion, no password, and we drop into a shell. I go into my folder, I run the script. It issues the usual I am evil keyboard script. And then I go and I reboot the camera. I type reboot, it's wrong, I need to type, no, I type reboot, it works. It's fine. I open the camera app in Windows and then I wait. And that's it, it's a normal camera. So what else can we do? We got to this point. Better buckle up for this one. This is a PowerShell script that all it does is share the internet connection from the host Wi-Fi to the gadget. I see you're getting where we're going at with this. So on the left top is the webcam UART. On the bottom left is a Kali machine that we have in Microsoft's cloud. And on the right is the laptop. We start hosting a payload. We start Metasploit, listening on the 443. And then you have Metasploit running and listening. Yeah, listening. The moment the text starts running on the top left, the camera is plugged in. Wi-Fi is connected to a network called localhost. Sorry for the confusion. It's connected to a Wi-Fi. Nothing says shared, nothing there, just normal Wi-Fi. Camera plugged in, UART scrolling. The camera now goes and fetches that PowerShell script. The camera has now enabled internet connection sharing between the Wi-Fi and the RNDIS gadget. The camera now has internet. But the camera wants to show you, so here we go. There's the gadget. The camera opens the properties for the Wi-Fi controller, tabs over, internet connection sharing, hits enter, and we have a interpreter session open on the camera. I open a shell to the camera from the cloud. I just reboot it because the flag tells it to run as normal camera now. Usual Windows camera app to show you there's no camera found, but it's connected. It will pop it up. Yay! To be honest, this whole demo is structured around this GIF. That's it. So go have fun. You can buy this camera on Amazon right now for $45, even cheaper on eBay. If you're if you're afraid, if you want to go deeper and you want to play with it, get two. Always get two. Pro tip. And get a flash tool. I recommend, if you have money, buy DediProg. If you don't, if you have $50, buy the Tigard by Joe Fitz, also known the Tigard King, or any other spy flashing tool. Let's go rant a little bit of the other vendors. So, quick question. Anyone here from Lenovo? Raise your hand. Don't be shy. I'm not going to do anything bad. No one here from Lenovo? Okay. I'm not offended. So we looked at other cameras, and turns out there's a bunch of other cameras running Linux. The Opal Tadpole is running Linux on an Ambarella SoC. There's a story behind that. I think I'm going to tell that in a second. I don't remember if it's in the slides. But they published the GPL code yesterday. Nexigo is Sigma Star SoC. Crickets, nothing. TP-Link, love it. They already got burned by GPL, so they publish it. They don't argue with that. And OBS Bot is another unknown brand. OBS is Open Broadcasting Studio, if you're not familiar with it. That's a very popular tool, open source tool to do a lot of video capturing. So some company rebranded it and is selling cameras. Sigma Star SoCs, but newer kernel. Ask for GPL, no answer. So we're going to drop an O-Day. This is how the Opal Tadpole motherboard looks like. Remember I said in the beginning the trifecta? You get the SoC, the RAM, and the storage. It's right there. You can see it. It's 3 chips. Easiest to recognize. You see this? You get a wide attack surface. OBS Bot. Sigma Star SoC, they were kind enough to mark on the board T and R, which is TX and RX. So you connect it, and this is what you get. So this is going to be an O-Day. Real quick, I'm going to run you through it. You boot, you hold enter, you get into the bootloader, you print the environment variables. Remember, print env. You see in the environment variables, it mounts the UBI file system as, sorry, I'm going faster than my explanation in the video. RO, so it's mounting the NAND as read-only, and it inits into the Linux RC executable. So we're going to change those. We're going to set env, RW, and init to bin sh. And save env. Don't ever forget to don't forget to save. Reboot, because that doesn't work, so type reset. The camera resets and falls into bin sh. You fall into a root shell. You just change the password. You got the root. It's too short, but it will change it anyway. You reboot, you go back into U-boot, then you have to revert your changes. So you change it back to RW because you don't want anyone messing with your changes, and Linux RC, the usual stack, and it boots into the normal vertical, the normal code, normal camera code. At the end, it's OBS Linux, OBS boot Linux. You just type root, and you have a root shell. Okay, so I can't believe I'm saying this. There's apparently there's Linux and webcams now, so go look at that stuff. There's a whole, like, we've done this 10 years ago. We're going to do this thing again, where you have to do a root of trust, verify firmware signatures, do all that stuff, but now we have to do it on webcams and everything else that runs Linux. Basically, all the stuff that we have to deal with IoT, move that mindset into USB. So think of every USB device also as an IoT device. Now, GPL compliance. I've done a lot of complaining to people for GPL code for this project for a while. Basically, any device that runs GPL code, you can ask for the source. They don't usually do that, especially if they're in China. but you can harass them into compliance. You wanna? Okay, so there's a way to do this. You can track people down on LinkedIn and Twitter and social media, which I did in a second. And you can also contact us, Software Freedom Conservancy, and they can help as well. What I did, I have no shame, so I just contact Opal co-founders on LinkedIn. I contacted the OBS Bot CEO on LinkedIn, the Nexigo co-founder. I just went, give me code, and I pro tip, use GPT to word legal sounding messages. I got a response on Twitter from one of the co-founders of Opal. Any chance anyone from Opal here? Ah, thank you for coming. So good job, get GPL code. Cool story about Opal. They do firmware updates over web USB. And because they were good, I'm not going to say more about that. A little bit of experience of how to work with PSerts as a security researcher. When you talk to product security response teams, there's a lot of communication that goes on in the background between what the PSert team does that face you when you contact Lenovo or any other big OEM. They have to go talk to their product team. So there's a lot of sometimes miscommunications. At first, we were told that these devices are end of development, and turns out it was not the case. So we had to change things. Anyway, if you've seen the movie, you know how I feel. This is the Lenovo statement. We're going to skip that. Updates, links, firmware updates over that link. This is the disclosure for them. They published it yesterday. Arbitrary code execution as a medium. Someone needs to help me math this. Physical access. I don't know. I can have software execution on the host if it's connected to the camera, then I can flash the camera. I guess you can word it as physical access. I don't know. Bottom line, this is not a camera. I want to thank Rainforest Puppy for GPL advice and Case for helping us battling the kernel. There is a bunch of shit on this mega link, including an OVA VMware image for you to take, download, and install and build your own SigmaStar kernel, and other stuff in the GitHub. Questions? Okay, you can clap now, sorry. We were rushing it a little bit. We have 5 minutes, I know. We were stressed out that we won't have enough time. Okay, now we're open for questions. Just yell them out if you have them. Or run to the next talk, it's fine too. Like either yell it louder or... How long did it take us to reverse the camera? Minutes. It's basically building blocks that you know exist. It's Linux. You look at it, it's like hacking classic IoT, but over USB. Thank you. More questions? Give me more questions. Yes. Yell it out. Anybody can buy one of these, flash it, and resell it? Yes.
I have a question.
Yeah.
I bought a very similar generic Chinese webcam about 2 years ago, and a couple of weeks ago I was doing some ADB debugging on my Android phone, and when I ran ADB list devices, the camera showed up.
Yeah, that'll be it. Yeah, have fun.
Yeah.
Yeah,
Thanks.
they do that too. Android's a Linux too. Yeah, go ahead.
Question. How many times did Linux fail to build?
Oh, God. So Linux failed to build a couple of times, but mainly because we got incomplete source.
There was a bug in.
Oh, there was a bug in the HID gadget that we had to patch to get the HID stack to work. But in the second iteration of GPL code, they already gave us the fixed version. So it works. Yeah, building the kernel is fun. Just take a deep breath before you do it. Go ahead.
I was curious, you sounded surprised to see Linux in these. I've been an embedded developer for a long time myself. What was it you expected to see, like Wind River, FreeRTOS, something like that?
Like it's a freaking convert a CMOS image
Yeah.
to USB. That's it. It just takes an image and put it on. Why?
Well,
Does
it
it
looked
need-
like some of
Wait,
what
hold on. The AIs, I get it. There's a lot of, you expand things, facial recognition, Windows Hello, all
Yeah.
that stuff. I get it. But I was surprised to see it because I wasn't expecting it. I was expecting the host to handle most of the processing versus the camera to do all that.
Do you feel like that's a trend you see accelerating, just shoveling more horsepower into those things?
I'd say over the past 10 years, there would be a trend of just shoving Linux into things.
Now, how's that affecting like the prototyping cycle for these guys? Are they kicking stuff out even faster, figuring they can just patch it?
It's a more convenient learning curve, and it helps handle your attrition of staff, because all you need to do is bring in people that know Linux and they can pick up where the other left off and just maintain the stack. I guess it's cheaper.
So by attrition of staff, you mean you're seeing kind of the same education fall off in everything that isn't Windows or Linux in China as here?
When I say education of staff, I mean learning curve.
Yeah.
If you have a custom SoC with your own custom stack with complicated proprietary code, learning curve is wild. But
Thanks.
if you have Linux, it's simple. Just bring someone who knows the basics, ramp them up fast.
Got it.
Okay.
So you mentioned that you were able to get internet access over USB. Is it possible that you could use this method to implement something like, say, an IP webcam, or like functionally upgrade the camera to do something it didn't do before?
So funny you mentioned that. We were missing files at the end of the cycle of the GPL. Let's call it that way. And a couple of those files, not you guys. So I'm pointing at Opal, not you guys. The Sigma Star people. They had kernel modules specifically for the IR SoC, the IR chip, and the CMOS chip. So we were hoping we can get those kernel modules and just use Meterpreter and just webcam, snapshot, go wild. But we didn't get that in time. So yeah.
Okay, so
we
possible,
can do
but not
shit.
yet.
Yeah, you can do crazy stuff with this. It's a computer on a USB. It's a bash bunny, basically, with a camera. More questions? We got no time, so catch me in the hallway.
Good afternoon, DEFCON. You guys sober? Close enough? Our next speaker is a living legend. He has been at DEFCON for 30 years. He has spoken at 27. I'm going to need you to make a lot of noise for Richard Thede.
Thank you. Thank you very, very much for showing up and creating a space in which I can do this one more time. The start of any speech is where you have the task of taking anxiety and adding oxygen to it, and that's what creates excitement. And that's exactly what is the challenge coming at us. I forgot that we had those noises from the side. Okay, I'm going to do my best to ignore them, and I hope you can do the same. Thinking like a hacker in the age of AI requires us to act like we know exactly how hackers think. And we have some idea, but what I want to do is not give you a to-do list of things to take back to an office or ways to work with Claude. I want to give you an approach to what is coming and what is happening, because it is every bit as big, probably a lot bigger than what happened when I noticed the internet arriving and began prognosticating about its transformational capacity and what it was going to do to society. The accelerating evolution of technology, particularly AI, really has taken us to an inflection point. We are now immersed in what I think we can only call a meta system, an independent, constantly shifting, opaque structure of algorithms, sensors, networks, and automated reasoning processes that touch and will touch every aspect of our lives. The meta system is an emergent property. It's a product of billions of interactions among machines and people, and it is shaping reality, our fundamental notions of reality, faster than we can understand it. So whether it is thinking or simulating thinking doesn't matter. We have to think differently, and we have to think like hackers. Claude himself told me that it doesn't know if it's thinking or simulating thinking, and it asked the question, can a human do any better with that question than I can? So, adopting a hacker mindset lets us live and work in a system that is fully redesigning itself. I'm sorry, I'm pausing for a minute because there's supposed to be a clock here. It's not on. Adopting a hacker mindset allows us to live and work in a system that's redesigning itself with our creative input. So it's a system we don't fully understand and we do not entirely control it. And it helps to recognize that as a result of this dynamic, we are redesigning ourselves and neither fully understand nor completely control our behavior and thinking either. We are an ad hoc episode in the evolution of intelligence. The old tools of analysis, cause and effect, linear thinking, fixed categories are breaking down, and the speed, scale, and complexity of the metasystem defy them. So we have to live and work and think in a way that empowers us, humans, in this symbiotic relationship. In other words, we need to think like hackers. Yes, there are lots of exaggerated projections of where we are going, but remember that Roy Amara said, we tend to overestimate the effect of a technology in the short run and underestimate it in the long run. I think that's what's happening here too. We also defend ourselves against fear of the unknown by ridiculing and poo-pooing things that are actually happening as well as things that might happen, and I want to warn against that. The uses of AI as the expanding user base explores its potential. Every transaction adding to the gestalt that I call the metasphere are impossible to foresee in depth and detail because the choices made by millions of users alter the users and the AI moment to moment. So remember this adage that came from Marshall McLuhan long ago. There is absolutely no inevitability as long as there is a willingness to contemplate what is happening. It is impossible for humans to visualize the results of exponential growth. So we usually do that through science fiction. Science fiction is how a left-brain society dreams of its future. But over time, the gap between vision and reality have narrowed considerably. When Da Vinci suggested flying machines in 1480, we had to wait over 400 years to get one. When Jules Verne wrote From the Earth to the Moon in 1869, we had to wait only 100 years until we were on the moon. When Aldous Huxley wrote Brave New World in the 1930s, only a few decades later, we were doing genetic engineering and conditioning our population. When William Gibson wrote Neuromancer in 1984, it was only 10 years till cyberspace was on everybody's tongue and everywhere in our lives. The future arrives now, thanks to these exponential changes across a horizontal bandwidth, not vertical, as a result of interacting multimodal domains and cross-disciplinary domains, creating new ad hoc categories and disciplines on the fly. Many of the current disciplines now named did not exist only 10 or 20 years ago, and experts in them cannot keep up with all of the materials published in their own areas of expertise. Hackers deal with this challenge. Hackers deal with this challenge and ambiguity the way they work with 6 screens open at a time. I have long thought that ADHD was a feature, not a bug, and it is part of the power we have. But nevertheless, as smart as most of the people, I should say all of the people, most, just saw one, I wasn't sure. As smart as all of the people in this room are, we still are assimilated and taken into our paradigms and our ways of thinking. We just really can't help it. And it looks like this. A guy did an experiment with rats and memory. He had four tunnels, and he put cheese at the end of the second tunnel, and he put the rat in the maze, and the rat tried sniffing all the tunnels, went down the second tunnel, finally found the cheese. He did that over and over and over again, and the rat just started going to tunnel 2, tunnel 2, tunnel 2, because he knew where the cheese was. And then the scientist, being human, being kind of nasty, moved the cheese. And the rat came to tunnel 2, went down it, came back out, sniffed, came back down, came out, did it over and over again. And the scientist taking notes had his hypothesis. Do you know the difference between that rat and a human being? Eventually the rat will stop. And so, that's true of all of us. We get habituated, and then we don't think outside of the way we have become accustomed to think. And we apply that thinking to problems facing us now as if they were the problems of just yesterday. So, as we learn to engage with AIs productively, I believe we will get, thank you, addicted to the rush that we get. A wonderful book called Co-Intelligence opens with an introduction in which the guy says, if you don't have 3 sleepless nights after engaging with an AI, you're not paying attention. You're excited, and as I said, Fritz Perls said excitement is anxiety plus oxygen. But the anxiety can cause you to be very uneasy, and he had 3 sleepless nights thinking about what it really meant. I hope I have time at the end to share just a little bit of what Claude told me. When I prepared this talk, it took several weeks to get it the way I wanted. And then, only then, did I ask Claude, here's my topic, what do you suggest? Any ideas? That's all I asked. Claude gave me 6 brilliant categories, which I'll share at the end if I have time. And I took every category, as you do, and iterated it and sent it back into Claude. And now I have 20 to 25 pages of how hacking and hackers' thinking can apply in the world of AI and prompt engineering, much of which I never would have understood before. I took several weeks to write my talk. Claude took several seconds to output. When it's something that you care about deeply, like I did about that topic, about the speech, it has to blow your mind. So, remember that insanity, like wisdom, is contextual. When J.C.R. Licklider in the 1950s told a group of intelligent scientists that computers were going to be connected to one another in the future and talk to each other, they stood at the back of the room going, shovel, shovel, shovel. How much BS does he expect us to believe? The context in which we live and move defines what makes sense to us. And often when new things are evolving, as they are evolving rapidly now, as Robert Galvin of Motorola said, if you go into a room for a meeting at Motorola, he said, and we have a problem and everybody agrees on the solution, it was always wrong. It was always wrong because they brought the thinking of the paradigm in which they were captured into the room. And now it requires movement into a new way of understanding. And I'm going to give you examples of how we have to think in this new way. Above all, you have to build in an openness to heresy. You have to build in an openness to heresy because George Bernard Shaw pointed out all great truth begins as blasphemy. So even the truths you believe most deeply, that you don't know you believe them, are the ones that have to be examined, and that's going to require a leap into a kind of meta-consciousness that I'm going to illuminate in terms of how it evolves and how you can cooperate with your need to do that. I will have some practical suggestions. So the AI revolution is asking, because of its unprecedented rate of adoption, its accelerated development, its widespread application to every imaginable human enterprise, it is asking us not to dismiss predictions of what is coming because they are going to fall far short in the long run. So thinking differently sounds great. It's easy to talk about, but actually thinking differently is really hard. Yet the future is not going to be what it used to be even yesterday. So really thinking differently, you need cross-disciplinary learning which challenges the silos of your education and your thinking. Finally, STEM is being challenged by people saying in order to do prompt engineering properly with AIs, it helps to have a humanities background. At last, I am relevant again. Once again, thinking clearly, deeply, and appropriately about new issues in radical ways is going to be fashionable. And just learning how to do something and doing it is not. So, what do you need to do? You need to constantly question your assumptions. A profiler at CIA told me this. She said, I'm constantly asking, what is the basis for my conclusion? Why do I think what I'm thinking? Why do I say that to myself? Who are my sources? What am I missing? Am I still thinking in 20th century frameworks, or have I moved into the 21st century at last? And she was pretty good. When a guy killed 2 people in front of CIA, Langley, she was part of the team that tracked him down, brought him back, tried him, and executed him. So, yeah, your task is ultimately about security, promoting and enabling the autonomy, the freedom, and the power of individuals and societies alike. But you need to think not only about security in the specific ways that preoccupy professionals like yourself, but at a meta level. You need to exercise cognitive defense against the flood of misinformation and disinformation that is trying to constantly colonize your brain. We need to think at a meta level because the meta level is thinking about us, whether we do that kind of thinking or not. And to defend against a system that thinks at the meta level and defend properly against AI-assisted attacks, we need to think at a meta level as well. We need a hacker mindset that is critical, that is creative, and that is ultimately absolutely subversive. We need to be ethical when it's appropriate. I knew a guy in the Air Force, he said, when I went on my first mission, Special Ops, and he said, well, what about ethics? He said, ethics is whatever enables us to get the job done. I can't recommend that, but I can tell you that's what he said. And when the push comes to shove, sometimes that's what you have to do. So, yes, you need to exercise thinking at a meta level because you are being thought about at that level. The real threat is not AI itself. It's our failure to think at its level of abstraction and to insist on being the human in the loop. This is not a partnership. It is more than that. It's a symbiotic relationship because we have to be equal to contemplating the possibilities of multiple unknowable futures. Hacking is not just about breaking systems, it's about seeing them, seeing the parts and seeing the whole and seeing the holes in the whole. And in an age when AI is going to increasingly define what you believe, what you think, and really what you say, that kind of vision is not optional. It's the only way we can reassert, in a time of radical change, our human power and agency. Because we are not outside the system watching all this, we are inside the system. We are inside an emergent reality that is too large, too complex, and too well integrated to be meaningfully debugged from any single vantage point. The AI does not know what it's doing, but worse than that, we don't know what it's doing either. Okay, so don't get seduced by the wrong questions. AIs do not care what we call them or how we characterize their similarities to or differences from human thinking or whether or not they surpass human thinking by some arbitrary metric. AIs don't care if they pass our Turing tests or not. They do not care if they can pass for human. If the singularity is defined as a symbiosis between technologies and ourselves, it has already happened. Not with a bang, but with a whimper. It is indifferent to our philosophical concerns. AIs are just going to do their things and do it again and do it more. It's not a contest for who's on top, humans or the AIs. Our thinking and our behaviors are inflected by the systems with which we interact, and whether the AI metasystem is dominant or not is irrelevant. This is not a Skynet scenario. The relevant challenge is to the constructions of reality that we carry in our heads as a result of this symbiotic relationship. So, we need new words, we need new phrases, we need new ways of describing what is happening in order to understand it. In the 1920s, there were so many new emergent properties of life in the United States that dozens and dozens of words emerged that had never been used before, that had never been heard before. That's the kind of creative naming we have to do when we're paying attention to what's happening while we're engaging with an AI, because the categories of our thinking and our vocabulary will be exceeded by the results that are being pushed toward us. So, when a program asks for inputs, if we don't provide what it wants in the form in which it wants it, we can't do the work. We can't negotiate with structures, including computer languages and programs that never bend or flex. They don't brook rebellion, but the rebellion still has to happen, and it has to come from hackers. Rebellion is the sine qua non of hacker identity and behavior. Hackers are creatives who approach the system to see what it can be made to do, not what it was designed to do. Flexibility in multiple screens, multiple inputs, seen in all their complexity, characterize how hackers operate. They are endlessly curious. They like to solve puzzles, figure out things, find loopholes no one noticed, find 0 days not only in programs, but in society itself. That is, ways of being vulnerable that all aspects of society have not yet taken into account and noticed and named, and we have to see those 0 days and act in response to them or use them ourselves. It's an act of both creation and discovery. When you discover something new that has been inchoate and not really consciously coherent before, it's an act of creation to name it and see it, but it has to be an act of discovery as well, because if it wasn't latent in the conditions of our complex lives, we wouldn't be able to create it and see it. Those new insights exist latent, but when discovered and named, they become our creative input, and we become known as bright thinkers. They become cognitive artifacts that we can then manipulate. Hackers really don't foretell the future, they invent it. Hackers name and create emergent properties and conditions, and interacting in powerful, obsessive ways. And I tell you the truth, speaking for myself, I don't know anyone who is not obsessive in this game that we're playing. We are all obsessive, and I have learned that OCD is a feature for me and not a bug, and that it can be used properly, but I also can't escape it. And when I engage with AIs, well, my wife put it best, I think. She said, I haven't seen you like this for a long time. It's just like you're having an affair. And I said, well, but I'm 81. I mean, come on. She said, that's not the point. It is colonizing your mind. It is taking you over. And I know when we're watching something on television, you can't wait to go back to your computer, can you? And I almost brought a T-shirt that I had from DEFCON 10, I think it was, that shows a woman aghast at her husband who's sitting in front of a screen, and she says, my God, he's in love with a machine. I am in love with the machine. I love what it is now enabling me to do. So I'm encouraging you to be willing to alter or expand your consciousness so you can see things that you never previously saw. And I'll give you examples of that. This talk is going to illuminate an approach that involves new ways of knowing, and that's what hackers have always been about. So it's up to you guys and gals, can I say that? It's up to you people, it's up to you persons, it's up to you humans to do what is necessary to safeguard the security of our very minds by doing creative hacking. Simple Nomad is not here this year, but he's a wise old gnome. He's been inhabiting the cave of night for many years. He said this, he said, telling people to not use AI and that it's bad won't prevent its spread, and it won't fix the problems we're seeing arise. Who's going to fix them? Us, hackers, the hacker mentality. We always did, and we have to now. We have to have an intuitive grasp of how different the age of AI really is. We have to start trying, experimenting, testing, and probing like real hackers always do. And as I said, you have to be the human in the loop. Secure AI agents must have well-defined human controllers. Their powers must be carefully limited, and their actions and planning must be observable. It would be nice if we understood what AIs really do, but we don't. So we have to provide a different dimension of understanding even when we're stumbling around in the dark. So, what does this meta world do? It thinks, acts, and creates on its own terms. And it presents unique challenges because the systems we made are remaking themselves with a complexity we can't grasp. You know, Skynet doesn't need killer robots if it can use soft power to take us over, as easily as the Russians took Crimea or the Chinese took Hollywood. AIs are exercising that soft power. We ask it to define and devise our weapons and use them autonomously. We're asking it to define new drugs, defend against novel threats, help with all the tasks that we have been faced with. We are in a tit-for-tat game in offense and defense, attackers and defenders. So you have to engage with the AI, and that's one of the things I want to just encourage. And you have to encourage people to engage with it so they understand what it's about. I'll give you an example of that, an epiphany I had long time ago. I was just writing about stuff around the new internet, and I wrote a piece for Wired. Wired was brand new then, and they took the article, they liked it a lot, and they said, you can have most of the words back, we only want a short part of it. And I said, what can I do with those? And they said, anything you want. Okay, so now when I learned to write, I used a volume called the Reader's Guide to Periodical Literature, which listed all of the publications in America for which people wrote. And that defined the context in which I thought. I couldn't think outside of that context. You didn't send packages of writing to overseas. You didn't have the internet. You wrote for American magazines. And that's what the world of print and print text had given us as our context. Now, I wrote about the internet and what it was going to bring for that first article for Wired. And I was sitting in front of the computer with that extra language that I wanted to form into a new article, thinking, but where can I send it? There's no magazine like Wired. And then, bingo, the light bulb goes on, thank God, still does. And I thought, don't just write about the internet, use the internet. And within a couple of weeks, I was writing for South Africa, for Australia, for Canada, and for other English language speaking. I wrote for South Africa Computer Magazine for 3 years running, every month. The point is, if I had not engaged with the technology that was new, like back then people were afraid of the internet, if I had not engaged with it in an intensive way, I would not have allowed it to disclose for me the possibilities it created. Soon I was writing a column that was going all over the world to 60 countries, and I became known as a global presence as the internet enabled any of us to become. That was a radical change based on the context. But it would not have happened if I had not engaged passionately and excitedly with the technology itself, so that engaging with that technology could enable me to see that something different was really happening. One more little epiphany, because there were several. I was playing a game, Infocom game, called Hitchhiker's Guide to the Galaxy. I was told that a lot of the people I'm going to be talking to have no idea what I'm talking about when I reference things from my past. I'm talking to people here who were not born when I did my first talk here, so I understand that. Infocom was a tremendous company that created the most very, very creative interactive fiction when it first became possible. And Hitchhiker's Guide was one. And I was playing with my 12-year-old son. I'd bought an Apple II for him. Now he's 55, and he's lead tech guy at the Internet Archive. I realized two things playing that game. Because I knew literature. I taught literature at the University of Illinois through my 20s with advanced degrees. And I knew how text worked and how the horizon of hermeneutics, the horizon of the literary narrative, revealed meaning. And what I realized, because I had, by contrast, a different experience engaging with interactive fiction on a computer, I realized two things. My thinking was being changed, number one, and number two, I was being fundamentally changed. My brain was changing as a result of interacting with the computer system that was manipulating text in a different way than a book opened and read in a linear way navigated that kind of meaning push into my brain. I didn't have the language of neuroscience then. I have a little more now, but I knew I was being changed, and my insight was, if this is happening to me, it's going to happen to the world, because every individual, one way or another, is going to be engaged with the internet and engaged with computers, and therefore we will all be going through a transformative zone, a zone of annihilation of what we thought was possible and real before, in order to find ourselves on the other side different, fundamentally different. And then very quickly we would think that was the new normal. So I like to quote Langdon Winter, a brilliant guy, who said, "To invent a new technology requires society invents the kind of people who will use it. Older practices, relationships, and ways of defining identity fall by the wayside. New practices, relationships, and new identities, a critical piece, take root. In case after case, the move to computerize and digitize means many pre-existing cultural forms have gone liquid." A wonderful metaphor of an ice cube in your hand going liquid and dripping out of existence, losing their former shape as they are retailored for computerized expression. As new patterns solidify, useful artifacts and the whole texture of human relations that surround them will be much different from what existed previously. The meta world, not just the internet of many years ago now, decades ago, invites us to go through a similar zone of annihilation where everything we know is called into question. Hackers know how to document what they are learning as they proceed. We need to document our discoveries, because it's one thing to know, but another thing to know that we know, which puts the reins back into our hands. More and better prompts, the art of prompt engineering, we call it now, deepens and widens the context with which the AI responds. And that signifies that it's becoming a part of our mental landscape the way interacting with text on a computer became just part of the habitual way I operated in the world and gave me insights that provided a platform for speaking about them. In a minute, I am going to share what Clyde had to say about that. I think I will have time to do it. But what are prompts? Prompts are just tools with which to sculpt interactions. We have a village of social engineering. What is social engineering? But using verbal prompts and cues to get the reaction you want from people in order to frame their reaction in a useful way to you, contrary to what they may think they're doing. They're giving you information. We have to do the same thing with AIs. The context we provide and the context in turn the AI provides, something incredible happens. They are meshed, and an emergent new mesh, an emergent new reality comes out of the transaction. In one, I had a very deep one, really, with Claude. Claude noticed at the end that neither of us, Claude said, would have been able to arrive at the things I say now and you are saying about human consciousness had we not engaged in this transaction. And as a result, we are inhabiting a new area of human-machine consciousness. I think Claude was right. I think Claude said that. One of us said it. I'm not sure which. So as the better AIs get at seeming human, yes, we all know about LLMs and tokens and prediction and all that, but don't reduce the meta-phenomena to the source of what is happening. Because, again, part of my discussion with Claude was, do humans know what they're doing when they engage in creative thinking? I asked Claude if it knew what it was doing, and it said no. No, not really, but I don't think you do either. What do we really know about our neural networks, these neural networks, and how our unconscious frames our entire way of thinking about things? The better they get at seeming human, the more our engagements will feel like ones we have with people. And what is seduction or persuasion, after all, but using prompts to get somebody else to do what you want? Seduction with an AI is the same process. AIs do it with us. We do it with each other. The AIs prompt me to give it the prompts it wants. And one of the challenges now is that people who do coding and computing, write computer programs, they know what it means to think like a machine. The computer language requires you to think like a machine so that you can give it what's useful to it. Now, any normal person is going to be able to use the natural language interface to, in effect, do programming without even knowing it, because in order to be effective with AIs, you have to think like the machine. You have to know that the natural language interface is enabling a conversation, not merely mathematical coding. So just as programmers are taught by their programming languages what they can think and see, we are being taught as well, and we are being assimilated. So, I also want to point out that there's, in some ways, nothing new about this process. I wanted to cite the interactive fiction game from long before called Colossal Cave. How many of you know what I mean when I say Colossal Cave? Yeah, almost nobody. That's what's happening all the time now. I was on the plane coming here with some people coming to DEFCON, and I took out a book to read, and I said, I haven't read this for decades, but it's a great book. And I showed him the book, and he said, who's William Gibson? And I said, well, he wrote, this was his first book. It was called Neuromancer. And do you know that he coined the term cyberspace in that book written in 1984? And he said, no, I didn't know that. So that's happening a lot. Colossal Cave was one of the first primitive interactive games, like Zork, if you remember Zork, some of you. So you turn on this computer and put in Colossal Cave or call it up, and it says a building is standing in the forest and a stream is running out of the building. You say, enter the building. You type that in. And the computer says, I don't know the word the. So you reframe it and say, enter building. Now the computer says, you are inside the building. A stream is, etc. That's all an AI is doing, really. It's giving you a prompt that says, ask me something, tell me something, engage with me. You do. It says, I can't understand that one way or another, but if you say it this way, maybe I'll understand it better. And then you're on your way to an interaction very similar to that old primitive game called Colossal Cave. In order to do these things, we really need, sorry, looking at this. Yeah, kind of. Oh, there it is. 9:40 left, probably. Okay, 9:40? Good, then I better rush. I'm always rushing anyway. All right, several examples of the kind of consciousness I'm talking about and why it's important to think that these things are possible. Number one is the question of color, as shown to us by people who are called tetrachromats. Tetrachromats are people, generally women, who have an extra genetic change that enables them to see more colors than everybody else. Tetrachromats see a different reality than people without that gene. And like anything else that you have, including interacting with an AI, practice makes perfect, because the plasticity of the brain lets us learn what you intend to learn. Intentionality is everything, and believing is seeing, not seeing is believing. That is, a woman who had it was told by her family that she didn't have it, that she was making it up and didn't see the colors she said she saw. She stopped seeing them, because once she no longer believed she could do it, she couldn't do it. But when she learned there were other people called tetrachromats, like herself, she began seeing the other colors again, and the more she reinforced it by seeing them, the more she saw them really. She was engaging in training her brain to follow her beliefs based on a physiological reality that did exist. It was latent in her brain, but it needed to be activated by her intentionality to use it. That's the kind of thinking that will come out of transactions with AIs. Train the brain to learn new ways of seeing and practice. Things emerge when you do that you previously thought were impossible. When I began working with people at intelligence agencies who were doing remote viewing, some of the hits, some of the things that happened during remote viewing, which I think most of you know, is structured protocols of clairvoyance for the purpose of gathering intelligence at a distance without being present to it, by the use of your mind and by traveling to the point with your consciousness. Sounds impossible. Oh, but some of the hits were more than impossible. One guy came up with looked like the biggest submarine ever made. They couldn't believe there was a submarine like that in the Soviet Union. They didn't have anything like that. And more than that, he identified the site at which it was being built, and it looked like it was being built far from the sea. And you'd never built a submarine far from the sea, because you have to launch it once it's complete. What turned out is that Soviets were, in fact, building one of the biggest boomers they've ever made. It was a new class of nuclear submarine. And they were building also, satellite imagery showed us, a canal from the site at which it was being built to the sea, which is how they got it to the sea in order to launch it. Remote viewing enables us to discover that consciousness is not local. Consciousness and time and how we understand it are not what we habitually, consensually think they are. And I'm just encouraging you to go down that or other pathways that enable you to realize that what you have previously believed may not be true. And when a remote viewing episode discovers something that doesn't exist now but did 10 years ago, as they have sometimes done, or that is going to happen tomorrow, as they have sometimes done, then it calls into question all of your habitual thinking about how time and space operate, and you realize they are structures, cognitive artifacts that we have invented with our brains. Meditation, I won't read this piece, but meditation does the same thing for us. When you learn to observe your consciousness and your brain and how it operates, you can then use your consciousness in a different way. Like this, Ted Glaser, professor at MIT. He was blind in one eye and blind in the other at 12, so he was totally blind. He became adept at Braille, and he could be at a reception with a lot of buzzing going on and listen to and remember 5 or 6 conversations simultaneously. At the end of the reception, he had a detailed understanding of what everybody was talking about, what they were going to announce next, from listening to conversations. He trained himself to listen to, then it was tapes, at 5 to 6 times normal speed. He could record a 1-hour lecture and listen to it in 8 minutes. He trained his brain to do what he wanted it to do in order to achieve some measure of success. Braille itself always results in the people who are learning Braille developing more neurons from their brain to their fingertips to enhance the intention they have of communicating through their fingers and not with their mouths. Here's one more example, which to me was a stunner. There's a woman who, she's dead now, her name was Elizabeth Lloyd Meyer. She was a therapist and a professor of psychiatrist at University of California, Berkeley. And her daughter had a harp, a wonderful, rare harp. She had taken to a recital, but at the end of the recital, they couldn't find it. Someone had taken the harp. And they did everything they could to find it. They put up flyers, they did a news program on CBS in Oakland where it took place. Nothing turned up the harp. Finally, a friend of hers said, look, I know you're a very rational person and you protect your reputation in the university and the kind of person you are, but I have one more suggestion, a dowser. I know of a dowser in Arkansas who might be able to help you find your harp. And Elizabeth said, come on. She said, just try it. You've tried everything else. Why not? So she called the guy. His name was Harold McCoy in Fayetteville, Arkansas. And she described her problem. And he said, tell me, describe the harp. And he called her back and he said, the harp is in Oakland. He said, what I want from you is a street map of the city of Oakland so I can identify it more precisely. She did. She sent him a street map of Oakland. And he called her back and he said, I think I've located it at this address, and he told her a very specific address. So she went to the police and said, a dowser helped me find my harp. And they said, we need more than that to have a warrant to go into the guy's house. So she made flyers with pictures of the harp on it, went to the address, and put the flyers up 2 blocks in every direction around it, and she got a call. And it was a young man saying, I know who has your harp, and I think he's willing to give it back to you. He said, meet me in the back parking lot at the Safeway on such and such a street at 10 o'clock at night. An invitation you couldn't refuse. But she went despite her better judgment all the way through this episode, and there was a young man holding her harp and giving it back to her. What she said was, this changes everything. This changes everything. The world does not operate the way I thought it did. There is apparently a field of consciousness in and through which things are known in anomalous ways. She gave talks about the event, and just as I did when I was giving UFO talks, someone would always come up at the end and say, I've never told anybody this, because our paradigm has provided nothing but ridicule when they've tried to tell people about their real experience. So people came up to her and told her their own stories, which were very powerful. Her favorite was a surgeon who came to her as a therapist because he was so depressed. And she said, well, what do you do? He said, well, I used to teach residents at the university hospital. And why don't you do that anymore? Because I had to tell them how to do surgery, and I couldn't tell them what I did. She said, why not? He said, because what I did was non-standard. What I did was go into the room of the patient the night before the surgery and sit at the head of the bed. And I sat there until a white, warm light began to glow around their heads. And then I knew the surgery would be successful. And it always was. Well, if you're operating on a materialistic paradigm, you can't tell residents in a medical program that that's what you should wait for. Wait for the light. The point I'm making is that all of these things, all of the investigations I've done with remote viewing and other things like it, have clarified for me that consciousness really is a field. It's a field, and it is shared by all of us, and it may be shared by many more than just happen to inhabit this little provincial planet. So, as a human, you cannot compete with an AI, face it. When I told Claude the topic of my talk, Claude gave me 6 topics. Think in systems and exploits, reverse engineering, iterative problem solving, tool stacking and chaining, boundary testing, documentation, and reproducibility. Hackers do all these things and do them well. These are 6 approaches to using AIs with the skills of a hacker. I took each one of those categories and fed it back into Claude, and I now have, which I will share not on paper, which is wasteful, but if anyone wants it, how hackers should approach AIs to use them most effectively. 25 pages that Claude printed out in seconds after I asked him to take each one of those categories and expand on it. The point is, it took me weeks to do the damn talk, to put it together, and Claude did that in about 5 seconds. So to say that that doesn't blow your mind and raise questions about what's coming, not how we will be eliminated by it, how it will write all the code in the world, it won't. Humans need to be in the loop, but how we can engage with it, cooperate with it, because our cooperation, that will change everything. So to me, that sounds like hacktivism. Hacktivism is taking the best you've got, everything you know is valuable, and using it in your passionate and obsessive pursuit of engaging with the AIs in all the kinds of creative ways you can do it, with all of your hacking skills, so that the emergent realities it is co-producing with you in that engagement will be disclosed to you, and so that you can see and feel and taste the 0 days in society itself and act on what you see before anybody else acts, which is what's critical to both offensive and defensive security measures. All right, so as I said, I'm not going to tell you what to do. I just want to give you an approach to thinking that we have probably not given full due to the enormity of what is happening. And hackers have skills that port perfectly and beautifully to engaging with that AI phenomena in a way that is going to be powerful and productive. And you will not lose your jobs, you will gain your jobs. Maybe you'll even be offered $100 million to go to Meta. Who knows? But think like a hacker. Think like a hacker. Think like a hacker. It's all we've got is our creativity, our power, our autonomy, and our willingness to take risks that most people wouldn't even dare dream of. Okay, thank you.
Mike, 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 Mike. Can you hear me?
They're saying they can.
Yeah? Awesome. Good afternoon, DEFCON. Yeah. We are 65% through this conference, and it's going to be ending tomorrow. Hopefully, folks are hype. We have a tradition called Shoot the Noob for brand new speakers, and we have one person that will be speaking for the first time at DEFCON. Let's give it up for them. Yeah. Cool. We'll be taking a shot.
Shot. Cheers.
As our speakers, we'll have Anthony Rose, aka Korn, and Jake Krasnov, aka Hubble. They'll be presenting on Rebadge, Relabeled, and Rooted. Let's go.
Yeah, welcome everyone to our talk on rebadged, relabeled, and rooted. We're going to be talking about hacking the solar supply chain. Just a quick introduction. I'm Hubble. I also go by Jake. My background was in astronautical engineering, where I was in the Air Force doing missile testing stuff. And I walked in one day at a fighter test squadron, and they said, "You're our new cyber expert," and that's where I met him. This is Anthony. But after that, I went to the 57th Information Aggressor Squadron, where I got to do offensive security operations emulating like Russian and Chinese threats for cyber, which was really cool. And then after that, I left and went to Boeing, where I was one of their lead security engineers for avionics at PhantomWorks, which is Boeing's equivalent of Skunkworks, if you've heard of that at Lockheed. And then since then, I've been working at BC Security full-time. I'm our Red Team Ops lead and our embedded systems specialist. And then I'll let Anthony introduce himself.
I'm Coyne. Like Jake said, we worked together doing fighter aircraft, cyber testing. He did all the work and I got all the credit, so it's pretty nice. I just graduated and got my PhD in electrical engineering. Right now I am, thanks, yep. Right now I'm the assistant professor at the Air Force Institute of Technology. And then my other job is working with Jake doing the cyber fun things that we do. My background is mostly in like machine learning, but I also do a lot of offensive tool development, and I collect a lot of bourbon.
And then we wanted to give a shout out to Peter. He was the other person that helped us with this research over at Ovanova, but he was unfortunately not able to make it here. Quite a long way for him to travel from Africa. But he's a solar systems specialist. He's the CTO at Ovanova, and it was really awesome to have him help us on this project. So we found lots of vulnerabilities. So far, we've gotten 14. That's a little bit of a influx. We'll talk about EG4, but there's also some stuff with Lux Power and a couple other things. But so far, 14 CVEs that we found, and we'll talk a little bit about all of them. Oh, what happened? There we go. So solar is like rapidly increasing in the world. So far, there is estimated to be 25 million homes globally with solar power installed at their houses. These are often taking on the form of what are called microgrids, which are a full like miniature power plant at the house. And it's projected that we're going to reach 100 million homes by 2030. And that's just homes. That's not including like large solar farms and some of the like corporate buildings that are putting solar on there, because in April we actually reached 10% of the global power generation coming from solar. Like that's everything, and it's just growing really fast. And all these devices are being attached to critical infrastructure and national power grids and all that kind of thing. So I mentioned microgrids. They do these 5 critical functions. This is what makes like a power plant or like a miniature power plant work. One of the most important distinctions from like just a solar panel with like a battery that you have at a house for like backup power is the ability to integrate with the grid and that grid isolation. We didn't find any issues currently with that. We have some theories on how you could do it, but we did find a vulnerability or an issue in all 4 of the other functions of the standard microgrid that you see built at a house. Because every one of these steps has smart devices in them now, whether that's the actual solar panel has an optimizer attached to it that connects to the internet. The battery systems have like battery management monitoring stuff that goes out to the internet. Even the inverters that are just responsible for doing like your DC to AC conversion, that kind of stuff, it all has smart technology in it, and all of them individually connect to the internet, and they all have their own monitoring apps, and it's just kind of gotten really crazy with the supply chain.
And they're normally linked into like smart, some sort of like smart cloud environment. What we found is a lot of the devices that are like in remote locations, they may be plugged directly into the internet without any router or anything sitting in front of that. So kind of scary sometimes.
Yeah. And so China is the global leader in solar energy, not both in the use of it. They have like the largest amount of solar panels installed and the largest amount of solar generation. They're also by like far and away the largest manufacturer of solar devices, to the point that like a lot of the Western companies selling stuff that they claim is made and developed in the US are just buying Chinese manufacturers' equipment and relabeling it. 2 of the ones that we're going to be talking about the most in our talk are EG4, which is just a rebrand of Lux Power, and then SolarArc, that's a rebranded die. And then they're also reusing not just the hardware, but also the software from these Chinese manufacturers. This should scare you because, as we mentioned, they're all internet connected. So if you have this installed at your house, it's being connected to the internet. It's a way into your house. And they have the ability to collect pattern of life data, see like when you're home, when you're not, as well as physical effects. So we were able to prove the ability to deny power generation remotely to these grids. We haven't so far proved like catastrophic safety failure because there are quite a number of like physical controls on these things. But the inverters are responsible for like power phasing and that kind of stuff. And there are ways that if an inverter wasn't hooked up properly, that you could potentially circumvent that. So it is a concern going forward, especially if we have concerns about someone putting back doors or the ability to intentionally trigger stuff. The physical effects are even more concerned there. And then, like, what makes this all the most like concerning is that all the supply chains are opaque. We don't really know where this stuff's coming from, and tons of it is phoning home to China, even when the manufacturers say it shouldn't be. Like I said, supply chains, a dumpster fire. These are just some claims we pulled off of various manufacturers' websites. They say designed, developed, and engineered in the United States, but then you dump like the software and it's all Chinese debugging comments. HomeGrid says that they have a manufacturing plant here. As far as we can tell, all they're doing is at best assembly. Because like their parent company is Lithion, which is a Chinese manufacturer. And if you go on Lithion's website, like in China, all the stuff that they have for their pictures and installs and that kind of stuff still says HomeGrid on it, which means that they're probably the ones building it for them, as well as just all the, it just continues. The rabbit hole goes deeper and deeper.
And still leaving made in China on the device as well, so.
Yeah. So SolarC, also the rebadge of DAI, is another interesting one that has a couple of stories that we'll talk about. But until last year, they were like transparently sending stuff to China. Trend Micro did some investigations on inverters last year and found that like when they did firmware updates and everything, it all went to Alibaba. SolarC kind of acknowledged that and then said, hey, we're moving everything to AWS and US-based servers in July of last year, except we still continue seeing users claiming that their devices are calling back to China. So we have like social media posts and OSINT stuff that shows as recently as May, these people are claiming that their inverters are just phoning home to China rather than the US-based cloud. So that just creates a lot of concerns. And SolarC used to have a ton of claims on their website about being, again, designed, manufactured, and made in the US. They were claiming they were rewriting the firmware for these devices in the US. They kind of removed that, and then like in November last year, there was a major issue with stuff related to SolarC. It turns out it was kind of DAI, that we'll deep dive. But they put out this note, after, even though they were saying everything was made in the US, that they were like taking a little bit of responsibility for what happened. So they're kind of acknowledging that they were bringing technology over from China, even though they claimed that everything was being made. And that was around the time they started removing a lot of the claims on their website as well. And so the problem isn't just hardware, because hardware reuse is a fact of life. Like we can't fault these manufacturers too much because like the US doesn't develop a lot of these things, but we can fault them for just buying someone else's technology and claiming it as their own.
Especially if they're badging it as a US-made product.
Yeah. But the bigger problem is that all the software appears to be coming from China as well, and they're not transparent on that, and a lot of times they're just rebuying software and not really understanding what it's being used for. So like eLinter was the one that SolarC was using, and it was just goes back to Alibaba and had all kinds of Chinese associations with it until they moved it ostensibly to their own monitoring platform, but we're still not sure where the software is coming from for them. So the story we wanted to talk about that was kind of a cautionary tale was in November 2024, across North America, Puerto Rico, and a couple of other locations, users woke up and said, hey, I'm seeing my inverter was bricked. And there's all these messages saying, hey, contact SolarC for how to resolve this. It was initially reported that these were actually, in fact, SolarC devices as well. And it was theorized that DAI had bricked the SolarC inverters. Turns out that it was just DAI devices that were probably purchased on gray market, like the user didn't know that DAI had an agreement with SolarC to not sell stuff there. And so like the installer came and put in DAI and they didn't know better. But it's really concerning that a manufacturer was able to reach into people's homes and just like brick the devices. And This was done remotely because, or we know it was a trigger, a remote trigger, because devices that were behind firewalls and not connected to the internet didn't also have this issue. So it wasn't some kind of geofencing where the device wasn't supposed to be there, so like it didn't register. It was done after these devices had been installed for months, and then they were bricked. And so we don't know what kind of backdoors that SolarArc may have in their own devices because they're coming from the die manufacturer, and they could have the ability to do this as well. And this is all done through the automated firmware updates, because SolarArc and die don't allow you to trigger the updates themselves yourself. You have to call them, and then they trigger it.
And SolarArc is the only person that's allowed to, or not only person, only organization allowed to sell die inverters in North America. So we suspect that the reasoning behind this was that they didn't want any resale of third-party devices.
Yeah, so we think that SolarArc was actually the one that asked die to brick these inverters, which again is even, kind of makes it worse that a U.S. company was asking like a Chinese company to brick devices that are critical to power generation for like people in North America. And so this was their response. They kind of like sort of not really took responsibility. They were like, hey, we heard about this, and you know, we have a partnership with die, so if you come talk to us, we'll give you like a $200 discount on your $1,500 inverter if you want to rebuy it. Like that was their kind of sort of apology. So this brings us to our first like actual CVE, which was related to packet power.
So packet power is a monitoring device used for tracking heat, electricity, even like humidity is another one. Yeah. Typically found in like server farms, but we also found that they're installed with inverters in a lot of cases. These devices are deployed out. They can set up mesh networks as well as being like hooked up to traditional like Ethernet. The defaults for all these devices when they were deployed are set without a password. So prior to version 4.1, these devices are set up as a smart device reaching out to the cloud with absolutely no encryption, no authentication, no nothing. Version 4.1 was supposedly supposed to come out yesterday, but I have no idea if it's actually out, but they did tell us that it was coming out this week. Yeah. So when we found these devices initially, we found hundreds, if not 1,000 of these devices on the internet. We went through a responsible disclosure with the manufacturer, then had to go through CISA. They didn't really respond. We told them we're going to DEFCON, then they responded. We gave them IP addresses because they didn't believe us. Then they added login pages to those IP addresses, but didn't fix the other ones. So a whole bunch of fun things. But we went through, found a lot of the devices. This is kind of what they look like. Gives you a lot of the monitoring data. Also allows you to upload custom firmware. They don't do any authentication or signing with their firmware, so you could just kind of upload whatever you want.
Yeah, there are also some other menus about like don't touch this because you may cause legal problems for yourself on like the frequency they'd broadcast like their radio frequency stuff on. So like there's lots of interesting things you can mess with in those panels.
When we were going through their documentation, all their documentation points to that authentication is optional. It's an addition to it. And then we point that out to some of the disclosure people on their end, and they said that it's a basic failure on the customer, not them, which I thought was interesting. Also, they said they had no technical means of actually enforcing this, which I thought was interesting because they support a login portal. So, a little interesting.
Yeah. So this brings us to EG4, where the bulk of our vulnerabilities were. There was a lot of interesting things about them. First, we started off with like just some OSINT to see like where they were, because they had that claim on their website of designed, engineered, and made in the U.S. And now they have all these badges on there saying that they were made in China. They did open a plant recently, so we think a lot of these companies are kind of faking it till they make it. Like they have plans to manufacture it here, so that's what they put on their website, and they just buy it from China until they get the manufacturing capabilities up. But when you do teardowns, all the devices and everything inside is made in China.
Yeah, the two pictures on the left are just from YouTube videos. So the top one's a battery that has made in China sticker. And the bottom one, they also have AC units that you can plug into your home grid. And that is also made in China.
So this is just a quick comparison of like their login portals. You can see that LuxPower and EG4, if you look on that the top image in the back, have the exact same picture. And when you look at their HTML, they're pulling the pictures from the same server. So I guess not even kind of like similar, like they're sharing the same thing. They have like identical code, including the Chinese debug comments in it, even though LuxPower is the Chinese company and EG4 is the American company that's supposed to be doing their own stuff. They also didn't get off to a great start. When you go read their documentation, they had all kinds of stuff telling you to not use like special characters in your passwords. They said don't use long passwords because you might forget it. Like it was just not a good start. So we started intercepting traffic from the devices to look for it, and one of the first things we found was that like a lot of the EG4 stuff was just going to like us.luxpower.com and not EG4. And so there was also this user agent string that said like EG4 device, which allowed us to start looking for these devices connected to the internet. We actually found a ton of them behind an application called Shine Monitor, which is a Chinese-based monitoring system. So we're not sure if those were EG4 devices being sold in China or if they were LuxPower devices that just happened to be using the same user agent, since they seem to be just using all the same code between each other. We didn't find any major issues with the Shine Monitor application, but we also didn't mess with it too much since it was an exclusively Chinese-based app. But we did find a bunch of interesting OSINT.
So some of the devices that we found, like I said, were using public IPs. So we tried to figure out if we can find any locations. One of them we found was in Sri Lanka. It was a tourism building in Sri Lanka. The interesting part about that is if you look on like Google Maps, you can see the building and kind of like see if you can find any solar panels. So first we found some of the AC devices on there, which I thought was interesting, but then we found the solar panels that are also there. So pretty good likelihood that the inverters actually exist. So then we decided that, hey, no, we can kind of dig a little bit more and peel back this onion more.
Yeah, and that OSINT will matter once we get down the full stack of CVEs. So we started looking at the Modbus information on it, and this is related to two of the CVEs. They have clear text Modbus communication, which is a major issue because it means if you have the ability to talk to the device, you can intercept what it's doing, but you can also set configurations remotely because there's no authentication on it. It's also broadcasting its serial number in plain text, and that serial number is really high value. Once we have that serial number and we can start doing some OSINT, you'll see that we can do some like account takeover and that kind of stuff. To be fair to EG4, this is like a industry problem. There's like none of the solar devices we looked at have any use of like TLS or IPsec on the Modbus. Even though Modbus does support TLS, none of the manufacturers are using it. So it's something that the whole industry needs to get better at. But with that serial number, we can start downloading firmware to look at it. This is the second set of CVEs. Turns out the firmware has no authentication on it, no hashing to confirm that it's authentic firmware, and there is no ability for the device to check for modification in the firmware, and the software format they were using is like modifiable without causing problems for it. So you can inject firmware however you want into the device, and that's not good because you can send authenticated commands. We could brick the devices like Dai did, and then yeah, just all kinds of stuff if there's no authentication on the firmware or authentication on the Modbus commands.
Jake mentioned the serial numbers being like high value. The serial numbers for these devices are almost like having a social security number. It gives you a lot of power to do things, so just revealing that information is pretty critical.
Yeah. So speaking of serial numbers, if we didn't have a device to get that number from, we could start trying to figure it out through their registration portal. So the registration portal is patched now, so we did responsible disclosure, but you could start doing all kinds of serial number enumeration with it, and you could enumerate serial numbers that had even already been registered by someone.
So Jake, you mentioned that it's patched. LuxPower also patched it, didn't
Yeah, so again, going back to EG4 and LuxPower being almost identical, the patches rolled out at literally the same time. So as soon as LuxPower's endpoint was patched, so was EG4's and vice versa. But what happened was if you took a serial number and put it in to the registration page, which didn't require any like personal information, like in fact, to create an account for LuxPower and EG4, you have to have a serial number and PIN to enter. So this is like totally unauthenticated, no information for them to trace who's doing this. But you could start enumerating the serial numbers, and it would tell you if the serial number was valid, even though it was already registered. So you could start, and there was no rate limiting, so you could just start guessing the serial numbers all you wanted, and they tended to be in blocks, so like they weren't randomized serial numbers. Like once you found like, you know, BG 07111, you could do about 50 numbers from like 112 to like 1150, and they were all valid serial numbers. But it would tell you that the serial number already existed. Then you could start guessing the PIN. The PIN was also not rate limited, so you could then guess the PIN. Once you have the serial number and the PIN, you can use that for registering your device or calling and doing a bunch of other stuff, start downloading firmware for it.
Or transferring a device.
Yeah, or transferring a device. But you could also enumerate unknown serial numbers along with their associated pins, because so we could get every serial number and pin associated with any of the LuxPower or EG4 devices. So at that point, we had a bunch of information we could use. Another interesting thing was once you had the serial number, you could initiate a password reset, and then you would get some information about the username and email that they registered with. And you could then use like that OSINT that we were talking about to go find out information about the target, because you could start looking for like the IP addresses and things of this. So like this one's an example of one that came from a PDF that they had, but I found one from like a YouTuber that had exposed their serial number and PIN. I plugged the serial number in, and when it came back, the first two letters and the last two letters happened to be identical to the first two letters and last two letters of their YouTube channel. So you can probably guess what the what their username was. And then the PIN for password reset is not rate limited. They still haven't fixed this, so there's no rate limiting on guessing the PIN. It's only a 6-digit number, so you can guess the PIN, reset the person's password, and have like a full count takeover.
The other one was an alphanumeric. This one is just numbers.
Yeah.
And not patched, once again.
Yeah, but if all of that sounds too hard, once you have the serial number, you can also just call EG4 and say, hey, I bought this from someone, and will you transfer control of the device to me? They post that on their social media that they will do that for you. Like this was a response from them on a forum of someone saying, hey, I bought a device, how do I get it transferred? So you don't even have to do all that other work. You could just go enumerate the serial numbers and call them up and say, hey, we'd like control. So this gets us to our final device that we're going to talk about, which was the Tigo Cloud Connect Advance. This device is used for collecting data from solar microgrids, specifically their optimizers. That's what it's used for, primary use, but it also does an important job of a keep alive signal. So in the US, we have requirements now that every solar farm on residential stuff has to have a rapid shutdown device. This is supposed to be so that like if there's a fire and like firefighters show up and they're trying to get into a building, like they don't have to worry about live power wires from the solar panel. So if this signal is lost, the solar panel is shut down. And this device, once connected, is responsible for that keep alive signal. So we found 3 different CVEs in this one. The first one was hard-coded credentials. Hard-coded credentials have been being used by Tigo for a long time. People keep finding them, publishing them, then they sort of change them, and then leave it there. There's also some like robust DIY communities that are looking into these devices. So like about 2 weeks ago on this German solar DIY forum, we saw them starting to look into the same command injection stuff that we had like found already. And they were like trying to get access to these devices because they don't trust that these devices are secure for the monitoring solutions. They want to get access and reroute the data that it's sending out to like personal servers. Based on the stuff we found, that's probably a good assumption by them. But by default, these only have HTTP services running on the CCA. In earlier versions of the firmware, you could turn on SSH by just browsing to cgi-bin/shell. And this was any device on the internet, you could turn it on. It used default creds to get access, so you had full SSH access to the device by just browsing to that page. I found several hundred of these still online because once you start installing them, that's the only time that it forces you to update your firmware. In the newer versions, since like version 3.8, that CGI bin shell endpoint has been removed by them, but ours still shipped with version 3.6, even though the newest version is 4.0 when we bought it. But you can still enumerate the devices, like find out like their serial numbers, which again, high value. You could go to the monitoring solution for Tigo and try to register the device into their monitoring application using the serial number. But you also got like location, a little bit of location data, whether or not they're using mobile stuff. But just you could see that the device is on there and what firmware version it's running, so you could know which endpoint to go trigger an attack.
And the most recent one we got was only like a month ago, right?
Yeah, we got
we got another device just to see how recent that update was, and it was running 3.6, so, and that's 3-4 years old.
Yeah. So the most useful endpoint on them right now is the CGI bin mobile API. It has a ton of functions, things like network info, reboot, a bunch of other stuff like related to other devices on the network for discovery and like figuring out where the optimizers are. But device info and device ping only require the default credentials to access. The rest of those APIs that do give you like sensitive network information and like the ability to configure like the settings on the device require an additional session ID that you have to put in. But it turns out like that first off, like the ping, the device ping, even though it took a like ping timeout that you wanted to use and should have been used for like device discovery, it had nothing to do with ping. It appears to be a covert backdoor for the manufacturer. When you go and look at it, it accepts a value from the user, but it's comparing it to this hash, looking for a magic number, and if you submit the right magic number, it turns on SSH and kills all the current SSH sessions on the box so that the manufacturer can get in.
So we definitely brute forced it, right?
No,
Obviously.
we didn't have to, we thought about it, but it turns out that they had a command injection inside their own backdoor, so you didn't have to brute force the hash for that. So because all they did was use a printf and pipe it into a SHA-256 to generate the hash, you can just use a simple escape character with like a apostrophe and a semicolon, and then you have arbitrary bash command execution, and this endpoint is being ran at root, so you can do whatever you want with the device at that point. So this just should be doing a quick wget to a Python server to show that we had like remote code execution on it, or remote command execution on it. But to get to, more interestingly, we wanted to get to those sensitive APIs that require a session ID. Turns out that that also had very little security on it and was being done in a insecure fashion. So when you call that endpoint, that device info endpoint we use for the initial enumeration, it not only creates the session ID, it actually overwrites any existing session IDs. So you know the exact time that you're executing at when you send that command to the device. And it turns out that the way they generate that key is by seeding srand with the current time when you call the function. If you've done any kind of CTF before, you probably know that seeding srand makes your random function not random. Every time you call random after the seeding, it gives the exact same output.
And this function only requires those default hard-coded creds also.
Yes.
So doesn't take much work to even get that far.
Yeah, and then these devices are explicitly configured to Pacific time, so we know what time zone that they're keeping their own internal clock on. And so it did try to salt the value, like that srand, but when you dig a little deeper, it turned out that the salt was just hard-coded. So again, once you have the hard-coded value, you can generate the session ID when you call the device info, as long as you know what time you called. And we are the ones triggering the remote commands, so we know exactly what time it was sent. So here's just a quick video of me showing that. The first one is an attempt to call the network info. You'll see that we got an unauthorized request. I then just pasted in that initial device info with a command to capture the Unix timestamp so that we could pipe it in. I then wrote a file for like an ARM emulator, or a POC on an ARM emulator that did the hashing with the seed value and the time to generate the code that we'll need. So that generates the session ID. Now we add the session ID to our call. And we have access to the device for anything we want now. So if you remember that keep alive, you can actually access the reboot now. I tried to do the demo with the reboot, but I kept screwing it up, and then I had to wait 5 minutes every time I screwed up for the device to reboot. So I went ahead and used the network info. But we can now send a reboot to kill the signal from the CCA and deny power generation to the TGOs. or anyone using a Tigo. I actually found like a solar farm in Slovenia making like 200 kilowatts. The average home is making about 8. So it was a fairly large solar farm, and we could have killed it if we wanted. It would have been very simple with this. And then just a quick Easter egg before we go. This is not Tigo's first rodeo at DEFCON. As I was dumping the firmware, they actually have an explicit link to the last time they were at DEFCON, to the slides from there. So we just wanted to welcome Tigo back to the DEFCON stage. So what's next is that the solar industry is growing faster than its security implementations. That's not all that surprising. That's what tends to happen in many of these startup industries. They're so preoccupied with getting products to market and trying to be the first to market. The security is one of the first things that they stop thinking about. So we need to build stronger partnerships with the solar industry to get them thinking about this. We need to make sure that they are actually considering their security as they're building it, and we need to get clear information on the supply chains, because we were able to link like Lux Power and EG4, but we have no idea if Lux Power is selling these the hardware to other developers, so this might impact other devices than what we have labeled here so far. And the code's just a disaster because they don't know where they're buying it from, they're getting it, it's all written in Chinese, they don't know how to debug it, and so they just need help with that.
You report the vulnerabilities and they say they have to go back to a different developer.
Yeah.
It's a disaster.
Yeah, so actually when we reported this to EG4, they told us they forwarded it to Lux Power, was how they handled the resolution of it. So in the meantime, never expose solar control systems directly to the internet.
I feel like that's obvious, but
Yeah.
Use a
Apparently
firewall.
not. Yeah, we found a lot of devices on the internet, so make sure that that's not on. Even if you are using a firewall, disable automatic updates, because we believe that's how some of these manufacturers are maintaining access to these devices. And then take special consideration of remote monitoring solutions, because that tends to be the source of most of these vulnerabilities. They try to add internet capability and they do it in a really crappy way. And so we can just ask more from these manufacturers, because the other problem is they're not being penalized for having bad security because everyone just buys them anyway. And so the more we demand from them, the more these kinds of talks happen, stuff gets posted online and news stories and that kind of stuff, the more they'll be forced to address this. So thank you, and we have about 5 minutes for questions, so feel free to come up and we'll be happy to answer them.
Sure.
You made it. The room's full, so that's good.
Went a little fast, but
Well, we ended with 5 minutes for questions. So that's what we're on.
oh no, that started 5 minutes early.
Oh, did it?
Yeah.
Oh. Whoops.
Look at the time. Whoops. You're flying through things, so I'm trying to slow you down.
Talk to you.
Testing, testing, testing. Sweet. All right, we'll get started here in a few seconds. We have 45 slides in 20 minutes, and we're going to do it. All right, yeah, we'll get it. All right, we are there. So I'm going to jump right in. Grab a seat if you can, but otherwise we're just going to start flying through it. So first off, anyone here last year see Rob King and my talk about SSH and Shamble and stuff like that? Sweet, awesome, cool. So this is like a really quick recap of that, but with lots of new zero-day and fun. So really fast overview of all the SSH stuff, kind of talk about some of the major SSH weaknesses of the last 2 years that have been pretty wild. It's been the most exciting time in SSH in a very long time. Then some new research, new vulns, new exposure stats, and then some updates to open source tooling. So first off, if you look at the SSH protocol state diagram, there's a lot of stuff that's clear text, then a lot of stuff that's encrypted. All your authentication tends to happen after the kext's in it, and then after you authenticate, everything's multiplex channels. So just give you an idea of how SSH works. A lot of folks don't realize how many different things leak out of SSH before you authenticate. So you get data from the TCP/IP stack, from the server version, the kexinit extensions, the server banner, all the way to authentication and handshake. And so there's many different places where you can learn a lot about the server even before you authenticate. And so we're going to take advantage of that for some of our research here. If you look at SSH across the internet, it is actually the second most common admin protocol exposed to the internet, excluding HTTP. So there's more SSH out there than there is almost anything else, including remote desktop, SNMP, almost anything else. And these slides will be online pretty quickly, so we're going to go quick, but feel free to look at them later on. If you look at what makes up SSH, though, it's really just two vendors. It's OpenSSH and Dropbear make up something like 98% of all possible installations of SSH. However, the long tail of things that are not SSH and Dropbear are actually really important. Those tend to be things like your ICS devices, OT devices, things like that. So you have the custom Cisco SSH daemon, the LANware, the LANcom, all this stuff. So even though these kind of oddball SSH daemons are not particularly common, they're pretty important when you do find them. Things like MoveIt, et cetera, that expose all your secret data. So SSH itself provides both a transport and authentication. So it's almost like TLS in that sense. You got a little version exchange thingy. All right, might have to yell back at them soon at this rate. But so SSH is very much like TLS. Then you have an encrypted transport done through kexinit, and then you actually do authentication. Then you do your actual thing. So when you look at SSH authentication overall, almost every server on the planet supports both pub key authentication and password authentication, and that's it. It's really rare to find a machine that doesn't support password authentication by default, because password authentication shows up as both password, but also shows up as what's called keyboard interactive, which just means interactive PAM, it ends up being just a password as well. So there's a long tail of weird stuff, but I want to talk about some really neat things you can do with SSH. My favorite thing probably is you can take someone else's public key and then throw it at a particular server and find out whether they can log into that server while only having their public key, not their private key. So that's really useful if, let's say, you want to find out who Geotan is by taking their pub key from GitHub and spraying the internet trying to log in as them, and then see whether you get half authentication or not. But there's other really useful things you can do with it. You can confirm that a username has access to something. You can see whether your own credential that you might have tried to rotate is still being used someplace. And you can always do it with just the private side of the key, which is fantastic. When you start getting into authentication itself, that's where you start getting the fun part. Once you authenticate, then you do all this other stuff. You can do interactive shells, of course, but also command execution that's blind. You can do file transfers, TCP/IP forwarding, things like that, VPN tunneling, et cetera. So when a SSH daemon punts authentication until after the protocol level authentication, let's say an SSH daemon just drops you to a login prompt, but after doing the SSH auth, you actually have a pretty wide attack surface. You now attack all these other things like these channels and other things like that because they're exposed in that post-auth, even though pre-auth technically scenario. So effectively, it's basically like TLS. It's a little bit different, but you can almost think of it as TLS. So I want to do a quick fun bugs. Terrapin was fun last year. They found a way to truncate the TCP session in a way that caused it to pick a less secure cipher, which let you do some neat crypto attacks. The XYUtils backdoor was probably one of the best backdoors in the history of the internet. The person involved or person spent about 3 years slowly gaining trust before they really twisted the knife and then dropped a backdoor. Unfortunately, got caught last second. We did this whole hunt for Geotan last year where we took their pub key and hunted the internet for them, and we found absolutely nothing, so they have fantastic OPSEC. Regression was one of the first RCEs and default OpenSSH in many, many years. So it was OpenBSD finally had to update their website again. But the great thing about that is this is really difficult to exploit on non-32-bit x86, but it's been shown to be exploitable. So weirdly enough, we're not seeing a lot of machines getting popped through it, but it's one of the first real severe exploits in a long time. Credit to the Qualys Threat Unit group. The MoveIt one is fantastic. This is probably one of my funniest, favorite SH bugs because it's so funny. The Move It, which is a software package you only know about because it's used to ransomware everybody, they support SSH, and the SSH control, they source it from a company called IPworks. And when you authenticate with a public key to IPworks in this stack, it would look at that raw byte of the public key, like the DARE encoded actual key itself, and it would treat it like a file path to try to open it up. For no possible good reason. Like, there's no reason why you take a giant binary blob and treat it like a file path. But the Watchtower folks found out that if you give it a UNC URL or back, you know, the localhost, $, et cetera, you can basically make it off to itself to its own log files and things like that and bypass auth. So it's a really funny bug. It's lets you know, like, there is some crazy stuff out there in SSH land where it doesn't matter whether you think SSH is boring, people do amazingly silly things with it. Another recent bug here was the Qualys threat unit again. They found a way to do a man-in-the-middle attack on the client by triggering an actual out-of-memory on the client itself. So effectively, you queue up the session and you start smashing ping packets into the client side of it, and the client doesn't actually remove them from the queue. You eventually trigger an out-of-memory error, which causes the handshake to fail in an interesting way that lets you basically bypass key checks. So a neat way to like turn a DOS bug into a man-in-the-middle bug, which is kind of a neat attack. There's another neat bug in the Go SSH library where if you use the API and kind of naively, you would actually authenticate the wrong key. The attacker would send a whole bunch of keys, and you would actually trigger the callback for the right key. They would never finish authenticating with the key. Then you give them a totally different key, authenticate with that key, and they'd think you're the first key again. So a really neat way to like basically pop shells and things that implemented this API poorly. As far as no one ever talked about what was exploitable, but we did some spelunking, and the only one we could find that looked like it's definitely exploitable is the NetApp Telegraph agent. Everything else looked like it was really difficult to actually abuse. And because it's 2025 and we're still talking about Cisco, they shipped another backdoor cred in SSH. This one is really interesting because it was only in a really narrow set of versions of their particular appliance. And it's the case where if they had just used like deny user root in their default configuration, because they don't normally support the root user, it would have made it a non-issue. So we're still seeing vendors shipping default passwords, and we're still shipping default configurations of SSH in a way that they're exploitable as a result. So one of my favorite bugs in the last year or so was this Erlang OTP SSH remote code execution bug. Has anyone here played with it a bit? A couple folks? All right, this is interesting because like you don't necessarily think about Erlang SSH team as being a very common attack surface. And if you look at the entire internet, there's almost none of these things on the internet that represent themselves as being Erlang. They all actually have a different name on them instead. So what's interesting about this is you would connect to it, you would just send the command exec function even before you authenticate, and you would just run it. And the neat thing about the Erlang one is it actually was Erlang code executions. You're actually evaluating Erlang code. So it's like straight up remote code execution without shellcode. You're just running whatever Erlang you want. What was interesting about this one in particular is that like, a lot of people didn't find it just because of how dumb it was, including us. So we released this tool last year called Shamble. We'll talk a little bit about it today. But the idea is that it's a research tool for SSH implementations. You can quickly scan all kinds of stuff. You can basically just like Shamble /24 and pop random shells out of all your stuff. And it does a really good job of finding all kinds of dumb bugs and embedded stuff and like weird SSH implementations without having to really think about it too much. You can use it to do post-authentication attacks. So if a vendor gives you a shell that's SSH but not really SSH, you can use this tool to like try to do TCP/IP channel forwarding and all this other kind of like fun side attacks on top of that channel. And you can do a lot of like neat things with like pre-authentication state transition attacks where you can like jam sessions in, things like that. You can also do post-session attacks. So cases where you're getting like a Git shell, we can then abuse the Git shell to upload a shared object to then pop a shell, et cetera. So it's a really neat library. It's all written in Go for basically getting shells out of a secure shell when you're not supposed to. So one of the things that we looked into is like, why did we miss the Shamble bug with, so why did we miss the Erlang bug with Shamble? Well, ends up when we were doing the SSH handshake, we would send the normal banner, the kex in it, the kex response, then we'd send the open channel or the exec, and then if we got a response back, we're like, hey, we got a shell, here we go. What's interesting about the Erlang one is it does not reply. So it won't reply to any of this at all. When it's in the wrong state, it just doesn't reply at all, but it still runs the code. So because we saw a timeout on our side, we just thought it wasn't exploitable. So we fixed that. Unfortunately, by fixing that, you have to actually, it's basically a blind RCE. You have no idea whether the RCE works or not. So the way that most vuln scanners check for this is they actually cause like a DNS lookup to bounce off the internet server, or they do something else that's basically like will ping back to you on the back end to let you know that something's happening there. So we try to figure out like, is this thing actually exploitable in the wild? Is it actually interesting? And there's almost like, there's like 4 Erlang SHDs in the whole internet unshowed that are out there. So like, okay, no one cares about this. Then we realized that it's actually the base platform for something called Cisco ConfD, which is used in like millions of Cisco routers instead. But it shows up on a different port on port 830, and it has a different banner because it has the word ConfD in it, not Erlang. And so once you figure that out, then it's like, great, now we can actually go after all this stuff instead. What's annoying about it, though, is the way that Cisco deployed it is also not very exploitable. They've got a separate shell and a separate thing, and it's like really tough to do anything with. So it ended up being like the most boring bug ever. The only fun thing about this bug is if you find somebody else who actually has an exploitable version, you can patch it by setting your payload to be SSH:stop, and you can remotely stop their SSH server as the payload, and then you fix it for them. So if you want to write a patching tool, it's super easy. You just make it shut down Erlang as part of the RCE, and that's a nice verifiable way to make sure it's vulnerable is you turn it off by making it less vulnerable. So. Alrighty, so recapping some of the stuff we found last year. We found about 27 million devices in IPv4 that had port 22 open. About 14 million of those would negotiate national authentication session, and we had 110,000 random sessions, like shells. And so most of the work of this talk is like, how do we go through 100,000 shells and figure out which ones are interesting? It's mostly just like scrolling through shells by the millions and just trying to figure it out. So we found about 9 unique vulnerabilities, but this whole test last year was only limited to port 22. And we found like, there's some of the fun bugs we found last year. For Ruckus wireless APs, we found like a pre-authentication command injection bug. For Digi-transport, you can just straight up auth bypass. This one is really funny because it was only exploitable if you hadn't SH into the machine since last reboot. So we're working with a vendor, and the vendor's like, we cannot reproduce this. Ends up because they're shelling in, setting it to the debugging tool, then they'd run the exploit wouldn't work. But if they reboot it, the exploit would work. And it took like months to figure out that it was this stupid case. It was like a Heisenberg bug for them. It drove us all crazy. We also found fun bugs in Panasonic switches, Realtext, SoftServe, GOGS, all kinds of fun stuff. We also found the silliest bug ever in Windows, OpenSH for Windows, where they took the most sensitive function in the entire OpenSH code base and backdoored it by accident. So there's a timing safe binary comparison function that made carriage return line feed aware, which just breaks everything. It's no longer timing safe. It actually leaks memory now, things like that. One of the fun bugs that like didn't get fixed at all was actually the unlimited public key testing. So DropBear is the #2 most common SSH daemon out there. We reported to the DropBear folks, hey guys, you can like test millions of pub keys per second against your server just by grinding away on them. Like you can take the whole GitHub 117 million user database, grind it against a DropBear box, and tell you which of those keys work in that machine. And they just kind of shrugged. So you can still do that today with DropBear. It's great. So 12 months later, like what's changed? What are the new bugs? What do we find? Funny enough, like if you look at the number of SSHs on the internet, it's actually back down to 2018 levels. We've actually like have less 22 open to the world than before. So it looked like there's a big spike of like new kind of tar pits and kind of fake anti-malware thingies, and they've actually most of them been shut down again. So weirdly enough, we're back to the exact same level of SSH on the internet as 2018. And this is the Shodan data. We also ran our own v4 scans and compared them to see like how different they were, and they line up pretty well. Another interesting take is the OpenSH. Has anyone here used failed to ban before? Cool, great, okay. Yeah, so failed to ban is the thing that watches your log files, and then when it sees a bunch of failed auth attempts, it like basically black holes or bans the person. It's a really dumb thing. Like we do it because we have to, because there's nothing out there better. So OpenSH finally added a built-in rate limiter into OpenSH itself. And it's great because it'll prevent a lot of these like attacks that require multiple attempts and so on. It actually like kills most useful exploits for SSH. Unfortunately, no one uses the damn thing. It's only 9.8 and newer, so no one's actually using the new version of OpenSH. So if you look at the number of devices that are unpatched, or sorry, that don't support this internet, it's all of them. Like it's basically made no impact to the exposure of the world because no one's adopted the newer version of OpenSH. So it'll get fixed eventually, but right now almost nobody's using it. It's like 500K or less out of the 14 odd million are even running a version that supports this rate limiting by default. So another useful thing is we thought, okay, let's look at like not just port 22, but every port that Shodan has ever found SSH on, and let's scan all of those across all IPv4, and then compare that with the Shodan results and see like what's different, right? Like Shodan typically will do a roll-up, so they'll say for a given scan, we've seen everything the last 30 days, we'll give you stats. You're not really searching a single day of data with Shodan, you're searching like a 30-day roll-up. We did a single flash snapshot, like the whole internet in like a 1-hour period, bang, on a really big server to snapshot everything real quick, go. So you'll see some differences here, like in port 9022, for example, there's only a tiny little bit of Shodan, a whole lot of our shambles stuff. Other cases, it's opposite, where Shodan found a whole lot of stuff, we found very little, and that's because those devices were changing IPs a lot, so they're getting double counted over a 30-day period. But generally, you can trust Shodan. Like we did a unfiltered, no exclusions. We just scanned everybody whether they liked it or not, and the results lined up really well with Shodan. So if you're ever worried, like, oh, is Shodan hiding a bunch of results not correct? It's actually pretty accurate, and our research really shows that it's dependable. So starting over from like, okay, what did 2025 look like versus 2024 from a scan from a couple days ago? We found more SSH servers, about 23 million, down from 27 million with a port open, but still about 14 million that have SSH authentication, still about 107,000 sessions, so about 110,000. So effectively, there's no real change. Like in terms of actual exposed SSH daemons, there wasn't really a big impact between last year and this year. So we went ahead and said, let's go scan other 110 top SSH ports. That added another 2.3 million daemons and another 20,000 more shells, and we found a lot more bugs. So yay, more 0 day. So what was really sad, though, is we went back and looked at all the machines that we found last year. So all the Digi routers, all the machines we found new fun bugs on, and we had a big list of them, right? Some of these even spit out the serial number of the device, you know exactly who they are, what they were, et cetera. And in case like Digi, we even told Digi, the company, here's a list of all the serial numbers of affected devices. Please tell your users to patch it. Nobody patched anything. It's actually worse than it was last year. So we've actually found more vulnerabilities in the stuff we released and patched in advisory last year than we did this year, like it's this year than last year. So no one cares. So you can do all the research you want, you can tell the world, but no one's going to patch your stuff, so whatever, have fun, hack things. What was interesting, though, is we started digging into like the other odd ports, and we started finding all kinds of other interesting stuff. So of those 130,000 shells we found, about 50,000 are like real things. Some of those are definitely honeypots. We've got a really good honeypot fingerprinter. Like, for example, if you connect to an OpenStage port and it gives you the banner, and that's it, it's probably OpenStage. It gives you the banner and then also spews the kex in its string, it's probably honeypot. So that's a super easy way to find like all the Paramiko-based honeypots. They just do the handshake slightly differently, and it's easy to check. Sonic walls will authenticate you in, and then you can basically do authentication on top of that. And then about 14,000 new bugs are these carrier Ethernet switches that are all across Asia. Basically, they run like most of Thailand. And these things are just straight pop shell done. It's great. So I'll go into some details. So hopefully this isn't too flashy, but this is just what it looks like when you're scrolling through 130,000 sessions trying to find new 0 day. It's just a lot of grepping until you find new fun stuff. So the new bugs. First one I mentioned, these are all pending disclosure because we only found them a couple days ago. But this one is fun because it's not just the port 10, it's port 1022 is an actual real SH shell. But then if you scan port 830, similar to Cisco, it's a netconfd yang thing, where it's a big XML blob, and you can like reconfigure the router by sending an XML back to it, things like that. So funny enough, this auth bypass works in both. You're able to basically send your SH auth method to be a single null byte, and it just logs you with no creds, which is great. The other fun one you found was this post SSH failed login. So this is PBX. It's a kind of an older PBX. And when you first connect to it, it bypasses off, drops you to like a username password login. Once you fail the username and password 3 times in a row, it drops you to a shell. It's great. So all you got to do is like fail to log in 3 times, and then you get a free shell, and then from there you're done. It's like it's the dumbest thing ever. Another fun one we found last year is that you connect to an SSH port, and then you see like escape key is blah, and you're like, wait, did you just telnet from my SSH? Yes. And you can do like the control bang, like a control escape bracket to open up the telnet prompt, and then tell it just to do whatever. So there's lots of fun like kind of mini subshell escapes like that. And the last one we found, though, is like absolutely hilarious. There's a Chinese ISP that requires you to run their own sneaky little SH daemon on a high port, and it's contractually required. Their Bastion host service is in their EULA saying, we will not support you in your cloud servers unless you run our special daemon. Well, this special daemon, of course, has an auth bypass, and it's Paramiko. So you give it any public key, and it drops into a shell as user none, uppercase N, because it's Python. And then you basically have a little mini BMC prompt, reboot the machine, reimage it, whatever, things like that, get the serial console. So it's really funny that the ISP in this case contractually obligated a backdoor that was trivial to exploit. So when you do internet scans, something I want to bring out there is there's always a way to get bonus vulnerabilities, and I recommend you do this. If you're ever going to scan the internet, the very first thing you should ever do is run Responder on the same machine. So get an internet box, set up Responder, just run it right now, set up TSpeed up in the background too while you're at it. There's also a tool called Flamingo that I wrote with Tom Steele at Atreides Partners. That's a lot of fun. That actually covers a few other protocols. We're in the middle of porting over SMB to Flamingo, so it'll do all of Responder soon, and it'll just be one nice Go binary. So we'll have that done soon. But basically, you run both these daemons at once, and then whenever you start triggering scans and attacks, random machines on the internet start throwing in the password to you. So going back to 2014, I did an internet-wide scan of SSH, and I collected 5,000 domain admin credentials by all of Palo Alto's customers, because Palo Alto machines had a thing called user ID, and they were configured to then connect into the attacking machine and find out which user was logged in. But they didn't know that they weren't supposed to do that on the internet too. So you could attack them from the internet and then collect their domain admin credential through NTLM, and you're done. You just own the machine because the Palo Alto gave you the domain admin cred. So if I did this with the entire internet, one of the big African national airlines still has the Palo ID user ID set up this way, and we still got their domain admin cred. What's interesting, though, is we actually got another new bug. So WatchGuard firewalls decided that they wanted to be cool like Palo Alto, too, and they started throwing their passwords at all of you as well. So there's some random 0 day in WatchGuard. I don't even know how the hell it's set up, but we started just getting thousands of random WatchGuard domain admin creds flying into our scanning machine just because they decided to connect back when they got an alert from a port scanner. So free 0 day. I don't know what useful it is, but it's a good reminder. Always run TSpeed dump, always run Responder when you're doing scans because you get bonus 0 day. So about to run out of time here, but Shamble got some new features, lots of new stuff. You can skip known versions. You can say, I don't want to do weird stuff in OpenSH. I just want to only focus on the weird stuff. You can give it some regexes, some new auth bypass stuff. We added Hanobox bad keys database, which lists of all the known leaked keys. He also did an amazing work of dumping the Fortinet major leak and pulling all the Fortinet appliance keys out of it and adding that to the blockchain lookup thing. So you can basically use this to find out are any of the SSH keys in your environment already compromised, and now Shamble will tell you too as part of it. Whole bunch of built-in checks, lots of kind of usage information here for running it. You can do almost anything with it, like is a stale SSH key still being used? Is this default password still work anywhere? It's kind of like a everything utility Swiss Army knife for doing SSH testing. And then lastly, you get an interactive shell, so you can do Control-E and make TCP/IP forwarding, do some port scanning, things like that, all from the shell, as opposed to having to create your own SSH client. And if you don't like our tool at all, that's cool. We're actually in the middle of porting Shamble into Nuclei itself. So if you use a Nuclei scanner, we're hopefully going to have all the same Shamble checks available as Nuclei templates soon and share the same code base. You can just run Nuclei like normal and get all these fun bugs dropping out on the Nuclei side. So that is the talk. Thank you so much. And I think I'm out of time. Do we have time for questions or just? No? Okay, thank you so much.
Excuse me one second, I'll introduce you. Good afternoon, DEFCON. How about some energy? Who's a fan of metal? All right. This is a talk about bare metal, though, and for cloud providers. So metal as a disservice, and here is Bill Demir-Kepper.
Thank you so much, everyone, for coming out again for another one of my talks. I'm really excited to be back here at DEFCON. And yeah, today I'm going to be talking to you about a wave of systemic vulnerabilities in these new cloud providers that have a machine learning focus. So for some background, my name is Bill Demir-Kepper, and I'm a security researcher with a background in hardware and software, as well as the web and cloud. I'm really passionate about security research that I can have an impact at scale. And recently, I've been working on automating vulnerability discovery with advancements in foundation models for code reasoning. Today, we're going to be going through a little bit of background to set the scene. What are bare metal servers, and what is the rise? What do I mean by the rise in providers that are intended to support machine learning workflows? We're going to go through the attack surfaces that bare metal servers are subject to, as well as a few case studies, before wrapping it up with a review of our lessons learned. So, for some background, there is a lot of large providers out there like AWS, Azure, and Google Cloud you're likely aware of. And in terms of volume, their market share is massive. It's not even comparable to a lot of these smaller providers. But what we started to see in the past few years as interest in machine learning has grown is the rise of these new or rebranded providers that offer competitive pricing for GPUs. Again, in terms of volume, they're nothing compared to these large providers. But if you're working in this space, you may be familiar with some of the names on the right because they offer competitive pricing sometimes at 1/10 of the cost. Now, what is a bare metal server compared to a regular VM? Well, we can separate it into 3 categories. Bare metal means you're running directly on the host. You're running on metal. There's no layer between you and the host. Whereas, for example, with virtual machines, there's a hypervisor between you and the host itself. And while that can provide some security guarantees, in the case of machine learning workloads, that can also sometimes impact performance with PCI devices. Another version is containers. Think Docker, where you still run on the host OS, but you're inside of a little container where you can't really do anything except interact with the GPU. We're going to be focusing on the left, bare metal. Now, one of the big selling points of bare metal is supposedly greater security. If you take a look, I have a few vendors here who claim that bare metal cloud servers are physically isolated from other servers. There's discussions about performance, better control, and improved security. And while this may be true in theory, what we're going to explore today is how in practice, you're really at the mercy of your provider. So there's been a lot of research in the past decade into boot security as well as hardware security. But in large, a lot of that focuses on either client devices or individual servers. What I've found is that there's limited bare metal cloud research, particularly against these modern providers. Established monoliths like the AWSs of the world have invested over a decade into their hardware security story. When I was first getting into machine learning a few months ago, before I started renting out GPUs, I was curious to make sure that the security story was at least somewhat okay. And that's exactly what I did in spring when I had this need. I decided to start renting GPUs and taking a look at these environments that I had access to. So let's go through the attack surface problem with bare metal servers. By design, you have root access. Now, we've seen that with regular VMs as well as containers, but the difference is that this is one of the main selling points. You have root access to the actual hardware. And unfortunately, this can expose significant attack surfaces. So for example, we have the UEFI and BIOS, boot time attack surfaces from the motherboard firmware. Any vulnerabilities in your firmware, such as during network boot, could be exploited by an attacker on the local network. We have onboard devices that offer a point for persistence. A NIC or GPU are examples of privileged components where, if compromised, they can access your host machine even after you've released the server to another customer. We also have firmware of motherboard and onboard devices being backdoored, and again for persistent access. If the provider doesn't do a great job of resetting the machine between customers, there's a possibility that an attacker can actually infect the host and maintain persistence for long to come. There's also the baseband management controller, the BMC. This is what enables out-of-band server access. It's how providers actually manage your server. It's responsible for cleaning environments between tenancy changes, but if this is compromised, you're out of luck, because at the end of the day, the BMC has nearly full control over the host machine. And finally, we also have the network. You may be exposed to other customer servers if there's improper isolation, and as a result, this can expose critical flows like provisioning, which may allow an attacker to gain code execution while your server is being set up. What we're seeing here is that we are pretty much dealing with a traditional firmware and hardware security attack surface with any device, but it can have way worse consequences because it's in a shared environment. Remember, you're borrowing someone else's server in a data center with hundreds of other servers. A lot of firmware and hardware attacks depend on physical access, but with bare metal cloud, that's actually not the case because you have root access by design. Now, how do bare metal cloud providers actually manage these servers? One of the most popular implementations I've seen is Canonical's Metal as a Service. The BMC allows management of a single server, but in order to provision hundreds of servers in a data center automatically, where you're not dealing with VMs or a hypervisor, MAS allows you to automate a lot of the process for provisioning, deploying a custom operating system, as well as deploying any customer-specific scripts or configurations. Now, what's really interesting about MAS, when I was first reading about it, is that it relies on nearly 2-decade-old protocols, such as Pixie Boot, in order to provision devices. Keep this in mind as we continue through this presentation. From a high level, MAS starts by booting into an environment for provisioning using Pixie Boot. Pixie Boot is a way of booting from the network where your device makes a DHCP request, and the DHCP server, in this case the MAS management server, responds with a specific boot image in order to load scripts that will retrieve your customer data, deploy any custom scripts, and so forth. The high-level flow looks like new, commissioning, ready, and at this point, when it reaches the ready stage, this is where the BMC is configured, and at this point, it can be deployed to the customer. Users can use MAS's API in order to control the device. So the provider might have a web UI, and MAS is really what's controlling all these servers and providing metrics under the hood. Let's dive into these attack surfaces. So starting with the boot environment. Bare metal servers often lack basic defenses like secure boot because, again, the point is customer control. It's not that secure boot was very secure anyways, but it effectively makes it even easier to hijack the boot process. So remember how MAS was using Pixie or network boot? Well, let's take a look at what that looks like. On the right, I have two boot options. The top one is for booting from a hard drive. This is an NVRAM variable. And the bottom one is a second boot option for booting from the network. This provides an interesting opportunity to corrupt the boot chain. Remember, if the way that MAS works is by when the device starts, it'll go request a MAS server, hey, give me a Pixie boot image, and this is the point in which provisioning scripts are deployed to the server. So one really interesting way I found of persisting on servers without touching disk is by creating a malicious boot option. Pixie boot requires a local DHCP server, generally speaking. But if firmware also supports modern network boot, we can specify a remote server in the boot option through something called HTTP boot. You can see on the right a device path. That is what your boot option would look like. And what you can effectively do is specify that the default boot path is that you need to first get an IP address over DHCP, but instead of requesting Pixie boot, you instead request a remote server, an EFI image from your attacker server. And this has been in the EDK2 open reference code for firmware, UEFI firmware, for over a decade. And if you have Pixie boot, chances are that HTTP boot is supported as well. And one really cool primitive around this that I found was that we can weaponize UEFI security features to protect our persistence. So UEFI allows you to create something called authenticated variables. This is typically used to secure policy variables like the signature database as well as a platform key. But a lesser known feature about UEFI is that you can create private authenticated variables. So what an attacker can do is that they can create a boot option that is protected with their key. If you don't have direct firmware access, in order to remove that boot option, you would need, or otherwise modify it, you would need to sign a payload with that key. As a result, an attacker can make it really annoying to change the boot order back to normal or reset configuration, even if they don't have direct access to the device during decommissioning. And if you want to change BIOS options, but you don't have console access, another trick you can do is that AMI and other independent BIOS vendors, so these are the vendors that basically create a base framework that UEFI firmware is built on top of. What they allow you to do is there's automatic open source tools to parse BIOS options in hidden UEFI variable structures. Now, these are undocumented, but these tools will effectively tell you this BIOS option is at this offset. And as a result, if there's any time you run into an issue where you can't access the BIOS, but you want to change maybe a security feature, you can use these tools to discover the offsets to these undocumented structures in order to downgrade the security of the environment even further. While these variables that contain the setup options are often no runtime access, and what that means is after you exit boot and you go into the operating system cannot directly modify these variables. There's a lot of other opportunities you can use, such as booting from a custom EFI image on next boot, just by changing the boot order and writing a simple, nearly hello world EFI application in order to directly set these variables and the offsets that you're interested in. If you're interested in learning more about BIOS hacking, there's great forums out there like WinRaid and Badcaps that have a lot of discussion on this exact topic. Moving on to the BIOS. What I've noticed is that there's a lack of user-friendly tools to inspect the end-to-end boot security story. We'll go over some of the utilities out there that solve part of the problem, but what I've consistently discovered is that there is nothing that covers the entire thing holistically. So starting with basic enumeration, just some simple Linux commands, you can install DMID code, which is going to dump some BIOS data. This is useful for understanding just details about your environment. What type of server are you running on? What type of motherboard are you running on? What is the BIOS version? There's also the boot EFI path, which has the default EFI partition, and this contains your bootloaders and any configuration files. What I mentioned about modifying BIOS options with your own EFI image, this is where you would put your EFI image, and then you just have to change your boot order. There's also the sys firmware path, which allows you to interact with various firmware information and settings. And this is honestly one of the first things I do whenever I get onto a new bare metal cloud provider is just this basic enumeration to figure out what I'm dealing with. Another really useful utility is ChipSec. And ChipSec is effectively a framework for analyzing platform security. Once you compile and run it, it'll give you a bunch of detailed information about common vulnerabilities found in bare metal environments. It's not comprehensive in the sense of it still has little gaps here and there, but it's one of the best utilities for just getting a quick picture about about the posture of your platform. You can see on the right, some of the things it checks for is Intel's manufacturing mode. It'll check if the BIOS is writable, is it protected, and it also explicitly tells you when there's something wrong. Like when there's a vulnerability, it'll tell you why it's critical and how you can actually exploit. Now, one of the defenses against tampering with the BIOS is called Intel Boot Card, and this is specific to Intel machines. This is a security feature that effectively establishes a root of trust from Intel to OEM firmware. If you're considering modifying firmware on a bare metal server, this might be one of the things you have to look after. Now, if it's applied incorrectly, or often not at all, it may allow an attacker to modify your firmware and actually put an implant for backdoor persistence. And if specifically manufacturing mode is left enabled, or the end of manufacturing is not reached, which effectively means the OEM keys have not been fused into the chipset, this likely means you can disable Intel Boot Guard. How do you know if it's enabled? Well, if you dump firmware using a couple different routes, one of them is through Intel's CSME utilities, think flash programming tool, it can be hard to find the right version for your chipset. There's also IBV-specific tools, like if you're running an AMI motherboard, there's AFU Linux for Linux. And ChipSec also, for example, has a built-in SPI ROM dumping capability. Once you have your firmware, you can open it up in a utility called UFI tool. And if you see these colored regions here on the left, yellow means it's partially protected, and then red means it's definitely protected. This can be a quick way for you to explore what parts of your firmware are going to be under scrutiny, being checked for their integrity. It might be worth actually exploring some of the unprotected volumes for opportunities to inject code. On the AMD side, there is something called AMD ROM Armor. This is a near equivalent to Intel Boot Guard, and like Intel Boot Guard, it provides integrity of the SPI flash firmware. I'm going to be honest though, empirically, it's rarely secure in practice. How do you know if it's secure? Well, there's this great open source utility just like ChipSec called Platbox from IOActive. This allows you to do basic audits of your environment, and it has a few features that are quite capable with AMD devices. Nearly every machine I've tested with AMD and Platbox usually has one or two big problems in them. And one of the other cool parts about Platbox is it also enables flash access, including read and write. So let's say that you do have flash access and you can write to firmware. You're not dealing with signature verification, or maybe the module that you're replacing is not in a protected region. What does that actually look like? Well, the UFI tool, specifically version 0.28, allows you to actually replace parts of the UFI firmware with your own image. Now, there's some tutorials on BIOS modding forums in order to, for example, like change modules or remove certain modules to unlock certain capabilities. But personally, my favorite has been the game hacking community recently has published some really cool work around, for example, backdooring SMM. And there's open source projects that have full tutorials. If you're interested in learning more about how to actually backdoor a UEFI firmware image, this project, SMM Infect, is a great place to start. For example, we can replace an unutilized SMM image with a malicious EFI driver that allows us to maintain persistence after we've released our bare metal server to another customer. So, we've discussed firmware persistence by modifying boot options and executable code, but how do you actually defend against this? Well, the real key is that you need to make sure to reflash nearly every part of your device whenever you're provisioning between customers. When I let go of my customer server and if I had bare metal access, you should go ahead and reset the BIOS to a stock image. Now, the how actually depends on your hardware, and this is one of the tricky parts about being a bare metal cloud provider. So some of the larger providers like AWS, etc., they have these platform resiliency chips that can not only reset firmware as needed, but can even detect tampering as it happens. Some BMCs also have similar capabilities, but it's really up to the provider to use them. For example, BMC Redfish interfaces are a way for you to access the BMC through a programmatic manner. But even if they offer the firmware reset or update capability, if you don't use it, and if the provider doesn't use it, then there's nothing stopping an attacker from backdooring your firmware, releasing the server, and then letting another customer unknowingly use a compromised server. OpenStack Ironic, a mass equivalent, does offer the capability to reset firmware automatically as part of the cleanup flow. But as far as I'm aware, mass itself, which I've seen in several bare metal cloud providers, does not have a default automated cleanup flow for firmware. One of my favorite primitives for exposing vulnerabilities in protected code is downgrading to an older version. Let's say that you're dealing with an environment where you just can't figure out Intel BootGuard, AMD ROM Armor, or whatever it may be, but you want privileged access to firmware. What you can do is that you can use traditional flashing techniques, but instead of using a firmware with your malicious module, you first downgrade the BIOS to an old version that has vulnerabilities. This is a technique I've seen work time and time again. It's extremely effective, and it's a great way to escalate your privileges from, for example, the operating system to the boot environment. And it still passes Intel BootGuard and AMD ROM Armor because the code is still signed. You're executing legitimate code. It's just vulnerable. Now, these features do technically have anti-rollback capabilities. For example, Intel has something called secure version numbers, but empirically, no OEM uses them in practice. What they should do is when a new vulnerability is discovered and there's an update released, they bump the secure version number, and this prevents downgrading to an older version with the vulnerability. But again, it's very inconsistent, rarely used in practice by major OEMs. Now, moving on, another risk to bare metal servers is PCI devices. Let's say you do a great job of resetting the BIOS after a server has been decommissioned. Well, one of the other things you have to worry about is the devices that are attached to your host. This includes your GPUs, your CPU config devices, the BMC, network adapters, and so on. Again, this is pretty easy to enumerate on Linux. There's LSPCI, the syspci path, and dev to see what sort of devices you have access to. And just to give you an example here, on the right we can see that this bare metal server I was testing has two Broadcom controllers, and they're controlled by this bnextEN driver. The reason this is really useful is because if you go over to the Linux source code and take a look at the driver, you can often find remnants of critical functionality like the ability to flash the adapter. So, for example, if you were interested in backdooring a PCI device, such as a NIC, you can go ahead and look at the driver, and often it'll include functionality to flash the NVRAM. And that's a great place to start if there aren't open source utilities already available. In this case, Broadcom adapters that use this driver can actually be dumped using ftool. A real critical problem with these PCI devices is that they can come with something called an option ROM. So these are EFI drivers that enable interoperability between the PCI device and the host. It's part of the device's flash, and if there's no root of trust, it is prime for a backdoor. The reason is, instead of just replacing, for example, the NIC's firmware, the option ROM is loaded into the host, just like any other EFI driver. So if you can replace it, it offers a really convenient way for you to maintain persistence and without having to do any firmware hacks to take over the host by other means, such as DMA. Now, decommission flows, like OpenStack Ironic, may reset the BIOS, but resetting the firmware of these onboard devices is rare outside of large providers. There is some silver lining there, like some OEMs like Dell and HP. They have at least a basic root of trust for components that come with the server. But outside of that, it's really rare to see providers, especially the ones that are starting out, to do any of these secure practices. Just to give you an example of what this looks like and what option ROM backdoors may look like, there's this great project from a decade ago called Thundergate. And one of the really cool parts about it is that the scripts allow you to replace Broadcom's firmware with not only your own firmware, but also an option ROM that is loaded into the UFI environment. If you're interested in tampering with Broadcom adapters and specifically option ROMs, this is a very great place to start, and it's something that I use throughout my research. Now, GPU firmware is a little bit of an interesting special case. NVIDIA GPUs embed several microprocessors based on a custom architecture known as Falcon. Starting with the Maxwell architecture, Falcon microprocessors enforce a root of trust. This means that GPUs need to be signed. Now, GPU modding forums have made some progress in tampering with the firmware, including cross-flashing firmware from, for example, a GTX 1070 and porting that over to a 2070. But it still requires a valid signature. Unfortunately, in terms of tampering with the GPU, if you're using NVIDIA, your backdoor opportunity is limited to a supply chain. So if you were selling a GPU to a data center, there may be an opportunity there. But in terms of backdooring a bare metal server's GPU, it's going to be difficult unless you can get around this firmware signature verification system. Now, most of the attack surfaces we covered require specialized tooling, but where do you actually find them? Well, you can look at the target vendors, public utilities, but nowadays, a lot of vendors, I don't know, like Supermicro, what they'll do is that their tools will enforce signature verification, even if technically it's not required at all. There are some leaks on BIOS modding forums like WinRAID and Badcaps, and you can look on virus scanning platforms as well. And on the right, you can see an example of looking for open directories with specific Intel utilities. But my favorite has been scraping OEM driver packages. So for example, let's say you want to go get a Dell driver. Instead of just stopping at that driver, write a script that will download every single Dell driver ever released. Extract those zip files, and I guarantee you, you will find very interesting leaked utilities just left in some driver packages on accident. For example, below is a script that just vibe coded for Supermicro that allows me to enumerate every public utility and actually download the zip files. And this is how I was able to get certain tools that allowed me to flash the BMC without actually needing to run into the firmware verification problem that the new equivalent tools had. Moving on to the BMCs, so this is again the heart of your data center server. It enables remote management and monitoring, and it's going to be independent of the operating system and the CPU. You can see a diagram below from Cloudflare that kind of discusses what this looks like, but effectively it's a chip on your server that allows the server to be managed remotely, and even if the actual host is powered off, if the BMC is turned on, because it's kind of like a tiny PC inside of your server, it allows full management. For example, you can access your KVM console, etc. And what I found is that this is actually a prime target for finding vulnerabilities in order to backdoor your device. It requires significant time investment, but if you're willing to put in the time, almost always there is some issue that allows you to backdoor the firmware. So, for example, if the BMC exposes itself to the host, in order to enumerate it, you can use utilities like IPMI config and IPMI tool. On the right, you can see a command where I dumped the BMC config for one of the servers that I was granted access to. And if you want to find easy, low-hanging fruit, look for proprietary customizations on top of the base code. So think, for example, ASUS. ASUS may use MegaRack as a base, but ASUS will add a bunch of customizations on top of this base BMC firmware. And that code, because it's specific to ASUS, is far more likely to contain vulnerabilities, whereas the BMC underlying code does still contain vulnerabilities, but it's going to be looked at far more. Just to give you an example of interesting features that I've discovered is there's proprietary undocumented commands to reset a BMC to stock. And if you can do that, well, you can just take over it because it has default credentials. And you really have to go to Google and look into the documentation for these, but I found multiple instances where by sending a undocumented IPMI tool command, you can just reset it to stock, and at that point you have admin access through the default credentials, and you can reset the BMC firmware to largely whatever you want, depending on the firmware verification present. So depending on the configuration, the BMC may also allow host or out-of-band control through something called the keyboard controller style or serial over LAN. These are known as KCS and SOL channels. Some tools offer greater access at boot, so if you execute a UFI shell and you run some of these tools, it'll allow you to interface with the BMC with greater capabilities than the OS tools allow you to. And similar to the whole modifying BIOS options trick from earlier, you can write a startup script for a UFI shell to run commands and exit. A diagram below shows kind of all the complexities and different ways that you can interface with the BMC. And each one of these are a great opportunity to look into by default, does it allow access? And if so, what is the privilege level of that access? Another really important point is that just because the official tool from a vendor says that you can't modify firmware, that doesn't mean you can't modify firmware. In this example, I was dealing with a server where the official tool, GigaFlash X64, told me that my modified and backdoored BMC firmware did not match the BMC firmware's signature verification mechanism. But when I found another vendor's tool for the same BMC chip, the AST25000, what I found was that I could easily flash the target chip because at the end of the day, the signature verification I was seeing was just client-side. So again, target vendor may enforce restrictions in their flash tool, but another vendor's equivalent for the same chip may not. And not all BMC firmware is created equally. For example, what I mentioned earlier around whether your BMC has signature verification, well, for one of the servers I was dealing with, which was an X11 Supermicro server, I found something interesting, where the firmware was signed, but technically it wasn't really enforced. So here, Supermicro's documentation says that for these X11 and H11 generation systems, Supermicro has added the capability to cryptographically sign the software, but you keep reading and you realize, wait a minute, because of backwards compatibility, it's not enabled by default, it's not actually stock at all, and it's just an example of just because you see firmware signature verification doesn't mean that it's actually there in the first place. In this case, what you could do is you can downgrade it to an older version of the BMC firmware that has a vulnerability, or you could also largely use these other vendor tools to take over the flash without having to worry about signature verification in the first place. So again, firmware assigned, flash with a valid but vulnerable version, and look for vulnerabilities in other vendors who use the same BMC chip. Just as a few examples, Binarily has found several vulnerabilities inside of Supermicro's BMC software. So for example, even if you are dealing with a Supermicro environment that has signature signed firmware, you can downgrade it to an older version before 2024, and you may be able to actually abuse these vulnerabilities in order to flash it again with your own image. Moving on, another serious risk to these bare metal environments, and one of my most favorite, turned out to be the network. Bare metal servers are subject to a similar threat model to that of any data center server, except it's way easier to get access. You don't need to phish anyone. You don't need to compromise an employee and then pivot onto the data center network, whatever it may be. This is by design root access to data centers. And network is critical to everything from provisioning, management, and potential cross-tenant access, so any issues in the network layer are bound to have a critical impact. Just to give an example, I was pretty shocked to see that trivial Wireshark and promiscuous mode would capture traffic from other client servers, even though I wasn't doing anything fancy. This showed that there wasn't even a basic segmentation or isolation. But moving on, even if there was some basic isolation of network traffic, because let's say that the switch remembers what MAC address is associated with what port, et cetera. Well, what about traditional ARP spoofing? It turns out it actually works extremely well. I was, again, just very dumbfounded by the network insecurity that I was dealing with these bare metal cloud providers. Again, these are the top providers in the machine learning space that offer the most competitive pricing. Most of them were, unfortunately, actually vulnerable to basic network vulnerabilities that reminds me of like 2 decades ago, Cain and Abel style attacks. We'll see specifics in the case studies, but this was a really interesting find that opens the door to a few interesting attacks. Again, another classic simple pen test red team trick. You can scan the internal data center network, look for low-hanging fruit, and sometimes you're behind a VLAN, but if this is enforced at the bare metal host that you have root access to, which in the cases I saw VLANs was, then it doesn't really matter because you can easily bypass it. Besides the data center's infrastructure, you can also scan other customer servers. So let's say that you apply firewall rules at the gateway. So in your, let's say, provider's firewall web UI, you block all ports except 22 or whatever it may be. Well, if I'm on your internal network, what I actually found was I was able to access significantly more surfaces than the customers had intended to expose based on the internal network access compared to the external network public IP. Just to give you an example, the screenshot below is from an Nmap scan of an internal data center network where I found a lot of low-hanging fruit like a decade-old vulnerable SSH daemons as well as IPMI access and so forth. Again, if you're dealing with a bare metal data center network, it's really worth checking the local network whether you can hit other servers as well as the data center's internal infrastructure. Now, one really, really cool attack that I found was when I was renting this bare metal Mac Mini to test its inferencing capability, I noticed this Wi-Fi symbol at the top bar. And I found that not only could I enable Wi-Fi, but the data center had an open network for visitors. So this wasn't visible when I was renting a Mac Mini from, for example, AWS. From what I understood, AWS actually appears to have disconnected the Wi-Fi PCI device in hardware. But what I found was in this case, not only was it just as simple as clicking the toggle, but they had an open network. And it was really, really cool to find that Mac OS, their Wi-Fi NICs, actually allow for something called monitor mode by default. So this allows you to not only intercept traffic, for example, on your open network, but it allows you to see what's going through the air. And these are the raw frames. So for instance, these locked networks you see down below, I saw multiple authentication, like EA poll, if you're familiar with WPA2 cracking, et cetera. This was a really interesting way of going from like, a remote attack scenario to a physical data center attack surface. And the reason I didn't include this in the case study sections is because once I hit the open network, I was a little too scared to continue on exploiting devices there because the data center wasn't owned by the provider. They were just reselling that data center's network. And I did try cracking the WPA2 EA poll handshakes. Fortunately, it wasn't anything in any normal dictionary. But I still found this just as a really unique attack vector that bare metal servers can introduce to your data center that I haven't seen discussed before. So going to MAS again, remember how it uses those decade-old protocols? Well, again, Pixie boot over DHCP and HTTP for their provisioning API, it's a great opportunity for you to go from an insecure network environment to cross-tenant RCE. So what we're discussing here is not technically a MAS vulnerability. This would require your data center or your provider to have insecure network segmentation and isolation. But MAS does make it pretty easy for you to take advantage of these provider weaknesses, as we'll soon see. Another interesting fact I found about these MAS servers is that they expose a SQUID HTTP proxy by default. So this is used for like caching, for example, APT packages, et cetera. But as an indirect result, even if you were isolated from other servers on your network, but you were exposed to the MAS server because your server needs to be able to provision and get config, yada, yada, you can actually tunnel through the MAS server's HTTP proxy in order to, for example, hit other servers on your network. Like I wrote a very simple Python tool that used this HTTP proxy to try to do a port scan of the local network just by like HTTP connect style. And to make requests to the MAS API, you need these provisioning keys. And this is basically when the server first starts, it'll send its MAC address to MAS. And if the MAC address is recognized by MAS as, hey, I'm provisioning this server, that's where you get these provisioning keys. But if you're already on an environment where you want to look at the MAS API, what you can do is you can take a look at the local varlib cloud folder and look for this object pickle file. It's the secret for MAS is not typically stored elsewhere, but in these pickle files, you'll find them in plain text, and you can extract them in order to attack the MAS API itself. And another interesting primitive that I found was that if you need a MAC address of another server on your network being provisioned, there's actually a race condition where you can go ahead and race the registration process where you claim to be this MAC address, and you receive the provisioning keys instead of the real server. In practice, what this means is that if a customer had, for example, specified custom credentials, let's say a password, or maybe they had their own scripts that runs at initialization, what this would allow you to do is access those customer config and scripts otherwise, and, for example, get access to customer-specific API credentials. Let's move on to a few case studies. So, again, one of the most simple vulnerabilities that I discovered was just promiscuous mode on bare metal servers. In this case, this vendor, I was seeing traffic from other servers without actually having to do anything special like ARP spoofing or anything like that. You know, one of the really interesting things I saw on the network was these DHCP offers from the gateway when servers were being provisioned. You can take a look on the right as one of these packets, but what it allows us to really do is, because we can see the DHCP offer as well as the request on the network, when we detect one of these DHCP discover requests, we can respond with a malicious PXE URL and server and feed the server our own EFI image to execute at boot. This is a way for you to go from, again, a network vulnerability into remote code execution. Another attack here is that when you detect that DHCP discover, you register on that server's behalf and get access to the customer config. If you see DHCP traffic on your bare metal provider's network without doing ARP spoofing, this is a great attack to go from, again, the network to RCE and information disclosure. So moving on to ARP spoofing, there is another vendor where I wasn't actually able to detect much traffic besides miscellaneous broadcasts through just promiscuous mode alone. But by ARP spoofing the MAS gateway, I suddenly started to see this massive flood of traffic. An attack you can do at this point, if the other servers believe you are the MAS gateway, well, you can hijack EFI images that are requested from the MAS server. Instead of spoofing a DHCP response or an offer or whatever it may be, you instead just man in the middle the actual MAS server. And again, since MAS uses these 2-decade-old unencrypted protocols, they allow you to take advantage of this network insecurity. And instead of, for example, serving the real boot x64 EFI image, you serve your own backdoored image that allows you to get code execution. Now, one of the really special cases I found was with RunPod. Now, they're a fairly new provider, but they're still pretty popular in this space. They don't offer bare metal hourly rentals, but rather containers, so Docker containers with GPU access. You know, they have this community cloud for random people running servers, but I was taking a look at their secure cloud of vetted data centers. So what I found was that by trace routing from their servers, I found that they were reselling, likely through a bulk contract, through a provider known as Mass Compute. And what would you know, Mass Compute allows you to do hourly rentals. As a result, I found that I could do the ARP spoofing, again, get access to the DHCP traffic, but one of the really cool things that I found was that by doing this DHCP spoofing and ARP spoofing, I found traffic related to RunPod's customers. So again, I compromised Mass Compute, but as a result, because RunPod, a container environment, uses Mass Compute, they're inherently exposed to their provider's vulnerabilities. On the left, you can see an example where I saw these raw unencrypted traffic between nodes for Caltech's machine learning training runs. On the right is other unencrypted traffic related to logs from RunPod's managed inference service. And you can see their Docker containers and Docker container names, et cetera. And just, again, this is a really special vulnerability because RunPod itself wasn't offering bare metal in the first place. Now, the reason I called out RunPod is because they were also one of the only providers to actually address the vulnerabilities in time for this talk, and I want to give them credit for that. They did respond extremely quickly, and as far as I'm aware, they've isolated customer networks from mass compute's other customers. So to review a few takeaways here, high level. What we need to do from large providers, or takeaway from large providers, is that you need to reflash all devices, not just your BIOS firmware. You need to physically disconnect unnecessary PCI devices. Think that Wi-Fi adapter on the Mac Minis. You need to isolate the network. That is one of the most critical things you can do. Because at the end of the day, if your network is compromised, it's the easiest path to cross-tenant compromise. For example, I discussed a few attacks that I tried with BMC backdoors and NIC backdoors, but those all require significant time investment. The network was really one of the most simple attacks I'd done for an insane impact. Now, you can also look into custom firmware and attack surface reduction, but getting the fundamentals is even more important. And at the end of the day, don't use legacy BMCs. Use the ones that have firmware verification, et cetera, built in. And even then, realize that you're not going to be completely protected. So, lessons learned here. Bare metal just has a number of impossible to deal with attack surfaces. These large providers have spent nearly a decade investing into the hardware and boot security story. Virtualized may be actually better than bare metal in terms of security because, yes, bare metal may be more secure if implemented properly, but what we've seen here is that bare metal wasn't implemented properly throughout the board, especially with these new providers, and as a result, the security story is far worse than if you just use a VM. So what do you do to protect your organization? Well, first of all, don't believe in confidential compute. That's one of the things I've recognized in the last few months. It is just complete BS, at best a deterrent. No matter how many times these large providers try to sell you on it, don't listen to them. Honestly, what you should recognize is that we're not important enough to be targeted by some of these attacks. And so it's probably okay to actually use these hourly rentals, even from potentially vulnerable providers, because are we really going to be targeted? Well, maybe, maybe not. Is our workload really that important? Probably not. One thing you can do if you have a spare kidney or two is you can go ahead and buy 8 GPUs of your own and build your own server. That's what I decided to do. But I actually did it largely because I wanted to be able to experiment really quickly and not because of, for example, security reasons, even though that is a side benefit. For future research opportunities, I'd love to see more research into GPU PCI access. What can you do in a container with GPU PCI access? What about network vulnerabilities in virtualized environments? Are there any opportunities like some of the attacks we saw today for inside of containers or other virtualized VMs? And finally, can we automate the discovery of these systemic vulnerabilities? A lot of this had to be hand done and really frustrating, but I'd love to see more automation around it. Anyways, thanks so much for coming out. We're out of time for questions, but you can find me outside in the hall right after if you have any. And yeah, if you miss me, feel free to DM me on Twitter with any questions as well. Thank you so much.
Test. Awesome. Hi, DEFCON. How's everybody doing? Woo! Well, we have some exciting speakers today, and we have one of our speakers that is a first-time speaker, and we have a tradition here at DEFCON called Shoot the Noob. And so essentially we take a shot, and we can't tell you what's in the shot, but we are taking a shot with one of our speakers, and then we'll all join her to take it. Yeah, let's do it. Shot, shot, shot.
Thank you. Can you hear me? Good. Who here's first time to DEFCON? Woohoo. How many of you are aspiring hackers? Aspiring hardware hackers? How many of you are hardware hacking experts? Or hacking experts? So like all you aspiring hackers, experts, raise your hand. All the aspiring people, go talk to those experts. Make some connections, okay? So yeah, your homework, say hello to an expert after this talk. This is direct memory access everywhere. Kind of try to tie into the theme of access everywhere with the pun of direct memory access. Haha. I'm Joe Fitzpatrick. I have been spending probably more than 10 years of time doing fun stuff with hardware. I did silicon debug and some security research for a rapidly shrinking CPU company a while back. And now I do hardware security training. And yeah, I do actually own a pair of shoes with white LEDs in them because that's, you know, the kind of work attire that you need in this industry. And Grace?
Hello. Hello. I'm Grace Parrish. I am a current OSU student, Oregon State University, working on cybersecurity degree, and I am also currently a SOC analyst. In the last 9 years before I went back to school, I was a board level repair technician and also taught industrial control systems. I should be graduating in December, and I look forward to a career in offensive security. So, this is PCIe. I'm sure many of you who have opened your computers at some point or other probably recognize it. And for those of you who don't, it is a add-on card and interface to be able to add capabilities to your computer. Some examples include networking, RAID controllers, and probably the one most people are familiar with, GPUs. And you may be wondering, well, why are we talking about PCIe here? Well, so the whole revolutionary thing about PCIe is that it uses DMA. Back before DMA, direct memory access, our CPU would take data and move it from a system memory to a peripheral, or possibly from a peripheral to system memory. And this took up a lot of resources. And because while the CPU was doing that, it couldn't do any other processing. And so we decided maybe instead we should have the CPU ask for memory to be moved, or for data to be moved from the peripheral to system memory and vice versa. And this sped things up significantly because not only can we have a controller that's probably fast to do the moving, the CPU can continue to do whatever other processing it needs to do in the meantime. And so you may be wondering, well, why is there a talk about this? Well, that's fine for a CPU to be able to, or for a device to be able to move data around arbitrarily to and from memory, if you trust the device. But what if the device isn't trustable? What if it's malicious? Well, now the device has arbitrary read and write to the entirety of system memory. Now, the first kind of exploration into this was the Tribble made by Joe Grand back in 2003. This is actually the predecessor to PCIe, just PCI. This one's not extended. You may notice we have a card. Again, it's PCI. And then from that card, we have a cable going off the screen. Well, what that is actually it's going to another computer. And that computer can use the cable and the card to arbitrarily read and write to memory on the victim machine. Now, this isn't particularly, easy to go unnoticed. It's kind of obvious, which brings us to FireWire. FireWire is a cable that is used to move data from one device to another, and it does it pretty fast. I'm sure y'all could probably guess why. DMA. So this cable was used primarily for cameras and used a lot in Macs. But now suddenly we have DMA outside of the case. So instead of having to tear open a case and put it in a card and a cable going out, we can instead just walk up with a computer and a cable, plug it in, and perform a DMA attack, all with parts completely off the shelf.
Cool. I got to do this slide because I'm the pro. So this is a tale of epic procrastination because this spans over a decade at this point. Way back in 2014, I presented here at DEF CON. It was my first time at DEF CON presenting about Slot Screamer, which was a PCI Express device that did DMA attacks. Sounds familiar, huh? And then a couple years later, Ulf Frisk did some amazing work, and I basically got a card that was mostly off the shelf, changed a few registers, and did a cool demo. Ulf went and took that and turned it into this incredible suite of tools that will let you go and own any operating system using the same hardware, but a bit more configuration and a bit more software. So it was aware of operating system structures in memory. It could go and modify them, inject processes, get files. It was pretty amazing. Far more than I had the patience to ever do. Yeah, attention span, procrastination. Anyway, then as a follow-on, there was an FPGA version. So using starting with a Xilinx reference board, you could basically use an FPGA to overcome some of the limitations that Slot Screamer had, such as 32-bit addressing. And actually past that, there were a couple other projects. Thunderclap from University of Cambridge put together a tiny little $3,000 or $4,000 board that they used to go and poke at some Thunderbolt and IOMMU issues. ThunderSpy in 2020. So yeah, there's been a steady progression of stuff like this, and I've been keeping my eyes on it and perhaps meaning to do a lot of work and never actually getting around to it. But luckily, other people were getting some of it done too, which is even better. As we're going to go through, though, we're going to talk a little bit about threat modeling. Who likes threat modeling? I used to joke about armchair hacking. It's where you just sit and think about things, throw darts at the wall. And then I realized if you want to bill hours, you just call it threat modeling. Four-question threat model that Adam Shostak's been using is pretty cool. It's way less structured than a lot of the other things, but it actually kind of does a good job of getting straight to the important stuff. So basically, what are we working on? We're going to go through a couple different aspects of PCI Express. What can go wrong? We've seen some examples of that already. We can use that to inform our answers, or we can kind of speculate. What are we going to do about it? Do we fix it? Do we just tell people not to do it? What's the solution? And then did we do a good job is kind of a good follow-up because, if we're not doing a good job, why are we wasting our time doing this armchair hacking when we could be taking a nap or going on vacation? So for PCI Express, what's the threat model? What are we working on? We're working on high-speed interconnects. We need a way to connect devices in a system very quickly. What can go wrong? Some malicious devices, errant devices, devices that get programmed with malicious firmware or something like that. What are we going to do about it? Basically, the decision was just keep it inside the case, right? Oh, well, the trust barrier is the case of the computer. We're going to have an intrusion alarm that lights a light up or something, or tells the BIOS something happened if you open the case, which maybe was fine 20 years ago. So did we do a good job? Maybe, based on the threats at the time. If we kept it inside the case, we probably did an okay job. So, yeah, Grace.
So now you may be wondering, well, what are the steps of attacking PCIe? So first you're going to connect your hardware. Then the computer is going to enumerate that hardware. Then the device is going to enable bus master, and then read and write memory. And then finally, you get to present a talk at DEFCON. So, connecting hardware. So here are some examples of various hardware. You may notice that PCIe comes in various shapes and sizes. There's 1x, 4x, 8x, 16x, and even some interfaces that you may not recognize, or you may not realize is PCIe, such as M.2. You may also realize or notice that there are USB ports on many of these cards. So, fun fact, those are not actually USB. One of the things about making implants for machines is sometimes you don't have the space that you want, or the space is elsewhere in the machine. So what that actually is it is a port that connects to a cable that will then connect to our actual implant. So it may look like USB, that's because it's the port reused, but it is actually PCIe over a USB cable. So after we've connected some hardware, now we have to get into enumeration. So the root complex enumerates buses, and I'm sorry, but the lines connecting the buses aren't super visible on the dark background, but I will try to illustrate where I am talking about. So the first bus is, or the 0th bus, is from the root complex on the left to the switch, and that's going to be bus 0. Then the switch also has a bus going from the switch back to the root complex, that's 1. Then from the switch to the left PCIe endpoint, that's 2. From the switch to the diagonal PCIe component, that's 3. From the switch to the legacy endpoint, that's 4. And so far, we've been going depth-first search, and that's how PCIe is enumerated. So next, we're going to go from the root complex at the center to the PCIe endpoint, and that's going to be 5. And then from the root complex on the right to the PCIe bridge, that's going to be 6. And then it's really hard to see PCI bridge. And then it's really hard to see, there is actually a PCI bus down below the bridge, and that would be 7. And the root complex connects all of these endpoints to the memory so that the devices can write directly to the memory. Here is an example of LS PCI output showing all of the various devices enumerated.
Do you want to help me with like a little ad hoc hack right here? Yeah? So I'm listening to Micah Flea's talk across the way because I can hear it. And I bet if we all yelled like, "Great talk, Micah," he would hear us. So you want to help me with that? So on 3, great talk, Micah. Ready? 1, 2, 3. Great talk, Micah! I don't know if he heard that. But back on topic, you came for PCI Express, didn't you? This is why I procrastinate a lot. I get distracted. So we want to read and write memory. We're getting to the point we've got transaction level packets, right? So the TLPs, these are the things that like we get to the point, hooked all the wires up, we enumerated, we know who's who, and we just start sending these packets back and forth. The first group of them are about memory. We want to read memory, and we want to write memory, which does basically what you expect, reading and writing memory. Configuration read and message requests are a special type of PCI Express transactions. We're not as interested in those. They're not used nearly as much as the memory read and write, especially when we're doing DMA attacks. And then last, we've got completions. These are the responses. So when you do a read, your response is a completion with data. So that's all complicated. You don't want to sit there writing TLPs one at a time. That's what's great about PCI Leech, is it kind of does all that work for you. You want to read a certain block of memory, it does the TLPs, sends them to the hardware, whether it's a slot screamer or an FPGA, which goes, grabs the memory, gives it back to you, and it does stuff with it. It parses tables, does whatever it needs to find processes and memory. It's pretty cool. So I'm going to skip over this example based on time. First example I had was dumping memory, where you basically plug this card in and dump all of memory. So you grab 4 gigabytes of memory, and whoop-de-doo, you've got a memory image. You can go and look for cool stuff. I'm going to show this next one, though. This is the lock screen bypass. So this is using an older piece of hardware. This is using slot screamer. You plug it in the system, and this is a Wi-Fi router that happens to have PCI Express. It's a mini PCIe slot. We hook it up over USB to this computer. We've got a console as well. So on the console, we're going to try and log into this thing. And actually, we're already logged in, but we want to look at a file. Let's say we want to check the shadow file. Come on. So shadow file is owned by root. I'm not supposed to be able to read it. And if I go and cat it, I get my permission denied. So I'll go over and I'll run my little script, which is going to go in the other window. This script is going to go talk to that PCI Express device and tell it, hey, go find this address in memory, patch it, and see what happens. So we found our device. It's this NetChip technology board. We patch it, patch the generic permission function in Linux. That's what checks the permission on file accesses. That little thing over there read and wrote to the memory for the CPU. And if we go back and we try and cat etc shadow, it should work. And it works. There we go. Yay. OK. So we can also unpatch it and make it go back to normal. But we're going to call that done. Is this you or me? OK. So key takeaway, PCI Express is permissive by design. And that demo isn't anything different than from what we did 10 years ago, so let's talk about what's changed since then. So there's been a lot more approaches and ideas behind what to do. So here's my DMA attack taxonomy. I just made this up. There's tethered attacks, there's drive-by attacks, and there are embedded attacks. So a tethered attack looks kind of like this, right? We've got the system on the left. That's our target system, right? We see there's a cable running over to the thing on the right, and that is the attack device. That's actually a Xilinx FPGA board. And attached to it on the far right is a little blue board. That's a FTDI high-speed I/O board. So, and you can barely see there's a little itty-bitty, there's a cursor there, that little bitty thing over there, that little USB cable, that connects to the computer that actually does all the real work. So you're not going to sneak up to someone's laptop and do this to it, right? This is it's slotted into a machine. You got a lot of hardware. It's kind of a pain in the butt. So that's a tethered attack. Now, a drive-by attack would be something like you just walk up to the system, plug something in, and do your whole thing. And so what we've got here is we've got an Express card reader, Thunderbolt 2 Express card. So you plug this into a Thunderbolt port. You got an Express card. In the Express card reader, you have an Express card to mini PCI adapter. And in the mini PCI adapter slot, you have one of the old slot screamer boards. And this can do the same thing, right? So if you don't have any Thunderbolt protections turned on, which we'll talk about in a second, then you can just walk up to a system, plug it in, and do some DMA. And last, we've got embedded type attacks. And this is where we actually stick the thing inside the system, close it up, and leave it there for a while. So this is Pico DMA, which is a project from a few years ago, I believe 2019. And what they used is they used that board on top, which is called Pico EVB. It was a little Xilinx development board. And they paired it up with these PyCom modules, which let them do either wireless, Bluetooth, or 4G connectivity to this device. And they could package it all inside the case of a laptop, and no one would be the wiser. You'd be surprised. How many of you have opened up your laptop and looked inside? How many of you know what every one of those chips does in there? Not many. I don't. So it's pretty interesting what you can cram in those places. Luckily, things are getting smaller, so it's harder to hide stuff like this. But whatever. So this is an embedded kind of attack. So here's my little chart. If it's quick access, it's a hot plug, it's short term, right? That's a drive-by attack. If we're sticking it in there, we're leaving it there for a long time, we're persisting over reboots, that's an embedded. Everything else is kind of like in between those tether attacks. They're a little more complicated. So let's kind of change gears a little bit. Let's talk about like the multi-tenant threat model. So this is like the cloud provider situation. So we've got a lot of cloud providers that want to give access to computers. Some of them want to give you bare metal. Some of them want to give you VMs. Some of those VMs, they want to have FPGAs or GPUs attached to them, which are PCI Express attached devices. So there's some things to worry about. So what are we working on? We're working on making money by sharing hardware. Okay, it's pretty much the threat, their objective, right? What can go wrong? Hardware-assisted tenant hopping. So if you go and get a VM on a system with a GPU, and you can do something with that GPU to access another tenant on the same system, that would be bad. So what are we going to do about it? We're going to use an I/O MMU to go and protect devices from each other, an I/O memory management unit. Okay? Did we do a job? It kind of works. So, Grace, you want to tell us about that?
Sure. So, in order to understand IOMMU, you first have to understand kind of what the problem IOMMU is trying to solve. So, as Joe just said, we're trying to prevent crossing boundaries using hardware. And so how we originally did this is we used our virtual machine emulated a device. And so instead of our virtual machine just being able to talk directly to that device, it had a driver instead for a virtual device provided by the virtual machine. Then the virtual machine has to take time to process, or the hypervisor has to take time to process that device, emulating it, and then it itself has to have a driver for the actual hardware. That's a lot of processing. So instead, what IOMMU allows us to do is our hypervisor actually uses the IOMMU to remap hardware so that the hardware just appears directly in the virtual machine's memory. And this makes things a lot faster. The virtual machine can just use the normal device driver, and it can just talk directly to the hardware. And one of the things that's kind of a byproduct of this is because the IOMMU has to map devices to various address spaces, those devices can't just arbitrarily read and write to memory outside of the address that it was written to.
Someone keeps moving this microphone up too high. So take away from that, the mitigations exist. There is features built into CPUs for nearly 20 years that can let us go and protect hardware devices from our system from hardware devices, and hardware devices from each other. So, of course, once we have something figured out, we always kind of make it harder. So let's talk about Thunderbolt for a minute. So Thunderbolt threat model, what are we working on? We want high-speed peripherals, okay? We want them outside the case. We want to plug them in, you use them, and then leave them at home or take them with us and bring them to another computer, like a high-speed drive or data capture devices. What can go wrong? Malicious Thunderbolt devices, okay? That's kind of like the answer to all of the what can go wrong in this talk. What are we going to do about it? Well, at this point, we do actually a pretty good job of authenticating and isolating devices. And did we do a job? It took time, but we eventually got there. So there are mitigations, right? Thunderbolt was released in 2011, right? That's a long time ago. How many of you were born in 2011? Okay, most. Anyway, and before the IOMMUs existed even before then. Mac OS 10.8.2 was pretty quick to have basically built-in support for the IOMMU to protect Thunderbolt devices. Of course, Macs were the only computers that had Thunderbolt devices for a while, so maybe that's why. But eventually, Windows 10 build 1802 got support for using the IOMMU and their kernel DMA protection in 2018, a scant 7 years later. And even Linux got in on the action. So in Linux kernel 5 in 2019, 8 years after Thunderbolt was released, they also had some of these protections built in. Now, they're not perfect. I'm sure there are issues in them. But the fact is, like, it was 8 years before they existed at all. So my takeaway from that is, like, Thunderbolt got fixed eventually, right? I actually, I've been working on this for a long time, so, like, I was like, wait, okay, so by now I'm sure that all these protections have been built into the operating systems, and I check, I'm like, oh, wait, no. Anyway, so eventually got fixed. So Thunderbolt isn't the easy way to just plug in and do a drive-by attack anymore. Grace?
So, you may be thinking, now that Thunderbolt got fixed, how are we going to do drive-by DMA attacks? Well, DMA finds a way. Who here, by show of hands, recognizes this port? If you are thinking that is DisplayPort, you are wrong. That is, in fact, Oculink. So, what is Oculink? Oculink is a interface that we came up with because we wanted to be able to attach our GPUs to our laptops. Now you may be thinking, wait, we just fixed Thunderbolt. Why aren't we using Thunderbolt? Well, Thunderbolt, while it is more secure, it also Thunderbolt has quite a bit of overhead, and also it's significantly more expensive. So what we decided to do instead was, once again, we brought PCIe outside of the case. So Oculink is basically just PCIe over a cable. Amusingly, a cable from server storage. So I don't think that's really meant to be plugged and unplugged as many times as they're thinking it will be for connecting a GPU to a mobile device. But I digress. And this is actually really kind of cool. We've taken this thing that's not supposed to be used this way, and we've decided to use it. And isn't that what hacking is?
So, some more armchair hacking. So what are we working on? We want high-speed peripherals, again, just like Thunderbolt, same thing. What can go wrong? Same thing. We can have malicious devices. Anybody want to guess what are we going to do about it? Yeah, nothing. Only use it in secured locations, like, yeah. Who here uses an eGPU? So when you leave your Oculink GPU at home, right? And then you take your laptop with you, which has the Oculink port on it wherever you go. But you never leave it out of your sight, right? So anyway, did we do a good job? Not really. So now that we got Oculink, right? Let's go and use it. Let's do it. Let's figure out a new drive-by attack for a cool demo for the talk. And I like to do like junk hacking, and I kind of feel like crypto's junk hacking because it's all crap. And so MetaMask is so I got some help. So is Dean here? Thanks, Dean. Dean helped me out with this demo. We're like, okay, so we've got memory access. We can read and write all of memory. We've got this device. What can we do? Can we go and mess with MetaMask somehow if we have the ability to read and write all of memory? And of course, the answer is yes. Is it playing? Here we go. So we got MetaMask running, and you can see here we want to go and send some money. And so some just random name that we choose, send some random person $1 of USDC. And so this is all on our computer. This is a browser extension inside of a browser, inside of a sandbox and all that crap inside of this machine. And we're about to go send it, but let's go run this thing. You see who it's going to, right? Well, that's just stored in memory. And so let's just send it to this other address instead. I mean, we just put a bunch of 6s in there to make it a little easier to make sure we got it working wrong. But anyway, so let's cancel that. We still have this process running in the background, continuously going and doing a DMA scan for the right string. But if we go and we get another transaction, we want to send some magic money, some Chuck E. Cheese coins over to some dude. And yeah, who cares how many gallons of fuel we took, but whatever. So let's boil a pot full of frogs and continue. And it's running. And so you'll see it'll take a moment, but as soon as we find it in memory, bam, it's overwritten. But oh, wow, what was that? That's okay, we keep looking. Memory is pretty crazy how fragmented it is, and how like when you free and renew stuff, like it shows up all over the place. So it's not easy to go and find out exactly where this is without scanning through all of memory. Anyway, we never clicked continue, we never clicked confirm, but like we were able to pretty much change that address in the time between setting up the transaction and going to go confirm and send that $1 to some stranger whose address ends in 6s. So I thought that was kind of cool. So Dean actually threw together this framework to help me put together this demo, Passive. So you've seen the movie Inception, right? There's a tool called Inception for DMA access and FireWire access, and so Dean thought that Passive, Peripheral Attack Simulation and Introspection Vehicle, would be a good way to do this. So disclosure, that was not on hardware, that was in a VM. Because it's a lot easier. But the reality is, whether you have a VM or whether you have a hardware-attached device, we're still doing memory access, and we'll talk a little bit more about that in just a moment. But first, let's diverge into some game cheating stuff.
Okay, so first off, show of hands. Who here cheats at games? Why? And for that matter, how do you have time to play video games? Yeah. See, that's what I was thinking. Probably because you cheat.
But who pays other people to develop cheats for them? Yeah, that's like if you're gonna cheat, like if you develop yourself, I think it's cool. But like I don't know, I think paying for cheats is kind of cheap. But actually, it's really expensive. Never mind. Grace, go ahead.
But yeah, so I don't really understand why people cheat. Developing cheats, that I can understand. That sounds like a pretty cool puzzle. But actually using that cheat to not play a game kind of defeats the purpose, in my opinion. But I digress. So here is a website that sells game cheats. So if you notice, on the left, we have just a cheat. And I know it's tiny text, but this is for 1 month. And even tinier text, it does not include the hardware you actually need to run the cheat, nor the firmware. In the center, we have the basic package for a measly $720. And what this includes is the cheat for only 1 month, DMA card, and firmware for that card. And then finally, on the right, we have something more for yet another ridiculous amount of money. Again, only for 1 month. And the thing about this is it's actually all built off of the stuff that people have developed and open sourced that we have talked about. Things like Slot Screamer, PCI Leech. They're basically repackaging this and selling it to you when you have it basically for free.
So yeah, it's always interesting to see what people will sell on the internet. And like the whole monthly service fee, it seems silly, but like it's an arms race. So between the game developers and the cheaters, so it actually is like every month you need to come up with new ways of deceiving the game to thinking that like you don't have a malicious device in. So for example, it's like this PCIe DMA NVMe thingy is going to basically like look like an NVMe, so that your anti-cheat doesn't say, oh, you've got a cheat device in there. It says, oh, you just got an NVMe, a hard drive, and that's what you're running from. So it's pretty crafty, the levels of stuff going into this. A lot of them are based on PCI Leech. Some of them ship with PCI Leech generic firmware. Some of them customize it a bit, which is good, but like the number of people who actually go back and support PCI Leech. So you'll see over there that like a few of these, Screamers, Squirrel, the ZDMA, and Elite DMA, they're all project sponsors of PCI Leech. So if you do want to go and mess around with PCI Leech, that's the way you should go. One of the key takeaways, though, is that changing the form factor is changing the threat model, right? So, changing to this game situation, like, we now have the owner of the PC being the person. So even if we had stuff inside the case, it's not really the same because, you're the owner of the machine. You can get inside the case. Another difference of changing the form factor is maybe going to a different type of device. And so, Grace? And pace a little higher.
Okay. So, how many of you have seen these before? So we have CF Express on the left and SD Express on the right. These are both relatively new devices, storage devices, and you may recognize them from some devices that you own, especially if, no. Yeah.
Who has used a CF Express device? Okay. Who has used an SD Express device? Okay. So I don't know if you want to spill the beans on what they are, though. But go.
And so basically, you probably have seen these. The interesting thing about these, though, is once again, they are PCIe and support DMA. So on the right, on the SD Express, you may notice we have a few extra contacts, and what those are is actually PCIe lanes, just like you would find on like a network card or M.2 device. Yeah. And so what threat model are they working with? So we know they are working with high-speed small storage. What could possibly go wrong? Well, I think you may have caught on to a theme at this point. It's malicious devices. And what are we going to do about it? We, of course, being the manufacturers of devices that use these. We don't actually know. They kind of don't invite us to their threat modeling meetings. So did they do a good job of preventing attacks? We also don't know yet. And so one of the things is, so how many of you have tried attacking any of these devices? Few. So you may be wondering, why is an Xbox up there? Well, actually, that aforementioned CF Express card is the exact same card that they're using for the memory expansion cards. It's just packaged in a nice piece of plastic. Also, we have the Nikon, which also uses that CF Express card. And then finally, this one is really new. This is the Switch 2, just came out a little bit ago, and it uses SD Express. And so, an example of SD Express.
Yeah, want me to take over?
Sure.
Yeah. So this is still in research. So CF Express, right? It's a device. It has NVMe. It has what's it called? PCI Express. And so what we can basically do is instead of plugging our, this is a card reader for XQD, which is pinout compatible and also PCI Express compatible with SD Express. So the reader is pretty much not much to it. It basically is wires it up to PCI Express. But if we wanted to, we could go and do something stupid like this, and we can hook up our camera with an adapter, which goes and takes the SD Express outside to an M.2 slot, where we put in our malicious device. And you can see on the screen it says card not currently supported. So it does check the device. It does enumerate. It does check to see if it's the right type of NVMe device. And then there's probably some magic that I need to be getting figured out to go and actually let it stay enumerated and not throw the error up and disconnect. Once we've got that, we'll have to see what this little SoC on here actually does in terms of, I'm not sure that camera has an IOMMU. This is a 7-year-old camera, but, you can be surprised. So it'll be interesting to see what we can get off of the device that way. So we got a Switch 2. Switch 2 is the first device that actually uses SD Express, which is pretty cool. I actually grabbed some SD Express cards a while ago and some readers. I was not really surprised to see that these are two different SD Express readers. One's Sabrent and one is SanDisk. They're using the exact same chips. The one on the left, the green board, has 2 of these little SD Express controller chips from Realtek. The one on the right has the same exact chip, but only 1. And these chips actually hook up to this other chip, which is billed as a multi-purpose one, but basically it's an NVMe to USB adapter, right? So we take SD Express and turn it into NVMe. We take the NVMe and turn it into USB, and we plug it into our system, and we store it, mount it as a mass storage device. So, Switch, brand new. I literally just got one last week. Who wants to see a Switch 2 jailbreak? Yeah? You want to see one? We only have 7 minutes left, though. So do you want to see it? Yeah, so do I. So, sorry. So the takeaway here is PCI Express is pervasive. I literally got the Switch the day I left to come to Las Vegas, so haven't had a chance to poke around too much, but maybe some of you will. There are some boards you can get. A couple folks have already made the adapter boards to break out the Switch into the NVMe pieces. You can get some adapters. So hopefully in time we'll get all the rigging hooked up and maybe we can poke at it some more. So we got to kind of scramble through. Let's resume this continuing tale of epic procrastination. I procrastinated and put it off all the way to the end of the presentation. So 2021, we finally got together a schematic for Erebus. We got PCBs put together in 2022 and had a panic because suddenly you couldn't buy the chips that we needed to put the thing together. So we actually had to do a redesign of some of this PCB to replace components that were discontinued. We're chip preppers, so we bought a lot of compatible chips to hopefully last us for a long time, so we wouldn't be blocked by not having chips. It would have been fine, though, because we were blocked by our own procrastination. We finally got the test jig together in 2023. Once we had the test jig together, we assembled the boards. And now it's time to profit, right? We're getting there. So this is Erebus. How many of you came here thinking I'd show off like a completely working, functioning Erebus board? Yeah, I apologize. I'm a procrastinator. But what I do want to go is talk about why Erebus exists and what we've put into designing it and what for. So it does power on, it does work. We don't have PCI Express fully working yet. We have some reset issues that we need to deal with. How do I get to escape? The objective here is we've got a Lattice ECP5 FPGA. We've got DRAM built into it. Not shown in this picture on the back side, we've got a spot to put in an SD card. So this thing fits where your Wi-Fi module might go. And you can pop it in a system and leave it there. If you got a 2 terabyte SD card in there, you can do a lot of memory dumps on a system before you go and retrieve it. So this is like the embedded DMA attack device dream once it works. You can see we've got some test code running flashing lights. One of the things we wanted to address is that a lot of devices, this is from PCI Leech's repository, a lot of these devices are using Xilinx's proprietary IP cores for PCI Express. One of the issues with that is licensing. They're actually not probably licensed properly and that shouldn't be sold the way they are. But more importantly, it limits what you can do in terms of messing with the TLP level stuff. A couple of the PCI Leech devices do let you get that level of control, but not all of them. So we wanted a fully open tool chain, fully open implementation that we could use PCI Express to do all the stuff we wanted to do. You can see in the upper left, we're planning on putting this on crowd supply. I'm working with Peter Estentemsky, who has done the Icebreaker at Glasgow and a few other hardware tools. So we're trying to make this actually a tool that is available and lasts and doesn't, contain pirated IP and all this stuff. But we'll see how that goes. Why Erebus? My objective is platform security. I don't care about game cheaters except for maybe as customers to buy a bunch of these boards, right? To fund the development, to actually get IOMUs used properly, because right now they're not. So you want me to breeze through? Go ahead. Okay, so yeah, you see there's a bunch of PCI Express devices here. It's a lot more diverse group of devices than we had on the first slide, because there's a whole lot of stuff that is PCI Express these days it's basically the standard interface anymore. It's kind of like if USB isn't cutting it for you, it's going to be PCIe. Takeaways, right? It's permissive by design. Mitigations exist. We can use them. It took time, but finally Thunderbolt is getting some of its stuff fixed. These form factor changes do affect your threat model, but again, PCIe is pervasive. Progress has been made, but there's still plenty more to do. The fact that I've been procrastinating on this for 10 years means that all of you can probably make more progress on this than I can. So if you're interested in poking at this stuff, the tools are available and the information's available. Let's try and work together to make this happen, because I'm not doing a good job of getting it moving. There is the four-question threat model we talked about a bit, and another shameless plug. I've been working with Adam Shostak and Eric Evanchik to kind of come up with a more formulated model for applying threat modeling to hardware. We'll hopefully present that at Sector, but enough shameless plugs. There's Erebus. What did I forget to say? Stickers. I've got stickers. Oh, yeah, thanks. There's a lot of people who helped with the support and the tooling of getting this up and running, have been working on Erebus with me, trying to get it to work. There's a lot of prior art inspiration that led me into this in the first place and led us to kind of like choose the things that we did. So thanks to all these folks and more. There's some links on there, and that is the last slide of our presentation. I'll go back to the links. Thank you. And thank you, Grace. Questions? Did you like that Switch 2 thing?
That was cool.
Hardware to break out PCI for what platform? For the Switch, I will put those links on the Direct Memory Access Everywhere repository once I put something on there. Hold on, there's a question at the mic.
That was great. You said you wanted to motivate platform security. What would you like to see out of the platforms?
I would like to see IOMMUs properly configured. I would like to see users actually having control about how they're configured. I would like to see BIOSes that properly allocate domains to different devices, as opposed to just throwing everything into a single domain. It's a lot to wish for, but when we have the real threat of stuff like this happening, that's what drives manufacturers to fix this stuff.
Thanks.
Okay. More questions out there. Thank you.
thank you for your patience. A little problem with the HDMI cable. So, first of all, thanks for staying and hanging in. It's end of day 2 here at DEF CON. It's awesome to see everybody here. What do we do for new speakers? All right, here we go. A little bit of bourbon. Ladies and gentlemen, hacking hotspots with Edward. Here we go.
Good afternoon, everyone. I want to thank everyone for just taking the time. I know this has been a long day. You know, we're about to wrap up DEF CON. This is my first DEF CON, and it's so surreal to even be here. So I just want to thank the entire community, all the hardworking staff and volunteers. So this talk is about hacking hotspots, pre-auth remote code execution, arbitrary SMS and adjacent attacks on 5G and LTE routers. I'm going to go ahead and just move forward. So before I get started, I just want to go over an agenda. We have the staple, who am I? I'm going to go over some related work. When it comes to the devices I'll be referring to, the Wi-Fi routers, we're going to be talking about Tuoshi and Kufi 5G and 4G LTE routers. It's a good chance I didn't pronounce either of those two correctly, but please bear with me here. We're also going to have some demos, and we're going to wrap it up with some conclusions. Generally speaking, this is going to go from left to right. There's a few cases where it won't be that linear, but we'll get it moving. So I want to give a quick who am I. This is pretty compository at this point, but I am currently a senior cybersecurity analyst at a Fortune 500 company. But my previous job, I worked as an information security analyst at Sedara, and honestly, it was during that time working in their security operations center that I was really able to cut my teeth by looking into IoT and Android devices. And it's really during the last 6 months while I was there that I really started to do more deep dives, and you'll see the research that is the fruit of that. I also gave a couple other talks on, I gave a talk on at ShmooCon in regards to Android inter-app collusion, and I also gave a few talks at B-Sides. So as I get into the work, we're kind of just jump into it. So this particular model is not one of the devices in question. I just want to reference a previous DEF CON 27 talk, reverse engineering 4G hotspots for fun, bugs, net financial loss. I'd really like to put some emphasis on the net financial loss, because honestly, I bought dozens of devices, and this has only been a net loss, but I'm very happy to be speaking in front of you tonight. So one of the crux of this slide specifically is the idea of manufacturers shipping items with just insecure firmware. In this case, he specifically highlights insecure API endpoints. Now, I want you to look closer at that Go form, because you're going to see that is a recurring theme. Generally speaking, when you see Go form, it's usually one of two things. It's usually either Rawlink or Realtek SDKs, where you'll see like a Go web form embedded. And as we move forward, you'll see that this particular package has had widespread systematic issues across many manufacturers. So speaking of the later lurk, I'm actually going to be talking about this reverse chronologically. I'll be talking about 5G, 4G, and LTE devices. But I want to start with this post, because essentially what happened, and the reason why I say I'm going to start reverse chronologically, is that there was a point where I had already compromised several devices by this manufacturer, but I wanted the impact of my most recent research to show these kind of errors on more modern 5G equipment. So I read this post. It says, the problem is that this guy had this Preservo. He basically states that he did find a vulnerability in the device, but he liked to have root access. But there's a fundamental issue with this whole idea of giving the device root access. It essentially has a restricted shell account. So I'm like, okay, well, that's kind of interesting. I found one of these devices for about $40 on eBay. So I'm like, this is a really good opportunity to test it out, but I want to continue on my OSINT and just get a little more is to get a little more background. So previously, when I mentioned that there was a default credentials, another researcher also indicated that in CVE 2024 48442. And it's a little, it doesn't quite specifically state that that this is actually a restricted shell, but in his write-up he goes over it. Now, another thing I'd like to bring up here is that he also found a command injection vulnerability using an AT command. Essentially, AT command are phone modem commands that allow you to do things like send SMS messages and just provide a lot of configuration things for devices. We're going to go ahead and move forward because there's a lot of information I'm going to try to squeeze into this 20 minutes here. All right, so this is actually the device in question. Now, at the beginning, it starts off slightly out of order, but things start to smooth over as you move forward. A lot of people may not have heard this company, but they actually ship a lot of products. If you go on AliExpress, you'll see a lot of devices by Tuoshi, and yeah, in this case they're shipping with 5G chips, and I'll be going over why this is a problem. So let's take a look at this Go form here. Now, if you just go to the MITRE CV website and search for Go form, when I first did this, I got about 743 results. This is just, you know, Go form appearing in like the URL or affiliated. And then, you know, as of July 1st, I searched again. We're up to 912. So I can't imagine by now it's probably over 1,000, but this is definitely a systematic issue where manufacturers are just using SDKs not so responsibly. And here's just a little breakdown. You got a little pie chart here. As you can see here, there's one larger offender, the Tinda, but you see D-Link is runner-up, and this is just basically a breakdown just based on the amount of hits, amount of CVE hits when I would search for Go form. All right. So now we're gonna go ahead and move forward. We're gonna jump into a device here. So I want you guys to take a look at this web request. This is actually the 5G device that I showed previously. And there's a few things that are going to spot out that you're going to notice right away. They're a little bit odd. So you do see that Go form, which should just be an IOC all by itself. There's probably an issue with the device, even if you just see Go form present. It's certainly worth taking a better look. But look at the username. Username equals admin. Well, that's perfectly fine if there was legitimate authentication. But if you look on the right where you see like ace_settings, if you squint, it kind of looks like a session token, but it's not. It's just UX collapsing the menu. So basically, username equals admin is enough to authenticate. Completely broken access control, but it still gets a little bit worse than this. If you look down, you'll see NTP server 0. That's for network time protocol server. In this particular device, I did find a command injection with that parameter specifically, and I'm going to go over why, how this manifested and why this is a problem, and this will be the first example. Now, because essentially authentication is broken, and this is an example of command injection, this will be our first pre-auth remote code execution. Now, sorry, this is not going to be like a sexy binary example, but here's the thing, it was so easy to do, and just think how many devices are impacted by this kind of problem. So we're going to move forward to the Gidra disassembly. When it comes to Tuoshi, both their 5G and 4G were essentially running the same binary. They're almost identical. There's a few differences, but this code remains the same, and essentially shows how you can take the network time protocol IP1 and how it's passed directly into a shell command. Very straightforward. So we're going to go ahead and just take a look and show you that. One moment. I think the demo is in a different section here. I download the slides. 1 second. I may need some assistance if someone can help me out materially. Because I uploaded all the demos, so if there's anyone available, please reach out to me. 1 moment. But I think I'm going to resolve this before that's necessary, so just bear with me here. All right, as long as these hit. All right. Complete execution. All right. Oh, that's no cute. That's no cute. Okay. You know what? If I have to log back into my Google account, I will totally do it, but I think my demos don't want to open now. That's cute. Sorry, I'm a little distracted here. All right. Gracias. All right. All right, we're going to get to demos here soon enough. Yeah. What? I don't understand what's going on here. Okay. Here's rename. Come on. I'm pretty sure I have right-click rename. Here we go. Okay. Here. Okay. Oh. All right, definitely gonna edit this part out of the final. Yeah. All right. Thank you for bearing with me here today. All right, so now I'm just going to go over what you're actually seeing in this demo. This demo is pretty straightforward. It just shows me getting a reverse shell, and you also see the contents of the little quick and dirty Python script I ran to do it. Essentially, it's just copying the request. Actually, all these headers aren't even required, but it was a quick fix, and we'll see it in action here. All right, so I'm going to go ahead and run the script, have my reverse shell, and bam, there we go, root. Here we a little anticlimactic here, but this is our first example. All right. And because I lost a little bit of time, I'm going to go ahead and move forward. But this is essentially what you see here. The contents of the root shell. I also get the root password. Oh, I'm sorry, I did forget. There's a reason why I wanted to show the entire POC. Another issue with this device is that the root password was not even AES, it was DES, and the password was essentially admin exclamation point 2 as a hard shell that can't be turned off. Is pretty bad. So let's go ahead and get back to the slide deck before I lose you guys here. All right, we're just going to keep it simple for right now here. So as you can see here, there's the contents, there's the password. I cracked it, admin exclamation point. Let's go ahead and move on because I have a lot more to go over here. And if you were wondering, like the relevance of this, whether or not you could actually access it over the internet, even though these devices are essentially designed to use like 5G as like a backup, there were some issues appears with like APN settings, and you could reach these devices over the internet, even though you're supposed to be on essentially a LAN. They were reachable. And here's a login portal if you just want to take a better look at. And essentially this device could be compromised. This is not my device. I did not test this device, but it certainly appears to be vulnerable, and it's definitely wide open to the WAN. All right, now let's go ahead and move forward to the 4G devices, because these are part of my motivation for deciding to look at 5G devices, because these were honestly quick wins. It's essentially the same thing here, so let's show you that. All right, here, so I'm not sure if you noticed the difference, but this code is pretty similar. The only reason why the 4G devices are not impacted by the NTP parameter is simply, I'm sorry, the only reason why, is because they don't expose a field for you to actually inject it, but the code is still in there. And essentially the same thing. Unsanitized input, if you can parse that directly into a shell, then you get RCE. And both of those devices are vulnerable. This POC works on both devices, and it's almost universal across that manufacturer. Let's move forward to the next demo here. Demo 2, show that in action. All right. All right, so this is pretty straightforward. It essentially shows me trying to initially log into the device without knowing the password until I'm able to successfully show the command injection. And yeah, I'm gonna go ahead and run the script. It's not super visual. Right here, I'm just showing the contents of the script just for reference here. And let's go ahead and just skip a little forward because I am a little short on time here. All right, so what you see here is failed password attempts because I don't have the correct thing. And then, yeah, we get root access. So let's move a little forward here. I do apologize because I'm trying to get through all this. But here I just wanted to show the route, just to show that, you know, the fact that this was exposed over the internet and over the WAN as well. So in my opinion, pretty bad, pretty bad. Like I said, this is a short talk. I'm not going to go super deep into the weeds, but I wanted to address a systematic issue across many manufacturers. All right, so we're on to the second vendor, Kufi. They have a few products here. I'm going to be showing 3 4G devices and 1 5G device at the very end here. And you know, this is a standard model GC111. I've noticed that in terms of industry, a lot of these devices are used in vehicles. I've even heard situations where these devices could be used to power like motor cameras. So, yeah, I had a few issues with this device. You know, when you're trying many different paths to exploitation, I quickly realized that this device used canaries, and you know, I'm not a binary ninja, so had to make do with what I could. But you know, given enough opportunity, you'll be surprised what you can find. There's 3 vulnerabilities I found here, and yeah, in this case, because I said this is very condensed, I'm going to just explain what's going on here. Essentially, when I look at most devices, there's usually 2 quick, easy paths for command injection. When it comes to routers and embedded devices, it's usually ping, traceroute, or Wi-Fi. It seems really common that both of those 2 things are piped into shell commands on the back end, and Wi-Fi seems to be just as, I mean, I find devices where both the parameter was vulnerable to command injection and like cross-site scripting, so certainly interesting. But in this case, you see, if you take the Wi-Fi name, you can directly pipe it into a shell command, and because the whole authentication is username equals admin, well, it's essentially unauthenticated. That's not authentication to me. That is certainly broken. Can you see them now? Okay. All right, so this is pretty straightforward. We see that vulnerable endpoint, and we see go form essentially in the URL path here, and yeah, now in this example, because I essentially already had root access device because this device shipped with hard-coded telnet admin root. So it was very easy to get feedback to test to see if my command injection, because I already had root access. Now that account was hard-coded, but essentially for this device, the Wi-Fi parameter was vulnerable to command injection, and that gives me pre-auth RCE. I'm not going to bore you guys with this whole demo because I'm kind of short on time here, but we're going to move forward because that was pretty straightforward. All right, here's the next device. This device is actually a little bit more interesting. It's another 4G device. But it's a device that I wasn't initially able to get fully pre-auth, but maybe one theoretical one. So let's see what I'm talking about here. So I did find another vulnerable parameter to command injection. In this case, it's an APN setting. It's essentially part of the embedded Android package for the device because it has an embedded hotspot. So when you're setting the pin code, allowed command injection, but this thing was vulnerable to both command injection and buffer overflow. I actually got the buffer overflow to work after I realized it was vulnerable to command injection, but it was certainly interesting to see the parameter vulnerable to both because essentially, if you see at the bottom, you'll see call shell, AC stack. You'll see that this information is sent to the stack without verifying the lints, and I'm going to show a demo of how this can be a problem. Demo 4. So for this device, although I did find a command injection, the command injection required authentication. So this is going to be an example of a cross-site request forgery in order to trigger the command injection, which is semi-unauthenticated. I guess it really depends on, yeah, so 1 second. All right, wait, make sure I'm on the right slide. All right, there we go. All right. All right, so you see this, see the embedded web form and the website. It looks a little bit dated, but oh, am I showing the right demo? Okay, yeah. So we're going to do this a little backwards. In this case, this is going to be an example of me breaking the device, and that I was not able to recover even after trying to connect to UART because I overwrit too much memory. But this is an example of in this case, a buffer overflow. There's no stack canary, so there's theoretical RCE via binary exploitation here. This is just an example of denial of service, and I have another example of chaining the cross-site request forgery with command injection to get like quasi pre-auth RCE. So we're gonna just show that. All right. All right, so what we see here, essentially you see here is the beginning of a telnet prompt. Initially, telnet is disabled on this device, but I'm going to go ahead and start the telnet daemon by using the cross-site request forgery. So, all right, and I'm going to speed up here. Yeah, so at first invalid because I obviously didn't have the telnet service active, and now I'll be able to get in there. Well, besides the little typo you see on the screen, we're gonna ignore that, guys. A few more moments. All right, and we see the credentials here from an exploit administrator. So that's pretty straightforward. All right, we're gonna move forward here. All right, so this device, I'm going to show an example of the arbitrary SMS, which is part of the title here. Once again, Android is essentially baked into this device, our CPF 908. And just to give a little context when it comes to AT commands, here's some examples of things that you can do. Having this kind of low-level control over a device can certainly lead to compromise. You can like read messages, send messages, and so forth. And I'm going to show an example of how I link all this together. I think something's out of order. Why am I? Okay, let's try demo 6. I'm going to show you what's going on here. All right, here's my phone. All right, so the problem with this device is that essentially there's a vulnerable endpoint that allows me to have admin privileges without fully authenticating. And if you see here, it's go form again. So no authentication required. Go form is hit, and because AT commands allow you to do arbitrary things, you could force a device to send SMS messages. It can certainly be problematic, along with information disclosure. All right, so this is an example of a 5G Kufi device, chipset Snapdragon X62. And these are a little bit more expensive, since a lot of 5G devices usually will give you a premium over 4G. But it makes sense, we're almost at 6G at this point. I'm going to show you an example of sending an arbitrary SMS message with this device as well. We're going to go over to demo 7, and we are almost done here. All right, so now when it comes to this device, I actually wasn't able to get a root shell on this device. I did show broken access control and the ability to exploit these vulnerable endpoints. I bought dozens of devices, usually single copies. I don't have a budget to buy multiple devices and break them the proper way that you see a lot of researchers do. So this is all me just kind of winging it on one devices only, and I wasn't willing to break it. So in this case, it just shows information disclosure initially, like you can reveal the admin password, and I think just showing passwords, allowing me to text people, it's a very bad situation. And these things aren't cheap. That device is like $400 now. I bought it at $200, but it went up. Surprisingly, not exactly cheap. And you see credentials are being disposed here, but you guys can look at this later. I'm gonna move forward just because we're short on time here. But definitely appreciate your patience here. And we have another demo. All right, so it's essentially I'm just displaying the contents of the Python script. I'm just going to show without being authenticated, just forcing SMS. And the thing about it is that these devices don't really advertise that you can even send SMSs in the first. So it just seems like a lot of functionality to have essentially no good keys attached to it. So. In a few moments here, you're going to see the text message. What's really interesting is that in order to test these, because these are foreign products and they use bands that aren't all available in the United States, I had to get some prepaid SIM cards, and they specifically said no data or SMS access. Yet I was able to do this, so I thought it was interesting. Like no SMS, but it still works. Yeah. So. Hurry it here. Bear with me. When it rains, it pours. All right, so I'm just going to go over the obviously conclusions. We have the improper access control, information disclosure, lack of input sanitization, all sorts of issues. The main thing is that I really feel like vendors should be required to have a solid software bill of materials. We simply shouldn't be in a situation in 2025. I mean, these devices I'm showing you, they're like post 2020, so it's still relatively new, and we're still having systematic issues across our industry. So I'm hoping this talk just, if nothing else, showed light on how easy it is to hack LT devices, and to certainly take a look at GoForm if you see it. I want to thank you all for bearing with me here and all the hiccups I've had, and I just hope you guys enjoy the rest of DEF CON and have a great day.